Hello everyone. Welcome to this Data Scientist full course video by Simplilearn. Data scientists are professionals who utilize their skills to analyze, visualize and find trends in the data. They uncover solutions to business challenges by creating models and generating insights. In this video, we will cover all the important data science concepts, skills and careers that will help you become a successful data scientist. But before we get started, please make sure to subscribe to the Simplilearn channel to learn new technologies and upskill yourself. We will start by understanding the basics of data science with a short animated video and look at data science lifecycle and its applications. We will then see the different Python libraries for data science such as Numpy and Pandas. Next, we'll focus on learning the crucial algorithms used in data science for solving specific problems. Next, we'll look at linear regression, logistic regression, decision trees, support vector machines, as well as some reinforcement learning algorithms. After that, we'll see the data science job roles and responsibilities, the skills that you need to possess, and understand how to build a data science engineer resume. Finally, you'll get an idea about the top data science interview questions that are often asked in any job interview. This includes programming, SQL, statistics, machine learning, as well as some scenario-based questions. So let's get started with understanding data science with a short animated introduction.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science, because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In her meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you.
Hi guys, I'm Rahul from Simplilearn, and today I'm going to tell you how you can become a successful data scientist. Now before I begin, let me give you an example. Say you're at home and you're bored and you feel like watching a TV show or a movie. Then you get on Netflix. You scroll through all the TV shows and movies that they offer. Then you're recommended the latest season of Daredevil because you've seen shows similar. We all enjoy binging shows on Netflix. But do you actually know how much of data science is used along with Netflix? Netflix analyzes the user's behavior from hundreds of different TV shows and movies to create the best recommendations for everyone. They measure user engagement and retention on various shows. Now, currently they're even applying advanced metrics that include when you pause, rewind, or fast forward. That's when you see something really cool and you want to watch it again. What day you watch the content. For example, some days you feel like watching a comedy show, sometimes drama, and so on. When and why you leave the content, when you stop watching a show, why did you stop? What time you watch, which content. Children tend to watch in the morning and adults when they return from work. From where you watch in the world, searches for the show, the ratings given, browsing and scrolling behavior, and what device you watch the program on. Netflix uses data science to show better movie and show recommendations, at the same time creating better shows for the users. There are 33 million different versions of Netflix, says Joris Evers, who's the director of global communications. Netflix at the moment has more than 125 million users worldwide, which means on an average, only 4 people get the same iteration of Netflix. This is because of all the personalization that is done to suit the user's needs. Or did you also know that the popular show House of Cards was created completely using data science and big data? This was using the advanced metrics that I mentioned earlier. Netflix collected user data from another show called The West Wing. From this, they took into consideration where people rewound a particular scene, when they fast forwarded, and when they stopped watching the show. With this, they were able to create what they believed was a perfectly engrossing show. Data science is the area of study which involves extracting knowledge from all the data that you can gather. Now that you understood what data science is, let's talk about what a data scientist does. We'll go through all the skills that are required by a data scientist. A data scientist needs to have the following 7 skills: database knowledge, statistics, programming tools, data wrangling, machine learning, big data, and data visualization. Let's go one by one. Skill number 1, database knowledge. Gaining database knowledge is required to store and analyze data. Oracle database, SQL Server, MySQL, and Teradata are some of the tools that are required for this. Skill number 2, statistics. Learning statistics, probability, and mathematical analysis. Statistics is a science concerned with developing and studying methods for collecting, analyzing, interpreting, and presenting empirical data. Skill number 3, programming. Mastering one programming language. Programming tools such as R, Python, and SAS are very important to perform analytics in data. R is a free software environment for statistical computing and graphics. It supports most machine learning algorithms for data analytics like regression, association, clustering, and so on. Python is an open source general purpose programming language, and libraries such as Numpy and SciPy are used in data science. SAS can mine, alter, manage, and retrieve data from a variety of sources. It can also perform statistical analysis on the data. Skill number 4, data wrangling. Learning how to wrangle data. Data wrangling involves cleaning data, manipulating data, and organizing the data. Some of the tools that are used are R, Python, Flume, and Scoop. Skill number 5, machine learning. To master the concepts of machine learning. Machine learning provides systems the ability to automatically learn and improve with experience without being actually programmed to do that. Machine learning can be achieved through a number of different algorithms like regression, naive-bayes, SVM, k-means clustering, KNN, decision tree, just to name a few. Skill number 6, big data. Having working knowledge of big data tools. Big data is a term that is used to describe large and complex data that cannot be dealt with traditional data processing software. Some of the tools that are used or softwares that are used are Apache Spark, Hadoop, Talent, Tableau, Splunk, and so on. Number 7, data visualization. To develop the ability to visualize results. Data visualization involves integrating different data sets, analyzing models, and visualizing them in the form of diagrams, charts, and graphs. Some of the tools or softwares that are used are Tableau, ClickView, Power BI, and Google Data Studio. Let's talk about some of the job roles in data science. We have data scientist, data engineer, data architect, data analyst, business analyst, and data administrator. Let's go one by one. Data scientist. A data scientist earns around $120,000 per year, and these are their responsibilities: to create data-driven business solutions and analytics, drive optimization and improvement of product development, to use predictive modeling to increase and optimize customer experience, revenue generation, targeting, and so on, and coordinating with different functional teams to implement models and monitor their outcomes. Data engineer. A data engineer earns around $130,000 per year. Some of the responsibilities are assembling large complex data sets, to identify, design, and implement internal process improvements, to build infrastructure required for optimal extraction, transformation, and loading of data, to build analytics tools that utilize the data pipeline. Data architect. A data architect earns around $112,000 per year, and these are their responsibilities: to develop database solutions, to install and configure information systems, to analyze structural requirements for new software and applications, to migrate data from legacy systems to new solutions. Data analyst. A data analyst earns around $65,000 per year, and these are their responsibilities: to interpret data and analyze results using statistical techniques, to acquire data from primary or secondary data sources and maintaining databases, to develop and maintain data analyses, data collection systems, and other strategies, working with management to prioritize business and information needs. Business analyst. A business analyst earns around $70,000 per year, and these are their responsibilities: to assist the business with planning and monitoring, eliciting and organizing requirements, validating the resource requirements and developing cost estimate models, creating informative, actionable, and repeatable reporting. Data administrator. A data administrator earns around $54,000 per year, and these are their responsibilities: assisting in database design and updating existing databases, setting up and testing new database and data handling systems, sustaining the security and integrity of data, and creating complex query definitions that allow data to be extracted. Now let's talk about some of the various skills that are required for the job. It's very important that a data analyst has a sound knowledge in programming tools, data visualization and communication, and data wrangling. A data architect needs to know a lot about programming tools, database knowledge, statistics, mathematics, and linear algebra. A data engineer must be good with programming tools, database knowledge, data wrangling, and software engineering. A business analyst needs to be good at data visualization and communication, statistics, data wrangling, and machine learning. A data administrator needs to be good with programming tools, database knowledge, and data wrangling. Now, however, a data scientist needs to be good at programming tools, data visualization, database knowledge, statistics, data wrangling, and machine learning. They also need to know a good amount of knowledge on software engineering, mathematics, and linear algebra, which means you basically need to know everything about the data. This goes to show that being a data scientist isn't easy, but it also cements why it is one of the most lucrative jobs in data science. Now, Simplilearn also provides certifications in data science. It provides a data science certification, which is a master's program. Under this program, we have courses in data science with SAS training, data science certification training with R programming, big data, Hadoop and Spark developer, data science with Python, business analytics with Excel, machine learning, deep learning with TensorFlow. We also have an integrated program in big data and data science, which is also a master's program.
So what is data science? Data science is the field of study that deals with modern scientific techniques, statistical methods, and algorithms to derive insights from vast volumes of data. Companies using data science are very numerous. With companies generating data every minute, there is a need to make sense of this data. Mu Sigma, Fractal, Fidelity, Intel, Genpact, Qubela, Amazon, Trendence, Connect the Dots. Just about every business out there nowadays uses some form of data science, even if it's indirectly, to help govern their business and help them grow and compete in the business world. And we use the data science to find unseen patterns within the data, analyze and draw insights from our data, and solve business problems and make decisions. And the data science has a life cycle. We start with our data discovery. Then we go through data preparation, exploratory data analysis, data modeling, interpret the results, and back to data discovery. When we talk about data discovery involves asking the right questions, identifying the business problems, finding the best solution, and gathering correct data from relevant sources for analysis. This is, in the data science life cycle, the most important step. Now, in general, it only involves like a small percentage of the time you spend on this. But if you're not asking the right questions, you can't go in the right direction. Data preparation. Data preparation deals with cleaning the data, finding the inconsistencies, tackling missing values, converting it into the right format, and making it ready for analysis. When I'm running the data science lifecycle, this is probably where the most time is spent. Data can be so messy. You have to break it down into different parts. You have to import the different pieces from different databases. Are you dealing with straight numbers off of spreadsheets and cells, or are you dealing with text documents and natural language tokenization? Exploratory data analysis. Analyze and visualize the data using different charts and graphs to find significant patterns and hidden trends. That helps to understand the data better. The building of the charts is very creative. Probably one of the more enjoyable parts is be able to come in there and describe the data and show that to the shareholders. Then we dive into data modeling. Use classification, regression, and clustering algorithms to build machine learning models that can help predict and forecast future trends. This is where we start getting into predictions. What's next? Where's it going to go? And then interpret the results. Validate the model results, draw the final conclusion, and check if the performance of the model is in line with the requirements. The final step is the one that you set up in front of the board members and give them suggestions as to what's next. Where are we going to spend our marketing money? Where are we going to start preparing our firefighters for the next fire breaks next year? What is the weather patterns coming in? This is where you interpret the results and say how accurate they are. Are they valid? Is it something we're going to keep, or are we going to throw it out and have to start over? When we look at data science components, there's the mathematics, statistics, domain expertise, data engineering, data visualization, and machine learning. When we sum this up in data science, really this point in all of this you want to focus on first is domain expertise. Now, when you're taking your classes, obviously you want to go through the mathematics, the statistics, the data engineering, the data visualization, the machine learning, and learning all those tools. But it really, in the job field, the domain expertise comes in. Because if you're really good with business and you go into business with these tools, then you're able to ask the right questions and deal with it. When we talk about the tools in data science and where they sit, there is a data analysis. Data analysis focuses more on statistics and mathematics, where the data science side focuses more on the machine learning, data visualization. And then there's database management, which really focuses on the data engineering part of it and how to manage that data and the data flow. And you can see all these components come together, and then they form the data science. And we talk about tools in data science. We have SAS, we have MATLAB, we have SQL, you have your Apache Spark, your R, Tableau, Python. Right now in the programming languages, Python is probably the most widely used, with R coming in a close second. The reason for that is these are both open source and anybody can use them. When we look at SAS and Tableau, those are two packages that are paid for, which have a lot of automation behind them. So a lot of larger companies will pay for those packages because they help work out a lot of the back-end stuff before you even need to use them. And of course we have Apache Spark. You almost have to know Apache Spark and the growing data lakes today. That's your big data. How do you distribute this if you're going to process it over a large amount of data? When we look at data science applications, there's internet search, very common. You enter your Google thing and it uses the data science algorithms to figure out what to return. Voice assistants, analyzing the voice coming in and connecting it with whatever patterns they need to activate so you can ask it to turn your lights on in the living room. Healthcare, biggest field growing right now. How do we analyze health data from a smartwatch and figure out how to know when a disease is being spread across the world? Healthcare, how do we identify cancer versus non-cancer so we know who to prioritize and get them in for surgery where other people might not need that immediate care? And even identifying problems somebody might have with their health long before they even happen. What a neat thing to do instead of waiting until you have a heart attack to know months ahead of time that you're having heart conditions. Logistics, how do we get from point A to point B? If you ever look at some of the major distributors, they pre-ship things based on what they guess people are going to need. This way you get your stuff right in the mailbox the day after you order it. E-commerce. huge in there because you have to know what kind of marketing we're going to put out. Who are we selling to? What's our target audience? Robotics. One of the funner ones when you're coming up into the future is how do we automate the different tasks we have, from self-driving cars to manufacturing lines to maybe even a self-robotic chef in the kitchen. So when we talk about solving problems with data science, we have to ask possible questions and the desired algorithms. And these really are kind of an overview of some of the terminology you'll want to know in data science. So when we talk about that, how much or how many, we're talking about regression. Regression basically means a number. If you've ever seen stock charts, you see the guess at what the next sales price is or buy price is. That's all on your regression side. Is it A or B? Classification. Is that a dog or a cat that my photo took a picture of? How is this organized? Clustering. This is where we take things that look alike and put them together so that we can then make predictions on it. How different is this? Just like you have clustering, you have the opposite, anomaly detection. How do we find things that don't fit in? Where are the outliers? What are things we might need to look at that aren't in our model? And what to do next? Reinforced learning. This is probably the newest market, is how do we set something up where as the data comes in, it learns from the new data as to what the next action is going to take. Most of these are combined. So when we talk about regression, classification, clustering, anomaly detection, reinforced learning, a lot of times when you put your model together, you might have multiple parts of this. We might look at the clustering of data and then feed it into a classification. Is this a bad loan to make at the bank, or is this a good loan to give? And from there we might start looking at, when we start clustering these things as good and bad and what kind of setup is, we then might run it through a regression model to say, hey, what is the dollar amount this person should be allowed to take a loan out? And you can see that all of these start coming in, and then a lot of the models, reinforced learning, we talk about like bank loans and things like that, once a year they have to rerun those algorithms. And so that's like a human run reinforced learning. Now we're starting to automate that so that as the data comes in real time, the models start updating themselves. They start figuring out a way to solve new problems as they occur. And of course in robotics, reinforced learning is one of the biggest growing fields. Algorithms used in data science. Linear regression. Logistic regression. When you're looking at both of these, think numbers. We're talking regression models. And so linear regression figures out the best line through the data. Maybe it's looking for a curved line. Logistic regression starts looking at data on a continuum so that it goes to an exponential. You have a spot where it might be one or the other, and then you know what it is as it goes to one side or the other. Decision tree. Wonderful tool. If you they used to call it a hack, now it's becoming mainstream, to look at the back end, what made the decision. So it's really easy to trace back to how you arrived at the decision. Decision trees are kind of nice that way. Nearest neighbors. K nearest neighbors is your clustering. K means clustering. Hierarchical clustering. So hierarchical starts dividing them and builds a hierarchy where the K means and the K nearest neighbor look for things that kind of connect each other. How close are they in data format? DB scan, another form of clustering your data. Principal component analysis. So we start breaking up and looking at the different components in our data coming in. These are all algorithms used in data science, and there are more. These are kind of the mainline ones. And each one of these has many settings which you can play with to build a better model to predict your data and where you want it to go.
So let's now talk about the difference between business intelligence and data science. Now, business intelligence was one of the initial phases where people started making or wanted to make some sense out of data. So for some of you who may not be aware, there were multiple phases of this IT revolution. So initially there was all automations. You had automation of your selling process, manufacturing process, you had your ERP systems, your CRM systems, and so on, which are basically enterprise resource planning and customer relationship management, ERP and CRM. And all these enterprise applications were generating a lot of data. So then people started saying that, okay, we need to understand or get some information out of this data. So that's how business intelligence started. So if we take from a data source perspective, let's compare these with each of these criteria. The criteria are: what is the data source, what is the method, what are the skills, and what is the focus. Now, if we compare business intelligence with data science, this is how it looks. As far as the data source is concerned, business intelligence was primarily using structured data. So you had all your enterprise applications like ERP, CRM, and so on, and they were working out of pretty much RDBMS, relational database management systems like Oracle or MS SQL, MySQL, and so on. So all this data was structured in neat form of tables, rows, and columns, and then they were all brought into a centralized place, because remember, these were still different applications, so they were working off different databases in silos. So if you wanted to get a combined view, you needed to create what is known as a data warehouse and bring all this data together and then look at it in a uniform way. So this is what business intelligence was doing. Pretty much it was structured data, and it had reports and dashboards. That was pretty much of what was there in business intelligence. Now, with data science, in addition to structured data, we also use a lot of unstructured data. Example, web logs or comments. If we are talking about customer feedback, there is a structured part, there is an unstructured part where people write free text. Data science includes that as well and brings everything and then performs analysis. So data source wise, that is the difference. Now, methods. In business intelligence, pretty much it is analytical in the sense that, okay, you have some data. We are just trying to present the truth and mostly what has happened. Historical data. That's it. In case of data science, we go beyond that. We go deeper in terms of finding why a certain behavior has occurred, and also go beyond just providing a report. There is a deeper statistical analysis that is done. That is what is the scientific part. And deeper insights are gathered, not just reporting. So that's from a method perspective. From a skills perspective, business intelligence needs a little bit of statistics, but more of visualization, because they primarily consisted of dashboards, or they primarily consist of dashboards and reports. Whereas in data science, the visualization, of course, is there, but there is a lot more of statistics involved, because we are looking at things like correlation. We are looking, for example, if we perform machine learning, we try to do regression, try to predict what will be the sales maybe in the future, and so on and so forth. So it is much more involved in case of data science compared to business intelligence. The skills are many more compared to business intelligence. And last but not least, what is the focus? Focus of business intelligence is pretty much historical data. So the sales have happened. Based on the sales till today, you try to come up with a report. What was my sales maybe for this whole year, or maybe for the last 5 years, and so on and so forth. In data science, you take historical data, but you also combine that with maybe some other required information, and you also try to predict the future. So we try to extrapolate maybe the sales and say, okay, sales as of now, as of today, the sales is 5 million, and if we, based on the historical information, we see that sales increase on a maybe, monthly basis 10%. That is what history says. So our sales for next month will be this much, right? So that is the focus of data science. It goes beyond just reporting. So what are the prerequisites for data science? There are 3 essential traits required to be a data scientist. One is curiosity. You need to be able to ask questions. The first step in data science is asking questions. What is the problem we are trying to solve? If you ask the right question, only then you'll get the right answer. Very often, this is a very crucial step where a lot of data science projects fail, because you may be asking the wrong question. And then obviously when you get the answer, that's not the answer you're looking for. So it is very important that you ask the right question. Needless to say, then the second part, or the second trait, is common sense. So you need to be creative. You need to come up with ways to use the data that you have and try to solve the business problem on hand. In many cases, you may not have all the data that you need. In many cases, the data may be incomplete. So that is where you need to come up with ways, what are the best ways to fill these gaps wherever this is missing. And that's where common sense comes into play. Last but not least, after doing all this analysis, if you're unable to communicate the results in the right way, the whole exercise will fail. So communication is a key trait for a data scientist. Maybe technically you may be a genius, but then if you are unable to communicate those results in a proper way, once again, that will not help. So these are the three main traits: curiosity, common sense, and communication skills. In a way, you can say these are the three C's. Okay, so what are the other prerequisites? The first one, so machine learning. Machine learning is the backbone of data science. Data science involves quite a bit of machine learning in addition to the basic statistics that we do. So a data scientist needs to have a good hang or need to be very good at data science. The second part is modeling. So modeling is also a part of machine learning in a way, but you need to be good at identifying what are the algorithms that are most suitable to solve a given problem, what models can we use, and how do we train these models, and so on and so forth. So that is the second component. Then statistics. Statistics is like the core foundation of data science. So you need to understand statistics and you need to have a good hang of statistics in order to be a good data scientist. And this will also help in getting good results. Programming is to some extent required. At least some program or the other would be required as a part of executing a data science project. The most common programming languages are Python and R. Python especially is becoming a very popular programming language in data science because of its ease of learning, because of the multiple libraries that it supports for performing data science and machine learning and so on. So Python is by far one of the most popular languages in data science. If any one of you is wanting to learn a new language, that should be Python. And then of course you need to understand databases, how databases work, and how to handle databases, how to get data out of databases, and so on. So these are some of the key components of data science. Now, coming to the tools and skills that are used in data science. These are some of the skills from a language perspective. It is Python or R. And from a skills perspective, in addition to some of the programming languages, it would help if you have a good knowledge or good understanding of statistics. And what are the tools that are used in data analysis? SAS is one of the most popular tools. It's been there for a very long time, and that's the reason it is very popular. And however, this is compared to most of the other tools, it is a proprietary software, whereas Python and R are mostly open source. The other tools are like Jupyter Notebooks. You have RStudio. These are more development environments and development tools. So Jupyter Notebooks is a interactive development environment. Similarly, RStudio is for performing or writing R code and performing analytics and performing data analysis and machine learning activities. You can perform in RStudio. It has a very nice UI, and initially R was not so popular primarily because it did not have user interface, and RStudio is a relatively new addition, and after the advent of RStudio, R became extremely popular. And there are other tools like MATLAB, and of course some people do with Excel as well. As far as data warehousing is concerned, some of the skills that are required are ETL. So in order to extract data and transform load, ETL stands for extract, transform, load. So you have data in the databases like your ERP system or a CRM system. You need to extract that and then do some transformations and then load it into your warehouse so that all the data from various sources looks uniform. Then you need some SQL skills, which is basically querying the data, writing SQL queries. Hadoop is another important skill, especially if you're handling large amounts of data. And also one of the specialities of Hadoop is it can be used for handling unstructured data as well. So it can be used for large amounts of structured and unstructured data. Then Spark is an excellent computing engine for performing data analysis or machine learning in a distributed mode. So if you have a large amount of data, the combination of Spark and Hadoop can be extremely powerful. So you store your data in Hadoop HDFS and use Spark as your computation engine. It works in a distributed mode similar to Hadoop in like a cluster. So those are excellent skills for data warehousing. And there are some standard tools that are available like Informatica, DataStage, Talent, and also AWS Redshift if you want to do some on the cloud. I think AWS Redshift is again a good tool. Data visualization tools. For data visualization, some of the skills that would be required are, let's say, R. R provides some very good visualization capabilities, especially for developing during development. And then you have Python libraries, Matplotlib, and so on, which provides very powerful visualization capabilities. And that is from skills perspective. Whereas tools that can be used are Tableau is a very, very popular visualization tool. Again, that's a proprietary tool, so it's a little expensive maybe, but excellent capabilities from a visualization perspective. Then there are tools like Cognos, which is an IBM product which provides very good visualization capabilities as well. And then coming to the machine learning part of it, the skills required there are Python, which is more for programming part, and then you will need some mathematical skills like algebra, linear algebra especially, and then statistics and maybe a little bit of calculus and so on. And the tools that are used for machine learning are Spark MLlib and Apache Mahout. And on cloud, if you want to do something, you can use Microsoft Azure ML Studio as well. So these are by no means an exhaustive list. There are actually many, many tools and probably a few more skills also may be there. But this gives a quick overview, like a summarization of the tools and skills. Now, moving on to the life of a data scientist. What does a data scientist do during the course of his work? So let's see. So typically, a data scientist is given a problem, a business problem that he needs to solve. And in order to do that, if you remember from the previous slide, he basically asks the question as to what is the problem that he needs to solve. So that is the first thing. He has got the problem. Then the next thing is to gather the data that is required to solve this problem. So he goes about looking for data from anywhere. It could be the enterprise. Very often the data is not provided in the nice format that he would like to have it or we would like to have it. So first step is to get whatever data that is possible, what is known as raw data in whatever format. So it could be enterprise data, it could be, there is probably a requirement to go and get some public data in some cases. So all that raw data is collected and then that is processed and analyzed and prepared into a format in which it can be used. And then it is fed into the analytics system, be it a machine learning algorithm or a statistical model, and we get the output. And then he puts these output in a proper format for presenting it to the stakeholders and communicating those insights or the results to the stakeholders. So this is a very high level view of like a day in the life of a data scientist. So gathering data, raw data, performing some quick analysis on that and maybe processing or manipulating this data to bring it into a certain good format so that it can be used for the analysis, feeding this into that analysis system that has been designed, be it mathematical models, machine learning models, and then get the results, the insights, and then present it in a nice way so that the stakeholders can understand. How about machine learning algorithms? So let's see what are the various machine learning algorithms that would be required for a data scientist. So these are a few of the algorithms. Again, there's not an exhaustive list. We have regression is one of the supervised learning models or techniques. So in case of regression, you try to, let's say, come up with a continuous number. So the difference between regression and let's say a classification is that in case of classification, those are discrete values. Whereas here we are talking about regression, where let's say you are trying to predict the temperature, which is a continuous value, or the share price, which is a continuous value. So that is regression. So you need to know what is regression, how to perform regression, and we need to understand clustering. So clustering is one of the unsupervised learning techniques. In this case, there is no label data that is available, and you get some data and then you want to put this into some shape so that you can analyze it and you try to make sense out of it. Let's say you have, one example is you have a list of cricketers and they have not been marked as bowlers and batsmen or all-rounders or whatever, right? So you just have their names and maybe how many runs they scored, how many wickets they have taken, and so on. But there is no readily available information saying that, okay, this person is a batsman, this person is a bowler, and so on. So I'm talking about cricket. Hopefully, most of you are familiar with the game of cricket. So how do we find out? So then we put this into a clustering mechanism, and then the system will say that, okay, these are the people who have all scored good amount of runs. So they belong to one cluster. These are all the people who have taken good amount of wickets. So they belong to one cluster. And maybe here are some people who have taken good amount of wickets and they have made good amount of runs. So they may be belonging to one group. And then we take a look at it and then we label them as, okay, people who have all together and those who have, scored many runs, we label them as batsmen. People who have taken a lot of wickets, we label them as bowlers, and people who have taken good amount of wickets and also made some good runs, we label them as all-rounders. But the system will just say, okay, this is cluster 1, cluster 2, cluster 3. The names we human beings have to give the names. Now, decision tree is used for what is known as classification. Primarily, it can also be used for regression, but by and large, it is used for classification. And here again, it's a very logical way in which the algorithm goes about classifying the various inputs. One of the biggest advantages of decision tree is that it's very easy to understand and it's very easy to explain why a certain object has been classified in a certain way compared to maybe some of the other mechanisms like, say, support vector machines or logistic regression and so on. So that's the advantage of decision tree, but that is also a very popular algorithm. Then we have support vector machines primarily for classification purpose, and then we have naive Bayes. This is again a statistical probability based classification method. So these are a few algorithms. There are a few more that are not listed here, but there are some more algorithms as well. And by the way, there are detailed videos about each of these algorithms available. You can check in the playlist. So now let's talk about the life cycle of a data science project. Okay, the first step is the concept study. In this step, it involves understanding the business problem, asking questions, get a good understanding of the business model, meet up with all the stakeholders, understand what kind of data is available, and all that is a part of the first step. So here are a few examples. We want to see what are the various specifications, and then what is the end goal, what is the budget, is there an example of this kind of a problem that has been maybe solved earlier. So all this is a part of the concept study. And another example could be a very specific one to predict the price of a 1.35 carat diamond. And there may be relevant information, inputs that are available, and we want to predict the price. The next step in this process is data preparation, data gathering and data preparation, also known as data munging, or sometimes it is also known as data manipulation. So what happens here is the raw data that is available may not be usable in its current format for various reasons. So that is why in this step, a data scientist would explore the data. He will take a look at some sample data, maybe pick, if there are millions of records, pick a few thousand records and see how the data is looking. Are there any gaps? Is the structure appropriate to be fed into the system? Are there some columns which are probably not adding value, may not be required for the analysis? Very often these are like names of the customers. They will probably not add any value or much value from an analysis perspective. the structure of the data. Maybe the data is coming from multiple data sources and the structures may not be matching. What are the other problems? There may be gaps in the data. So the data, all the columns, all the cells are not filled. If you're talking about structured data, there are several blank records or blank columns. So if you use that data directly, you'll get errors or you'll get inaccurate results. So how do you either get rid of that data or how do you fill these gaps with something meaningful? So all that is a part of data munging or data manipulation. So these are some additional subtopics within that. So data integration is one of them. If there are any conflicts in the data, data may be redundant. Yeah, data redundancy is another issue. There may be, you have, let's say, data coming from two different systems and both of them have customer table, for example, customer information. So when you merge them, there is a duplication issue. So how do we resolve that? So that is one. Data transformation. As I said, there will be situations where data is coming from multiple sources and then when we merge them together, they may not be matching. So we need to do some transformations to make sure everything is similar. We may have to do some data reduction. If the data size is too big, you may have to come up with ways to reduce it meaningfully without losing information. Then data cleaning. So there will be either wrong values or null values or there are missing values. So how do you handle all of that? A few examples of very specific stuff. So if there are missing values, how do you handle missing values or null values? Here in this particular slide, we are seeing three types of issues. One is missing value. Then you have null value. You see the difference between the two, right? So in the missing value, there is nothing, blank. Null value, it says null. Now, the system cannot handle if there are null values. Similarly, there is improper data. So it's supposed to be numeric value, but there is a string or a non-numeric value. So how do we clean and prepare the data so that our system can work flawlessly? So there are multiple ways and there is no one common way of doing this. It can vary from project to project. It can vary from what exactly is the problem we are trying to solve. It can vary from data scientist to data scientist, organization to organization. So these are like some standard practices people come up with. And of course, there will be a lot of trial and error. Somebody would have tried out something and it worked and will continue to use that mechanism. So that's how we need to take care of data cleaning. Now, what are the various ways of doing, if values are missing? How do you take care of that? Now, if the data is too large and only a few records have some missing values, then it is okay to just get rid of those entire rows, for example. So if you have 1 million records and out of which 100 records don't have full data, so there are some missing values in about 100 records. So it's absolutely fine because it's a small percentage of the data. So you can get rid of the entire records which have missing values. But that's not a very common situation. Very often you will have multiple or at least a large number of a data set. For example, out of 1 million records, you may have 50,000 records which are like having missing values. Now, that's a significant amount. You cannot get rid of all those records. Your analysis will be inaccurate. So how do you handle such situations? So there are again multiple ways of doing it. One is you can probably, if a particular values are missing in a particular column, you can probably take the mean value for that particular column and fill all the missing values with the mean value. So that first of all, you don't get errors because of missing values. And second, you don't get results that are way off because these values are completely different from what is there. So that is one way. Then a few other could be either taking the median value or depending on what kind of data we are talking about. So something meaningful we will have put in there. If we are doing some machine learning activity, then obviously as a part of data preparation, you need to split the data into training and test data set. The reason being, if you try to test with a data set which the system has already seen as a part of training, then it will tend to give reasonably accurate results because it has already seen that data, and that is not a good measure of the accuracy of the system. So typically you take the entire data set, the input data set, and split it into two parts. And again, the ratio can vary from person to person, individual preferences. Some people like to split it into 50-50. Some people like it as 63.33 and 33.3 is basically 2/3 and 1/3. And some people do it as 80-20. 80 for training and 20 for testing. So you split the data, perform the training with the 80%, and then use the remaining 20% for testing. All right. So that is one more data preparation activity that needs to be done before you start analyzing or applying the data or putting the data through the model. Then the next step is model planning. Now these models can be statistical models, this could be machine learning models. So you need to decide what kind of models you're going to use. Again, it depends on what is the problem you're trying to solve. If it is a regression problem, you need to think of a regression algorithm and come up with a regression model. So it could be linear regression. Or if you're talking about classification, then you need to pick up an appropriate classification algorithm like logistic regression or decision tree or SVM, and then you need to train that particular model. So that is the model building or model planning process, and the cleaned up data has to be fed into the model. And apart from cleaning, you may also have to, in order to determine what kind of model you will use, you have to perform some exploratory data analysis to understand the relationship between the various variables and see if the data is appropriate and so on, right? So that is the additional preparatory step that needs to be done. So a little bit of details about exploratory data analysis. So what exactly is exploratory data analysis? It's basically to, as the name suggests, you're just exploring. You just receive the data and you're trying to explore and find out what are the data types and what is the data clean in each of the columns. What is the maximum minimum value? So for example, there are out of the box functionality available in tools like R. So if you just ask for a summary of the table, it will tell you for each column, it will give some details as to what is the mean value, what is the maximum value, and so on and so forth. So this exercise or this exploratory analysis is to get an understanding of your data. And then you can take steps to, during this process, you find there are a lot of missing values. You need to take steps to fix those. You will also get an idea about what kind of model to be used and so on and so forth. What are the various techniques used for exploratory data analysis? Typically, these would be visualization techniques, like you use histograms, you can use box plots, you can use scatter plots. So these are very quick ways of identifying the patterns or a few of the trends of the data and so on. And then once your data is ready, you decided on the model, what kind of algorithm you're going to use. If you're trying to do machine learning, you need to pass your 80% the training data, or rather you use that training data to train your model. And the training process itself is iterative. So the training process you may have to perform multiple times. And once the training is done and you feel it is giving good accuracy, then you move on to test. So you take the remaining 20% of the data. Remember, we split the data into training and test. So the test data is now used to check the accuracy or how well our model is performing. And if there are further issues, let's say, and model is still, during testing, if the accuracy is not good, then you may want to retrain your model or use a different model. So this whole thing again can be iterative. But if the test process is passed, or if the model passes the test, then it can go into production and it will be deployed. All right. So what are the various tools that we use for model planning? R is an excellent tool in a lot of ways. Whether you're doing regular statistical analysis or machine learning or any of these activities, R, along with R Studio, provides a very powerful environment to do data analysis, including visualization. It has a very good integrated visualization or plot mechanism, which can be used for doing exploratory data analysis and then later on to do analysis, detailed analysis, and machine learning, and so on and so forth. Then, of course, you can write Python programs. Python offers a rich library for performing data analysis and machine learning and so on. MATLAB is a very popular tool as well, especially during education. So this is a very easy to learn tool. So MATLAB is another tool that can be used. And then last but not least, SAS. SAS is again very powerful. It is a proprietary tool and it has all the components that are required to perform very good statistical analysis or perform data science. So those are the various tools that would be required for or that can be used for model building. And so the next step is model building. So we have done the planning part. We said, okay, what is the algorithm we are going to use? What kind of model we are going to use? Now we need to actually train this model or build the model rather so that it can then be deployed. So what are the various ways or what are the various types of model building activities? So it could be, let's say in this particular example that we have taken, you want to find out the price of 1.35 carat diamond. So this is, let's say, a linear regression problem. You have data for various carats of diamond and you use that information, you pass it through a linear regression model or you create a linear regression model which can then predict your price for 1.35 carat. So this is one example of model building. And then a little bit details of how linear regression works. So linear regression is basically coming up with a relation between an independent variable and a dependent variable. So it is pretty much like coming up with equation of a straight line which is the best fit for the given data. So like for example here, y is equal to mx plus c. So y is the dependent variable and x is the independent variable. We need to determine the values of m and c for our given data. So that is what the training process of this model does. At the end of the training process, you have a certain value of m and c, and that is used for predicting the values of any new data that comes. All right, so the way it works is we use the training and the test data set to train the model and then validate whether the model is working fine or not using test data. And if it is working fine, then it is taken to the next level, which is put in production. If not, the model has to be retrained. If the accuracy is not good enough, then the model is retrained, maybe with more data, or you come up with a newer model or algorithm and then repeat that process. So it is an iterative process. Once the training is completed, training and test, then this model is deployed and we can use this particular model to determine what is the price of 1.35 carat diamond. Remember, that was our problem statement. So now that we have the best fit for this given data, we have the price of 1.35 carat diamond, which is 10,000. So this is one example of how this whole process works. Now, how do we build the model? There are multiple ways. You can use Python, for example, and use libraries like pandas or Numpy to build the model and implement it. This will be available as a separate tutorial, a separate video in this playlist. So stay tuned for that. Moving on, once we have the results, the next step is to communicate these results to the appropriate stakeholders. So which is basically taking this results and preparing like a presentation or a dashboard and communicating these results to the concerned people. So finishing or getting the results of the analysis is not the last step, but you need to, as a data scientist, take these results and present it to the team that has given you this problem in the first place and explain your findings, explain the findings of this exercise and recommend maybe what steps they need to take in order to overcome this problem or solve this problem. So that is the pretty much once that is accepted, and the last step is to operationalize. So if everything is fine, your data scientist presentations are accepted, then they put it into practice and thereby they will be able to improve or solve the problem that they stated in step 1. Okay, so quick summary of the life cycle. You have a concept study, which is basically understanding the problem, asking the right questions, and trying to see if there is enough data to solve this problem. And then even maybe gather the data. Then data preparation, the raw data needs to be manipulated. You need to do data munging so that you have the data in a certain proper format to be used by the model or our analytics system. And then you need to do the model planning, what kind of a model, what algorithm you will use for a given problem, and then the model building. So the exact execution of that model happens in step 4, and you implement and execute that model and put the data through the analysis in this step, and then you get the results. These results are then communicated, packaged and presented and communicated to the stakeholders, and once that is accepted, that is operationalized. So that is the final step. Now, in the end, let's take a quick look at the demand for data scientists. Data science is an area of great demand. The demand for data scientists is currently huge and the supply is very low. So there is a huge gap. So what are some of the industries with high demand for data scientists? I think gaming is definitely one area where it's a industry which is consumer facing industry, and a lot of people play games and growing industry, and it requires a lot of data science. So that is an area where data scientists are in demand. Then we have healthcare. For example, data science is used for diagnosis and several other activities within healthcare, predicting, for example, a disease. So healthcare is definitely finance, definitely banks, insurance companies, all of these, there is a huge demand for data scientists. Marketing is like a horizontal functionality across all industries. There's a demand for data scientists there. Then, of course, in technology areas. So pretty much all of these areas, there is a lot of demand. Globally, there is a huge demand. So this is a very, very critical skill that would be required currently as well as in the future.
So who is a data science engineer? Are you a data science engineer, or are you going to be looking for a different field? What exactly is a data science engineer? Well, a data science engineer is someone who has programming experience in Python and R, expert level knowledge, ability to write proficient codes. And we have Python and R. I'm going to say Python or R. Once you become really proficient at one language, transferring those skills into another one is usually fairly easy. Now, R is a little different because it is an analytics platform. So going from Python to R, if you already know the data analytics in Python, moving to R is pretty easy. Now, R doesn't have all the other code that you can access with Python. There's so many things you can do with Python that are not data analytics. So that's important to keep in mind, that you should probably be pretty well-rounded in Python and really have a solid foundation in R, or have a solid foundation in R and be well-rounded in another programming language where you really get the programming side of it. Strong SQL and big data experience. So you have to have a strong coding skill with hands-on big data experience. And of course, we're showing SQL here, most commonly used, whether you're using a Microsoft SQL server or MySQL server. You can also start thinking Hadoop and Spark in big data access. Hadoop file system is not a huge jump. If you've already learned your SQL and you've already learned your basics in coding, Hadoop sits on top of all that and does a wonderful job creating huge clusters of data. But you really need to know your SQL, because that is so common in most of the large companies now accessing their data. And an ability to visualize models and troubleshoot code of the models. This is a kind of an interesting one because these models can get very complicated, so you got to be able to break them down into something that you can put the pieces together and digest each of the pieces. So being able to visualize these models is very important, and then being able to drill down and troubleshoot the different models or the pieces in those models. You need to be a versatile problem solver, equipped with strong analytical and quantitative skills. A self-starter with a strong sense of personal responsibility and technical orientation. This is an interesting one, because when you talk about data science engineer, it's such a new field that most companies don't have it well defined. They don't know what they're looking for. You might not even know what you're looking for. You might have an idea and you're looking for patterns, but where do those patterns lead you? So you really need that self-starter side to jump in there and figure out where to go and be able to communicate that back to the team. And there we go. We have a strong product intuition, data analysis skills, and business presentation skills. And this is what I was talking about, is you got to bring that back to the team. So if you don't have a strong product intuition, if you don't know what's going on with the company, what they need, and where you're going with your analysis, it's going to be a dead end. And you got to be able to present that to the shareholders, to your coworkers, which leads us to great teammate with excellent interpersonal skills. And this is kind of a strange one because you spend so much time behind your desk, so you have to be able to kind of float between you're studying all the data and being able to explain this to people in simple terms that they can understand. No one wants somebody to come up and say, yeah, the P score and the F score is this, that, and the other thing, and you might have two people in the room understand you. You have to be able to sit down and explain what that means and why. So let's take a look at the data science skill set. When we talk about data science engineer skill set, we're talking about database knowledge, statistics, programming tools, data wrangling, probably the least favorite and most used, machine learning, data visualization, and then to touch on big data. And so we'll start with database knowledge. The most common databases, of course, your SQL, structured query language. Think rows and columns. It's an essential language for extracting a large amount of data from data sets. So knowledge of the SQL is mandatory for data science engineers. And you can see there's tools required. There's the Oracle database. I mentioned MySQL Server, Microsoft SQL Server, Teradata. There are so many different forms of SQL. And it'll just keep coming back and coming back. So if you don't have a solid basic understanding of SQL, go get it. Very important because it will come up. If you don't know it, it's going to bite you. And statistics, of course, that's what this is all about, is figuring out and predicting things. So you need to know your statistics. Statistics is a subset of mathematics that deals with collecting, analyzing, and interpreting data. Therefore, data scientist needs to know statistics. So you need to understand your probabilities and what that means, and what the p-score means, and the f-score, and means, and mode, and median, all that information, standard deviation, all of those you need to be aware of. And then we get into the programming tools, and I mentioned this earlier a little bit, but you need to master any one of these specific programming languages. Programming tools such as R, Python, SAS are essential to perform analytics in data. And again, you can move in there and you can be an expert in just R. You can be an expert in just SAS and a little bit. You can be an expert in Python, because most of these, when we're talking about data science and data wrangling, you really kind of get down to the point where you really need to have a full programming language, at least the basics. And if you're going to be working in data science, Python right now is the main one. But there's also Java, C++. So you need to know a solid language, at least the basics of it, so you can understand how to do basic iterations and things like that. I always find that interesting that my sister, who runs a university data analytics center, that's the first question she asks her candidates who come and work for her is, how do you iterate through data? You'd be amazed at how many people don't understand that very basic concept in programming. So when we look at R is a free software environment for statistical computing and graphs, supports most machine learning algorithms for data analytics like regression, association, clustering, and etc. Python is an open source general purpose programming language, and there's our general purpose I was just talking about you need to know a little bit about. Python libraries like Numpy and SciPy are used in data science. Numpy and SciPy are very central to Python, and I'd throw pandas in there also, that module. Those are very central to working with Python and data analytics. And then SAS. SAS can mine, alter, manage, and retrieve data from a variety of sources. It can perform statistical analysis on the data. So where R is the open source platform, SAS is more like the paid for platform. And so it has some things more automated because people are paying for it, developing it, but it's also, if you really start using it as a company, you're going to have to pay for it, where R is free software. Python's also open source and free to use. So we're going to talk a little bit about data wrangling, and I mentioned earlier that is both the probably people's least favorite aspects of data science, and also probably one of the places you spend the most time. So when we talk about data wrangling, it is the process of transforming raw data into an appropriate format to make it useful for analytics. And it involves cleaning raw data, structuring raw data, and enriching raw data. And this gets interesting because you'll get stuck on something like in Python, you might get stuck on something that is a date time based on an integer 64 Numpy set. You might not know what all those terms mean because you work in R or something like that. But you get the point that it's all one particular format, and then you have to figure out how to switch it so that the computer can see it correctly in whatever format you're using or whatever analytics platform you're using. Knowledge of machine learning techniques such as supervised machine learning, decision trees, linear regression, KNN, etc. is useful for few job roles. So this is kind of interesting because sometimes that's the center of the job role of a data scientist, and sometimes you just have to be able to apply the programming skills to it so you can get the answer and let somebody else fine-tune your machine learning techniques. So it really depends on what it is you're working with. And you can see here we have our nearest neighbor set up where it groups things together that look alike. Linear regression, you're drawing a line through the data, or a curve, so you can predict what the next value is going to be. And then our nice decision tree, which starts splitting things up and says, it's sunny out, yes, let's go swimming. No, it's raining, we're not going to go swimming. Yes, it's sunny out, we might go swim. It's raining, we'll stay indoors, yes. We'll walk the dog, no. So you have a decision tree that helps figure out how you get to the end result. So decision trees can be pretty powerful. And data visualization. Data visualization is the study and creation of visual representation of data. Data visualization uses algorithms, statistical graphs, plots, information, graphics, and other tools to communicate information clearly and effectively. This one you really have to master as a data science. This one you really have to master as a data scientist. And there certainly are so many different tools to use to visualize it. But when you're communicating, a picture is worth 1,000 words. When you can put a picture up and people can look at it and go, oh, I see what's going on, that's worth a lot more than saying, yeah, this is good. People hear that and they just kind of go, okay, it's good, but why? And you might say, okay, these numbers make it look good. No, people want something they can see. And there certainly is, Tableau is probably one of the most popular ones out there. Kalik View, Power BI, Google Data Studio. In Python, there's the PyKit and Seaborn. There's all kinds of different options for visualization. You need to master probably at least one or two of them so you understand how they work and how they're different. And then big data. Big data is a massive amount of data which cannot be stored and processed using traditional methods. Big data has various benefits like access to social data can enable organizations to tune their business strategies. Big data can improve customer experience. And so we're usually, when you say big data, we're almost always talking about Hadoop and Apache Spark. It used to be Hadoop is your file system, so that's how you store all your data going across the nodes, and there certainly are other ways to store it. But when we talk about Hadoop, we're usually talking about at least 10 terabytes of data when you're dealing with a Hadoop file structure. And then you can use Spark, where Hadoop processes on and off the hard drive. So it's continually reading and writing to the hard drive. Spark is running in your RAM. And so when you're doing a very intensive data process, you'll run a Spark setup, which will spread those processes over multiple computers. And of course, now the two combine, and Spark sits on top of Hadoop, and you get your big data. There's also Talent. Tableau has its own server set up. There's Splunk. Cassandra, you'll hear the Cassandra database. Pintaho, I'm not even sure how to pronounce that one. It's not one I've worked with. Certainly there's a lot of options for big data. The two big players are, of course, Hadoop and Spark. And even your SQL servers and MySQL servers will spread across 5 different servers. And you can be talking about big data across 5 servers with those, pulling them into, say, Apache Spark to do your high-end processing. And then there's non-technical skills. Probably the most important one in data science and any of our data analytics is intellectual curiosity. Updating knowledge by reading contents and relevant books on trends in data science. There's so much going on in this field, and it's exploding now that it's hard to keep track of it all. So you really need to have that curiosity in the data science, probably even more so than a lot of other fields. But I would say in just today's world, you need intellectual curiosity because things are changing so rapidly in today's world, the way that's going with our technology. Understanding how the problem solved can impact the business acumen. This is the one where a lot of people kind of skip over. You have to have a little business sense. If you don't know how it's going to impact the business, you're going to be in trouble. Why do they want to even pay you to be there unless they know what's going on and they're getting something in return? So this is your bottom line for your paycheck, is what's going on with the business. How is this going to impact the business? What are you doing for them? And communication skills. Companies look for someone who can clearly and fluently translate technical findings to a non-technical team. And I've talked about this a bunch, and I can't even iterate this enough. If you are struggling with your communication skills, work on building them. They don't have to be, this isn't rocket science where you have to know all these complicated terms. What you need to do is take the complicated terms you know from data science and reduce that down to something that anybody can understand. So when you come up and you have, KNN, no one knows what KNN is, unless they're in data science. Nearest neighbor, looking for things that match together. You got to explain that to people who do not have the technical skill in the data science arena. And a data science engineer needs to work with everyone in the organization, including customers. So it's teamwork, and that's always one that throws people for a loop, but ultimately you are analyzing your customers' information. And so sometimes getting in there and rolling up your sleeves, if let's say you're doing data analysis for a sales team and you're backing a sales team, you might have to get in there and go start making some sales and making some phone calls and see what it's like. What is that team doing when they call 15 people in cold calls? And then they do a follow-up 2 weeks later or 3 weeks later. Which one works better, 2 or 3? Does it work better to call and send a fax, call and send an email? When should you show up in person if it's that kind of business? So working with everybody, including the customer, is very important with the with this kind of setup and non-technical skills for a data scientist. So let's take a look at some of the roles a data science plays in the job market. Let's drill in there just a little bit here. So when you have a data scientist, they're going to perform predictive analysis and identify trend and patterns that can help in better decision making. Companies hiring data scientists include Apple, Adobe, Google, Microsoft. I would say that's even expanding down to smaller companies, where you're talking about only 100 employees or something like that. They're starting to look at data scientists because they need them to come in and be a part of that team. And the role is understanding challenges of a system and offer best solutions. This should always be the goal of a data scientist, is to be looking at the whole system and then trying to find those patterns that are going to best enhance the company or the business or the whatever group. Maybe you're working with the sales team or the marketing team. And you can see languages. Pretty important to have these are a number of different languages, and again, it depends on your own specialty. There's all kinds of different variations, but we have R, SAS, Python, MATLAB, SQL, Hive, Pig, Spark. You should have at least a knowledge of all of these. Maybe a Python programmer never used R, download it and go through the basics so at least you know what's going on in R versus Python. Because R is pretty powerful for doing a very quick display. And then of course there's a lot of things you can do in Python. You have to be able to do queries on database from time to time, create and modify algorithms which can be used to reduce information from large databases. And usually this is one of those things you do at the beginning, you set it up, and then you kind of let it go until it breaks, and then you have to go back and fix it because your query isn't working. That certainly is a very common thing to have happen, especially if you're pulling data off the web and the internet. And then we have some more companies that are hiring data analysis like IBM, DHL, HP. And so we're talking about data analyst. The role is responsible for a variety of tasks such as visualization, optimization, and processing large amount of data. And so when we talk about a data analyst, we're still talking a lot of the same stuff, but you'll see we now thrown in JavaScript and HTML in here, because that's pretty common with a data analyst versus a data scientist. And you can see that SQL is still pretty solid, and also C++ is pretty big. So some companies also use Java, so I'd put Java in the languages also on that for a data analyst. And then you have a data architect, ensuring that data engineers have best tools and systems to work with. And so companies hiring a data architect are like Visa, Logitech, Coca-Cola. They create blueprints for data management with the best security measures. I cannot highlight that a data architect really spends a lot of time with security measures. That's big. How many hacks have we seen in the last year on large companies that have lost data for millions of their customers and how badly that affects them? And we're looking at languages. You see that SQL is pretty solid across all of these. Under a data architect, XML. That's one that a lot of the data science jobs don't really you don't see as much, but you're going to see more XML with a data architect because there's a lot of XML files that have your security measures embedded in them. And of course your Hive, Pig, those are Hadoop systems for doing some basic queries. So instead of doing the high-end queries, you now have these simplified query systems built into Hadoop and Spark. So if you're using big data, you're going to want to know your Spark also. And then we have our data engineer. The data engineer updates the existing systems with better version of the current technologies to improve the efficiency of the databases. Think admin here. A lot of work tracking down what version you're in of the different programs. What version of Python are you using? What version of R are you using? What version of C++? So companies hiring data engineers are like Amazon, Spotify, Facebook. And they develop, construct, test, and maintain architectures such as databases and long-scale processing systems. And here we have our languages, our SQL, R, MATLAB, SAS, SPSS, Python, Java, Ruby, C++, Perl, Hive, Pig. You pretty much as a data engineer at this level, when you're talking about admin and updating all these databases, need to know all the different stuff that's being used in the company. And you're testing out these structures to make sure they work. And so you really are talking admin level kind of setup. So if you like spinning up an admin onto a Google Cloud service or Amazon Cloud service, now you start to get an idea what we're talking about, because then you can test it out up there and then you can bring it back and update it to the company. Statistician creates new methodologies for engineers to apply. And so when we look at this is where we're digging into the math of which models to use, what setup's going to work, what kind of activation do we have on our neural network. These little tweaks are going to make a big difference. And we look for methodologies at a large level. What kind of data are we going to be looking at and how are we going to pull it together? Companies hiring a data engineer, or we're talking about statisticians, we're talking about LinkedIn, PepsiCo, Johnson & Johnson, and of course these companies probably hire a little bit of everything, but they have a lot of statisticians working for them. And so we look at the role, extract and offer valuable reports from the data clusters through statistical theories and data organization. And the languages across the board, we're still seeing SQL, R, MATLAB, SAS, SPSS, Data. That's a new one that we haven't seen in some of the other roles. Python, Perl, an older version. And that shouldn't be a surprise because a lot of these companies probably built a lot of the original packages on Perl. If you go look at Johnson & Johnson. And of course your big data, Hive, Pig, and Spark. And then our database administrator. I mentioned the other one is an admin. They're more an admin level for the software itself. So administrator is another level. Some of the tasks involved are monitoring, operating, and maintaining databases, installation, configuration, defining schemas, training users, etc. And this is interesting, training users, because when you build a database and you define all the different tables that are embedded in that database and how they're all connected, the end user's got to have that information, otherwise you're in trouble. And we have companies hiring data engineers, of course Tableau, Twitter, Reddit. The role ensures that all the databases are available to all relevant users. Again, a little security in there. What role do they have? Who is allowed in and not? And is performing correctly and is being kept safe. And you better be ready to spend some time in security, because again, that's a very big thing nowadays with the number of people who hack into these databases. And the languages are going to be covered. You have your C#, your Java, SQL, Ruby on Rails, XML. Again, there's that XML because a lot of your security is embedded in XML files. Python, all the main players, depending on what the company's using. Data and Analytics Manager. So when you see manager, that means that somebody's going to sit on top and organize the people underneath. So they're going to improve the business process as an intermediary between business and IT. Oh, you better have some really good communication skills for this one. Some of the companies hiring a data engineers are Coursera, Motorola, Slack. And of course, these companies are hiring data scientists in almost all of these fields. So the role oversees the data science operations and assigns the duties to the team according to skills and expertise. So that's a big one. You better be able to communicate what's going on, help your team members come out and be able to communicate with other people. So sometimes your job is just being able to get people to talk to each other. The big thing on that is the whole communication line going from one end to the other. because you can't communicate all the information that everybody's working on. You have to pretty much come in there and help people communicate what there's going on, and also know what they're up to without being micromanagement, because that will crash a company if you micromanage everybody. But if you just let them do whatever they want and they never talk to each other, that will also destroy the company. You got to find that nice middle ground. And you really have to have an overview of everything as a data and analytics manager. One of the things, it's good to have at least one or two solid bases of programming under your belt for a data analytics manager, but you do need to have a very general understanding of all the different tools being used so that you know what's going on with your different team members. Of course, SQL, R, SAS, Java, Python, MATLAB, all of those are big. Business analytics. So this is when you're talking about your BI or your business intelligence and your business analytics. Very important to know this is kind of a subdivision of a lot of the other stuff we've talked about, a lot of the other roles we've looked at. So you possess specialized knowledge of their business domain and apply that knowledge and analysis specifically to the operation of the business. So you might be a specialist in banking. You might be a genetics engineer, so you know about genetics. You might just be general business, helping the marketing. So a lot of companies hiring data engineer are Oracle, Uber, Dell, and the role acts as a link between the data engineers and the management executives. So it's very similar to when we go back up here and we look at data analytics manager. A business analytics is going to also kind of fill that role in between, but they're more specialized in business. And you better know SQL, because when we're talking about business specifically, most of the large companies are storing their data that's up and running right now that people are accessing to purchase something on the Home Depot website or the Uber. They're logging in. You better know your SQL. It's very central to business analytics. So let's go ahead and take a look at the data science engineer salary trends. And you'll see that our source is Glassdoor. That's where we're pulling a lot of our data from. Average base pay is around $117,000 in the U.S., the average salary. And when we look at India, we're talking about $950,000 a year. And those are based on, some of them you need to go ahead and dig deeper to find out what education level versus entry level. But those are a pretty solid base once you're in the industry and once you created your career in there. And we look at the job titles. The most common job title is data scientist. Business Intelligence Manager is the second greatest one. That's kind of good to note. That's why they put that up there as being its own little subcategory of data science manager, as a business intelligence manager, because it's such a high level of jobs. And then we looked at some of the other ones: data architect, business intelligence architect. Again, your BI, your business intelligence, gets its own ranking because it's such a high level, it's a business. People want their businesses to make money, so that's who's hiring. Of course, data engineer, business intelligence developer, business intelligence consultant, business intelligence analyst, business analyst, and data analyst. So you can look at the data analyst as being the general one that doesn't go specific to business. So if you're looking just for your career as far as getting a job, probably should have some kind of business understanding in the background. And again, your companies want to make money, so they're going to hire someone who knows business. If banking business, if you specialize in banking, or retail, if you specialize in retail and marketing. And you can see here on the data science salary trends and the growth in data science job listings. It's continually going up. It's since 2014 to 2012, we've gone from 400 to 600. That's a pretty big increase. So, huge growth in this market. It's one of the biggest growing markets right now for jobs and careers.
Python libraries. Let's bring it together. We have data analytics and we have Python. So when we're talking data analytics, we're talking Python libraries for data analytics. And the big 5 players are Numpy, Pandas, Matplot library, SciPy, which is going to be in the background, so we're not going to talk too much about the scientific formulas in SciPy, and scikit. So Numpy supports n-dimensional arrays, provides numerical computing tools useful for linear algebra and Fourier transform. And you can think of this as just a grid of numbers. And you can even have a grid inside a grid, or data. It's not even numbers, because you can also put words and characters and just about anything into that array. But you can think of a grid, and then you can have a grid inside a grid, and you end up with a nice 3-dimensional array. If you want to talk 3-dimensional array, you can think of images. You have your 3 channels of color, 4 if you have an alpha, and then you have your XY coordinates for the image we're looking at. So you can go X, Y, and then what are the 3 channels to generate that color. And Numpy isn't restricted to 3 dimensions. You could imagine watching a movie. Well, now you have your movie clips, and they each have their X number of frames, and each of those frames have X number of XY coordinates for the pictures in each frame, and then you have your 3 dimensions for the colors. So Numpy is just a great way to work with n-dimensional arrays. Now closely with Numpy is pandas. Useful for handling missing data, perform mathematical operations, provides functions to manipulate data. Pandas is becoming huge because it is basically a data frame. And if you're working with big data and you're working in Spark or any of the other major packages out there, you realize that the data frame is very central to a lot of that. And you can look at it as a Excel spreadsheet. You have your columns, you have your rows or indexes, and you can do all kinds of different manipulations of the data within, including filling in missing data, which is a big thing when you're dealing with large pools or lakes of data where they might be collected differently from different locations. And matplot library. We did kick over the SciPy, which is a lot of mathematical computations, which usually runs in the background of Numpy and Pandas. Although you do use them, they're useful for a lot of other things in there. But the matplot library, that's the final part. That's what you want to show people. And this is your plotting library in Python. Several toolkits extend matplot library functionality. There's like 100 different toolkits to extend matplot library, which range from how to properly display star constellations from astronomy. There's a very specific one built just for that, all the way to some very generic ones. We'll actually add Seaborn in when we do the labs in a minute. Several toolkits extend matplot library functionality, and it creates interactive visualization. So there's all kinds of cool things you can do as far as just displaying graphs, and there's even some that you can create interactive graphs. We won't do the interactive graphs, but you'll see, you'll get a pretty good grasp of some of the different things you can do in matplot library. Let's jump over to the demo, which is my favorite. Roll up our sleeves, get our hands in on what we're doing. Now, there's a lot of options when we're dealing with Python. You can use PyCharm as a really popular one. And you'll see this all over the place. So it's one of the main ones that's out there, and there's a lot of other ones. I used to use NetBeans, which has kind of lost favor. Don't even have it installed on my new computer. But the most popular one right now for data science. Now, PyCharm is really popular for Python general development. For data science, we usually go to Jupyter Notebook or Anaconda. And we're going to jump into Anaconda because that's my favorite one to go to because it has a lot of external tools for us. We're not going to dig into those, but we will pop in there so you can see what it looks like. So with Anaconda, we have our Jupyter Lab, we have our Notebook. These are identical. Jupyter Lab is an upgrade to the Notebooks with multiple tabs. That's all it is. And we'll be using the Notebook. And you can see that PyCharm is so popular with Python that we even have it highlighted here in Anaconda as part of the setup. Jupyter Notebook can also be a standalone. So we're actually going to be running Jupyter Notebook. And then you have your different environments. We're going to be under main Py36. There's a root one. And I usually label it Py36. The reason is currently as of writing this, TensorFlow only works in 3.6 and not in 3.7 or 3.8 for doing neural networks. But you can actually have multiple environments, which is nice. They separate the kernels, so it helps protect your computer when you're doing development. And this is just a great way to do a display or a demo, especially if you're looking for that job. Pull up your laptop, open it up. Or if you're doing a meeting, get it broadcast up to the big screen so that the CEO can see what you're looking at. And when we launch the Notebook, it actually opens up a file browser in whatever web browser you have. This happens to be Chrome. And then you can just go under New. There's a lot of different options depending on what you have installed. Python 3. And this just creates an untitled version of this. And you can see here I'm actually in a Simplilearn folder for other work I've done for Simplilearn. And that's where I save all my stuff and I can browse through other folders, making it real easy to jump from one project to another. And under here, we'll go ahead and change the name of this, and we'll go ahead and rename it Data Analytics. Data Analytics. Just so I can remember what I was doing. Which is probably about 50 of the folders in here, or files in here right now. So let's go ahead and jump in there and take a look at some of these different tools that we were looking at. And as we go through the demo, let's start with the Numpy, the least visually exciting. And I'm going to zoom in here so you can see what we're doing. And the first thing we want to do is import Numpy. And we'll import it as NP. That is the most common Numpy terminology. And let's go ahead and change the view so we also have the line numbers. I don't know why, we probably won't need them, but I like it for easy reference. And then we'll create a one-dimensional array. We'll just call this array1, and it equals np.array, and you put your array information in here. In this case, we'll spell it out. You can actually do like a range and other ways. There's lots of ways to generate these arrays. But we'll just do 1, 2, 3, so 3 integers. And if we print our array1, we can go ahead and run this. And you can see right here it prints 1, 2, 3. You can see why this is a really nice interface to show other people what you're doing with the Jupyter Notebook. So this is the basic. We've created an array. This is a one-dimensional array, and then the array is 1, 2, 3. One of the nice things about the Jupyter Notebook is whatever ran in this first setup is still running. It's still in the kernel. So it still has the Numpy imported as NP, and it still has our variable ARR1 for array1 equal to NP array of 1, 2, 3. So when we go to the next cell, we can check the type of the array. We're just going to print. We say, hey, what is this setup in here? And we want type, and then we want what is the type of array1. And let's go ahead and run that. And it says class Numpy ND array. So it's its own class. That's all we're doing is checking to see what that class is. And if you're going to look at the array class, probably the biggest thing you do, I don't know how many times I find myself doing this because I forget what I'm working on, and I forget I'm working with a 3-dimensional or 4-dimensional array. And I have to reformat somehow so it works with whatever other things I have. And so we do the array shape. The array shape is just 3 because it has 3 members and it's a one-dimensional array. That's all that is. And with the Numpy array, we can easily access, stick with the print statement. If you actually put a variable in Jupyter Notebook and it's the last one in the cell, it will be the same as a print statement. So if I do this, where array1 of 2, it's the same as doing print array of 2. Those are identical statements in our Jupyter Notebook. We'll go and stick with the print on this one. And it's 3. So there's our print space 2, and we have 0, 1, 2, 2 equals 3. We can easily change that. So we have array 1 of place 2 equals 5. And then if we print our array 1, you can see right down here when it comes out, it's 1, 2, and 5. And there I left the print statement off because it's the last variable in the list. It'll always print the variable if you just put it in like that. That's a Jupyter Notebook thing. Don't do that in PyCharm. I've forgotten before doing a demo. And we talked about multiple dimensions, so we'll do an array, 2-dimensional array. And this is again a Numpy array. And in the Numpy array, we need our first dimension. We'll do 1, 2, 3, and our second dimension 3, 4, 5. And you can see right here that when we hit the, we'll do this. We'll just do array 2. And we can run that, and there's our array 2, 1, 2, 3, 3, 4, 5. We can also do array 2 of 1. And then we can do, let's do 0. Doesn't really matter which one. Actually, let's do 2. There we go. And if I run this, it'll print out 5. Because here we are. This is 0. 0, 1, 2, 3 is on our 0 row. 3, 4, 5 is on our 1 row. I always start with 0. And then the 2, 0, 1, 2 goes to the 5. And then maybe we forgot what we were working with. So we'll go do array2.shape. And if we do array2 of shape, we'll go and run that. We'll see we have 2 rows, and each row has 3 elements. 2-dimensional array, 2, 3. If you looked up here when we did it before, it just had 3 comma nothing. When you have a single entity, it always saves it as a tuple with a blank space. But you can see right here we have 2 comma 3. And if you remember from up here, we just did this array 2 of, let's go, what is it, 1 comma 2. We run that, we get the 5. You can also count backwards. This is kind of fun. And you'll see I just kind of switched something on you because you can also do 1 comma 2 to get to the same spot. Now 2 is the last one, 0, 1, 2. It's the last one in there. We can count backwards and do -1. And if we run this, we get the same answer. Whether we count it as, let's go back up here, whether we count this as 0, 1, 2, or we count backwards as -1, -2, -3. And you can see that if I change this -1 to a -2 and run that, I get 4, which is going backwards, -1, -2. So there's a lot of different ways to reference what we're working on inside the Numpy array. It's really a cool tool. It's got a lot of things you can do with it. And we talked about the fact that it can also hold things that are not values, and we'll call this array ask for strings equals np.array. Put our setup in there, our brackets, and let's go China, India, USA, Mexico. It doesn't matter, we can make whatever we want on here. And if we print that out, we run this, you can see that we get our Numpy array, China, India, USA, Mexico. It even gives us our D type of a U6. And a lot of times when you're messing with data, we'll call this array R for range, just to kind of keep it uniform. np.arange. So this is a command inside Numpy to create a range of numbers. And if you're testing data, maybe you want, maybe you have equal time increments that are spaced a certain point apart. But in this case, we're just going to do integers. And we're going to do a setup from 0, 20, skipping every other one. And we'll print it out and see what that looks like. And you can see here we have 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. Like you expected, it skips every one. And just a quick note, there's no 20 on here. Why? Well, this starts at 0 and counts up to 20. So if you're used to another language where it explicitly says less than or less than equal to 20, like for x equals 0, x plus plus, x is less than 20. That's what this is. It just assumes x is less than 20 on here. And if we want to create a very uniform set, 0, 2, 4, 6, what happens if I want to create numbers from 0 to 10, but I need 20 increments in there? We can do that with line space. So we can create an R, we'll call this L, equals, I don't think we'll actually use any of this again, so I don't know why I'm creating unique identifiers for it. But we'll do NP, lin space, and we're going to do 0 to 10, or 0 to 9. Remember, it goes up to 10. And then we want to, let's say we have 20 different increments in there. So we're creating we have a data set, and we know it's over a certain time period, and we need to divide that time period by 20. And it happens to just have 10 pieces in it. And here we go. You can see right here, we have 20, or it has 20 pieces in it, but it's over 10 years. And we got to divide it in the middle. And you can see it goes 0.52. Remember, yeah, there's our 10 on the end, so it goes up to 10. And then we can also do random. There's np.random. If you're doing neural networks, usually you start it by seeding it with random numbers. And we'll just do np.random, and we'll just call this array. We'll stop giving it unique numbers. We'll print that one out and run it. And you can see we have random numbers. They are 0 to 1. So you'll see that all these numbers are under 1. And you can easily alter that by multiplying them out or something like that if you want to do like 0 to 100. You can also round them up if it's integer 0 to 100. There's all kinds of things you can do, but it generates a random float between 0 and 1. And you have a couple options. You could reshape that. or you can just generate them in whatever shape you want. And so we can see here, we did 3 and 4, and so you can see 3 rows by 4 variables. Same thing as doing a reshape of 12 variables to 3 and 4. And if you're going to do that, you might need an empty data set. I have had this come up many times where I need to start off with 0, and I don't know, because I'm going to be adding stuff in there, or it might be 0 and 1, where 1 is, if you're removing the background of an image, you might want the background is 0, and then you figure out where the image is, and you set all those boxes to 1, and you create a mask. So creating masks over images is really big, and doing that with a Numpy array of 0. And we can also give it a space. And we'll just do this all in one shot this time. And we'll do the same thing like we did before, zeros. And in this case, we'll do 2, 3. And so when we run this, forgot the asterisks around it. I knew I was forgetting something. There we go. So when we run this, you can see here we have our 10 zeros in a row, and maybe this is a mask for an image, and so it has 2 rows of 3 digits in it. So it's a very small image, little tiny pixel. And maybe you're looking to do something the opposite way. Instead of creating a mask of zeros and filling in with ones, maybe you want to create a mask of ones and fill them in with zeros. And we'll just do, just like we did before, we'll do 3, 4. And when we run this, you'll see it's all ones. And we could even do this even, we'll do it this way. Let's do 10 by 10 icon, and then you have your 3 colors. And you can, so it creates quite a large array there for doing pictures and stuff like that when you add that 3rd dimension in. If we take that off, it's a little bit easier to see. We'll do 10 again. And you can easily see how we have 10 rows of 10 ones. And you can also do something like create an array. And we'll do 0, 1, 2. And then in this array, we actually we'll print it right out. We want a repeat. And so you can actually do a repeat of the array, and maybe you need this array, let's repeat it 3 times. So there's our repeat of an array, repeat 3 times. And if we run this, you'll see we have 0, 0, 0, 1, 1, 1, 2, 2, 2. And whenever I think of a repeat, I don't really think of repeating being the first digit 3 times, the second digit. I really always think of it as 0, 1, 2, 0, 1, 2, 0, 1, 2. It catches me every time. But the actual code for that one is going to be tile. And again, if we do arrange 3 and we run this, you can see how you can generate 0, 1, 2, 0, 1, 2, 0, 1, 2. And if you're dealing with an identity matrix, we can do that also if you're big on doing your matrices. And we'll just identity. I guess we'll go ahead and spell it out today. Matrix. And the command we're looking for is EYE. And we'll do 3. And then we'll just go ahead and print this out. There we go. There's our identity matrix. And it comes out by a 3 by 3 array, because there's our matrix. And then it puts the ones down the middle and for doing your different matrix math. And we can manipulate that a little bit too. We talk about matrices. We might not want ones across the middle, in which case we now have the diagonal. So we can do an np.diagonal. And we do a diagonal. Let's put in the diagonal 1, 2, 3, 4, 5. And when we run this, again, this generates a value. And by just putting that value in, there's the same as putting print around it, or putting array equals and then print array. And you can see it generates a diagonal 1, 2, 3, 4, 5, and there's your beginning of your matrix array for working with matrices. And we can actually go in reverse. Let's create an array equals, remember our random.random, and we'll do a 5 by 5 array. Oops, there we go. 5 by 5. And just so you can see what that looks like. Helps if I don't mistype the numbers, which in this case I just need to take out the brackets. And there you go. You have your 5 by 5 array set up in there. And we can now, because we're working with matrices, we might want to do this in reverse and extract the diagonals, which would be the 0.79, the 0.678, and so on. And we simply type in np.diagonal, and we put our array in there. And this will, of course, print it out because it returns it as a variable. And you can see here, here's our diagonal going across from our matrix. And we did talk about shape earlier. If you remember, you can do print the shape out. You can also do the dimensions. So in dimensions, very similar to shape, it comes out and just has 2 dimensions. We can also look at the size. So if we do size on here, we can run that. And you can see it has a size of 25, 2 dimensions, and of course 5 by 5. And that was from the shape from earlier that we looked at. There's our 5 by 5 shape. And if you remember earlier we did random, well, you can also do random. I talked a little bit about manipulating 0 to 1 and how you can get different answers. You can also do straight for the integer part, and we'll do minus 10 to 10, 4. And so we're going to generate random integers between minus 10 to 10. We're going to generate 4 of those. And so when we run that, we have 7, minus 3, minus 6, minus 3. They're all between minus 10 and 10, and there's 4 of them. And now we jump into some of the functionality of arrays, which is really great, because this is where they come in. Here's your array, and you can add 10 to it. And if I run this, there it takes my original array from up here with the integers and adds 10 to all of those values. So now we have, oh, this is the decimal, that's right. This is a random decimal I had stored in an array. But this takes the random numbers I had from 0 to 1 and adds 10 to them. And we can just as easily do minus 10. We could even do times 2. And we could do divide by 2. And it'll take that random number we generated and cut it in half. So now all these numbers are under 0.5. Another way you can change the numbers to what you need on there. And as you dig deeper into Numpy, we can also do exponential. So as an exponential function, which should generate some interesting numbers off of the random. So we're taking them to the power, I don't even remember what the original numbers in the array were, because we did the random numbers up there. Here's our original numbers, and if you build an exponential on there, this is where you get e to the x on this. And just like you can do e to the x, you can also do the log. So if you're doing logarithmic functions that reinforce learning, you might be doing some kind of log setup on there, and you can see the logarithmic of these different array numbers. And if you're working with log base 2, you can just change it in there, np log 2. You have to look it up, because this is not log 1, 2, 3, 4, 5. It is log and log 2. So just a quick note, that's not a variable going in. That is an actual command. There's a number of them in there, and you'll have to go look and see what the documentation is. But you can also do log 10. So here's log value 10. Some other really cool functions you can do with this is your sine. So we can take a sine value of all of our different values in there. And if you have sine, you of course have cosine. We can run that. So here's the cosine of those. And if you're doing activations in your Numpy array and you're doing a tangent activation, there's your tangent for that. And the tangent activation is actually from neural networks. That's one of the ways you can activate it, because it forms a nice curve between from whether you're generating 1 to -1 with some discrepancy in the middle. Just jumping a little bit in there into neural networks. And then we get into, let me just put the array back out there so that we can see it while we're doing this. as we're getting into this, you can also sum the values. So we have np sum, and you can do a summation of all the values in this array. And you'll see that if you added all these together, they'd equal 12.519, so on. I don't know what the whole setup is in there. But you can see right here the summation of this. One of the things you can also do is by axes. So we could do axes equals 0. And if we run the summation of the axes equals 0, and you can think of that in Numpy as the rows. So that would be, or you can think of that in Numpy as being the columns. We're summing these columns going across. And you can also change this to 1, and now we're summing the rows. And so that is the summation of this row, and so forth going down. And maybe you don't need to know the summation. Maybe what you're looking for is the minimum. So here's our minimal. You're looking for, and this comes up a lot because you have like your errors. We want to find the minimal error inside of this array. And just like the other one, we can do axes equals 0. And you can see here 0.0645 is the smallest number in this first column is 0.0645 and so on. And if you have a minimum, well, you might also want to know the max. Maybe we're looking for the maximum profit. And here we go. You can see maximum 0.79 is the maximum on this first column. And just like we did before, you can change this to a 1 on axes. You can take the axes out of here and just find the max value for the whole array. And the max value in here was 0.8344, so on and so on. And since we're talking data analytics, we want to go ahead and look at the mean. Pretty much the same as the average. This is the mean across the whole thing. And just like we did before, we could also do axes equals 0. And then you'll see this is the mean of this axis and so on. And we have mean. We might want to know the median. And there's our median, our most common numbers. If we have median, we might want to know the standard deviation. Or if we have the average, a lot of times you do the means and the standard deviation. We can run that, and there's our standard deviations along the axes. We can also do it across the whole array. If we're going to do standard deviations, there's also variance, which is your VAR. And there's our variance across the different levels. And so if we looked at that, we looked at variance, we looked at standard deviation, the median, and the means. There's more, but those are the most common ones used with data analytics. And then going through your data and figuring out what you're going to present to the shareholders. And some other things we can do is we can actually take slices. You'll hear that terminology. And a slice might be, like we have a 5 by 5 array, but maybe we don't want the whole array. Maybe we want from 1 on, we don't want the 0 in there. So we got up to 4. And maybe on the second part, we just want 2 to row 3. And so this notation right here says 1 to the end. And if we run this, you can see how that generates a single row to the end, and then row 2 and 3. Now remember, it doesn't include 3. That's why we only get the 1 column. So if you wanted 2 and 3, you would need to go ahead and go 2 to 4. So it goes up to 4. We could also do this in reverse. Just like we learned earlier, we can go -1. Whoops. And when we go to -1, it's the same thing because we have 0, 1, 2, 3, 4. This is the same thing as 2 to 4. It goes 2 to the last one. Also very common with arrays is you're going to want to sort them. So we still have our array up here that we randomly generated. And we might want to sort it. And we'll go and throw an axis back in there. Axis equals 1. If we run this, you can see from the axes that it sorts it, the 0.2 being the lowest value to the highest value by the row. We can also change this, of course, to axis 0. If you're sorting it by columns, so maybe your values are based on columns. And then, of course, you can do the whole array, and we can sort that. Don't usually do that, but I guess sometimes that might come up. And so you can see right here we have a nice sorted array. Something else, let's just go ahead and reprint our array so we can look at it again. Starting to get too many boxes up there. Something else you can do with an array is we can take and transpose it. This comes up more than you would think. When you transpose it, you'll see that the rows in the column are transposed. So where 0.79, 0.57, 0.064 is the column, now we've switched it and we have 0.79, 0.42 as the index. You can see this really more dramatic if we take a slice, and we'll just do a slice of the first couple, and then we'll just do all the other, the full rows, and if we run this, you can see how it comes up a little bit different. And we'll just do the same slice up here so you can see how those two look next to each other. There we go, there's our slice, run. And so you can see the slice comes up and it has 1, 2, 3, 4, 5 columns. Now we have 1, 2, 3, 4, 5 rows and 3 columns versus 3 rows. And the original version, when they first started putting this together, was a function. So the original version was transpose, and this still works. You can still see it generates the same value as just a capital T. So many times we flip this data because we'll have an XY value or we'll have an image or something like that, and it's being read one way into the next process, and the next one needs it the opposite. So this actually happens a lot. You need to know how to transpose the data really quick. And we can go ahead, let's just take, here's our transpose. We'll just stick with the transpose on here. And instead of doing it this way, we might need to do something called flattening. Why would you flatten your data? If this is an array going into a neural network, you might want to send it in as one set of values instead of 2 rows. And you can see here is all the values as a single array. It just flattens it down into one array. So we covered our scientific means, transpose, median, some different variations on here. Some of the other things we want to do is what happens if we want to append to our array. So let's create a new array. I'm getting tired of looking at the same set of random numbers we generated earlier. So we'll go ahead and create a new array here, something a little simpler so it's easier to see what we're doing. And 4, 5, 6, 7, 8. That's good enough. We'll just do 4, 5, 6, 7, 8. And if we print this array, there it is, 4, 5, 6, 7, 8. And we might want to append something to the array. So we have our array, we need to extend it. You got to be very careful about appending things to your array, and there's a number of reasons for that. One is runtime. Because of the way the Numpy array is set up, a lot of times you build your data and then push it into the Numpy array instead of continually adding on to the array. And then it also it automatically generates a copy for protecting your data. So there's a lot of reasons to be careful about appending this way. But you can certainly do it. And we can just take our array, we're going to create a new array, array 1. And if we print array 1 and we append 8 to it, you'll see 4, 5, 6, 7, and then there's our 8 appended on to the end. And if you want to append something to an array, you'd probably also want to, whoops, array 1. Let's try that again. There we go. Now we have the 8 appended onto the end. So you can see 4, 5, 6, 7, 8, and then we appended another 8 on there. And if you're going to append something, you might want to go ahead and insert. Instead of appending, it might be you need to keep a certain order. And we can do the same thing. We can do our array, and we're going to append or insert at the beginning. And let's go ahead and insert 1, 2, 3. 1, 2, 3. And we go ahead and print our array 2, and we run it, and you can see 1, 2, 3 is inserted at the beginning. Insert's a lot more powerful in that you can put it anywhere in the array. We can move it to the 1 spot, and there we go, 1, 2, 3. We can do a -1 just for fun, and you'll see it comes up 1, 2, 3, and we're counting backwards by 1. I imagine you can do a -0 and run this, and it turns out that -0 puts it back at the beginning because that's how it registers as 0, just takes a minus sign off. And just like we add numbers on, we might want to delete numbers. And so let's do an np.delete. Well, let's keep it a little bit, make it a little easy here to watch. We'll go ahead and create an array 3, and we'll do np delete. We were just working with array 2, and what we want to do is delete 0 space. So if you look at this, here's our array 2. Array 2 starts with 1, and when we delete the space on here and print that out, we deleted the 1 right out of there. And we can also do something like this, where we can do it as a slice, and we can do, let's do 1, 3. And if we run 1, 3, you'll see we've deleted the 1 space and the 3 space out, which deleted our 2 and 4. Now, keep in mind, when you're messing with adding lines and deleting lines, you have to be really careful, because there's a time element involved as far as where the data is coming from, and it's really easy to delete the wrong data and corrupt what you're working on, or to insert stuff where you don't want it. So there's always a warning when we talk about manipulating Numpy arrays. And just like anything else we're doing, we'll create an array C, which equals, we'll just do our Numpy array that we just created, our Numpy array 3, and we can do copy. So you can make a copy of it. Maybe you want to protect your original data, or maybe you're making a mask, and so you copy the array, and then the new array make all these alterations and change it from values to 0 to 1 to mask over the first one. And of course, if we do array C, since it equals a copy of array 3, it's the same thing, 1, 3, 5, 6, 7, 8. And now we're getting into combine and split arrays. I end up doing a lot of this, and I don't know how many times I end up fiddling with this and having a mess. So, but you do it a lot. You know, you combine your arrays, you split them. You might need one set of data for one thing, another set of data for the other. So let's go ahead and create 2 arrays, array 1, array 2. And I want you to note, and the terminology we're going to look for is concatenate. And what that means is we're going to take, we'll call this array cat. I like array cat. There we go. Our array cat, our concatenated array, we're taking array 1 and 2, and it's very important to really pay attention to your axes and your counts. I can't merge 2 arrays that have, like, if their axes are messed up and I'm merging on axis 0, it's going to give me an error and I'll have to reshape them. So you got to make sure that whatever you're concatenating together works. And what that means, as you can see here, we have 1, 2, 3, 4, 1, 2, 3, 4, and then 5, 6, 7, 8, 5, 6, 7, 8 along the 0 axis. These each are 4 values. So it's a 2 by 4 value. And if we go ahead and switch this to 1, you can see how that flips it a little bit. So now we have 1, 2, 3, 4, 5, 6, 7, 8. It's interesting that we chose that one. If I did something like this, where this is now, there we go, and we concatenate it, run this, and it gives me an answer okay, because I have 2 by 2, and I'm using axis 1. But if I switch this to axis 0, where now it's got 3 and 5, it gives me an error. So you got to be really careful on that to make sure that your whatever axes you are putting together, that they match. So like I said, this one, oops, axis 1. Axis 1 has 2 entities, and since we're going on axis 1, or by row, you can see that it lets it merge it right onto the end there. And you could imagine this, if this was a XY plot of value, or the X value going in and the predicted Y value coming out, and then you have another prediction and you want to combine them, this works really easy for that. And we'll go back, and let's just put this back to where we had it. Oops, I forgot how many changes I made. There we go. We'll just put it, whoops, I messed up in my concatenation order here. There we go. Okay, so you can see that we went through the different concatenation. Axes is really important when you're doing your concatenation values on here. And we'll switch this back to 1 just because I like the looks of that better. There we go. 2 rows. Now, there are other commands in here. So we can do cat v equals npv vstack. This is nothing more than your concatenation, but instead we don't have to put the axes in there because V stands for vertical. And so if we print out cat V and we run this, you can see we get the 1, 2, 3, 4, 1, 2, 3, 4, and that would be the same as making this axis 0 for vertical stack. And if you're going to have a vertical stack, you can also have an H stack. So if we change this from V stack to, oops, here we go, H stack, and we'll just change this from cat to cat, and I run this, it's the same as doing axis 0. The process is identical in the background. This is like a legacy setup, your V stack and your H stack. Most people just use concatenate and then put the axes in there because it's much has a lot more clarity and is more commonly used nowadays. The last section in Numpy we're going to cover is kind of data exploration, and that'll make a little bit more sense in just a moment. Sometimes they call them set operations. But let's say we have an array, 1, 2, 3, 4, 5, 6, 3, whatever it is. You can see we generate a nice little array here. And what I want to go ahead and do is find the unique values in that array. So maybe I'm generating what they call a one-hot encoder. And so these values then all become, I need to know how long my bit array is going to be. So each word, each word is represented by a number, and then I want to know just how many of those words are in there. If we're doing word count, very popular thing to do. And you can see here when we do unique, we have 1, 2, 3, 4, 5, 6. Those are our unique values. Some of the things we can do with the unique values is we can also, instead of doing just unique, we can do uniques, our unique values, and counts of each unique value. And this is very similar to what we just did up here, where we're doing NP unique, but we're going to add a little bit more into there. And it's just part of the arguments in this. And we want to do return counts equals true. So instead of just returning the unique values, we want to know how many of those unique values are in each one. And we'll go ahead and print our uniques and print our counts. When we run that, you can see here we have our unique value 1, 2, 3, 4, 5, 6, just like we had before. And then there's two of the first of 2 1s, 2 2s, 2 3s, 2 4s, 1 5, 2 6s, and so on. And you can go through and actually look at that if you want to count them. But a quick way to find out your distribution of different values. So you might want to know how often the word the is used versus the word and, if each word is represented as a unique number. And along the set variables, we might want to know, let me just put a note up here. We're going to start looking at intersection, and we might want to also know differentiation, and neither. So when we're, neighbor, neither. So when we're looking at now is we want to know, hey, where do these two arrays intersect? And we have 1, 2, 3, 4, 5, 3, 4, 5, 6, 7. We might want to know what is common between the two arrays. And so when we do that, we have NP intersect, and it's a 1D array, one-dimensional array. And then we need to go ahead and put array 1, array 2. And if we run this, we can see they intersect at 3, 4, 5. That's what they have common. And because we're going to go ahead and go through these and look at a couple different options, let's change this from intersect 1D. And we'll do the same thing. We'll go ahead and print this. So we might want to know the intersection where they have commonalities. Another unique word is union of 1D. So instead of intersect, we want to know all the values that are in both of them. So here's our union of 1D. When we run that, you can see we have 1, 2, 3, 4, 5, 6, 7. So that's all the different values in there. And one of the last words, we have 2 more to go, is we want to know what the set difference is. And so that's where you'll see that. If you remember set, we talked about that being what they call these things. So the set difference of a 1D array, when we run that, you can see that 1 is only in one array and 2 is only in one array. And if we want to know what's in array 1 but not in array 2, we might want to know what is in array 1 but not 2 and what's in 2 but not 1. And this would be the set XOR 1D on here. So we have the 4 different options here where we can do an intersection. What do they both have in common? We can do a union. What are all the unique values in both arrays? We can see the difference, what's in array 1 but not array 2, so set diff 1D. And then set XOR, what is not in 1 but is in 2, and what is not in 2 but in 1. So we dug a lot in Numpy because we were talking, there's a lot of different little mathematical things going on in Numpy. A lot of this can also be done in pandas, although usually the heavy lifting is left for Numpy because that's what it's designed for. Let's go ahead and open up another Python 3 setup in here. And so we want to explore what happens when you want to display this. This is where it starts getting, in my opinion, a little fun because you're actually playing with it and you have something to show people. And we'll go ahead and rename this. We're going to call this pandas and pyplot. So pandas pyplot, just so I can remember for next time. And we want to go ahead and import the necessary libraries. We're going to import pandas as PD. Now remember, this is a data frame, so we're talking rows and columns, and you'll see how pandas work so nicely when you're actually showing data to people. And then we're going to have Numpy in the background. Numpy works with pandas, so a lot of times you just import them by default. Seaborn sits on top of the matplot library. So sometimes we use the Seaborn because it kind of extends. It's one of the 100 packages that extends the matplot library. Probably the most common used because it has a lot of built-in functionality. Almost by default, I usually just put Seaborn in there in case I need it. And of course we have matplot library as pyplot, as PLT. And note we have as PD, as NP, as SNS, as PLT. Those are pretty standard. So when you're doing your imports, I would probably keep those just so other people can read your code and it makes sense to them. That's pretty much a standard nowadays. And then we have the strange line here. It says ampersand matplot library inline. That is for Jupyter Notebook only. So if you're running this in a different package, it'll have a pop-up when it goes to display the matplot library. You can, with the most current version of Jupyter, usually leave that out and it will still display it right on the page as we go. And we'll see what that looks like. And then we're going to go ahead and just do the Seaborn, the sns.set, and we're going to set the color codes equals true. Let them just keep the default ones so we don't have to think about it too much. And we of course have to run this. The reason we run this is because these values are all set. If we don't run this and I access one of these afterward, it'll crash. The cool thing about Jupyter Notebooks is if you forgot to import one of these, you forgot to install it, because you do have to install this under your Anaconda setup or whatever setup you're in, you can flip over to Anaconda and run your install for these. And then just come back and run it. You don't have to close anything out. And we'll go ahead and paste this one in here real quick where we have car equals pd.read_CSV. And then we have the actual path. This path, of course, will vary depending on what you are working with. So it's wherever you save the file at. And you can see here I have like my OneDrive documents, Simplilearn, Python, data analytics, using Python, / car CSV. It's quite a long file. When we open that up, what we get is we get a CSV file, and we have the make, the model, the year, the engine, fuel type, engine horsepower, cylinders, and so on. And this is just a comma separated file. So each row is like a row of data. Think of it as a spreadsheet. And then each one is a column of data on here. And as you can see right here, it has the make, model. So it has columns for a header on here. Now, your Pandas just does an excellent job of automatically pulling a lot of this in. So when you start seeing the Pandas on here, you realize that you are already like halfway done with getting your data in. I just love Pandas for that reason. Numpy also has it. You can load a CSV directly into Numpy, but we're working with pandas, and this is where it really gets cool, is I can come down here and I can print, you remember our print statement, we can actually get rid of it, and we're just going to do car head because it's going to print that out. The head is going to print the top values of that data file we just ran in. And so you can see right here, it does a nice printout. It's all nice and in line because we're in Jupyter Notebook. I can scroll back and forth and look at the different data. And just like we expected, we have our column, and it brought the header right in. One thing to note is the index. It automatically created an index 0, 1, 2, 3, 4, and so on. And we're just looking at the head. So we got 0, 1, 2, 3, 4. You can change this. You might want to just look at the top two. We can run that. There's our top two BMWs. Another thing we can do is instead of head, we can do tail. And look at the last three values that are in that data file. And you can see right here, it numbered them all the way up to 11,913. Oh my goodness, they put a lot of data in this file. I didn't even look to see how big the file was. So you can really easily get through and view the different data in here. When you're talking about big data, you almost never just print out car. In fact, let's see what happens when we do. If we run this and we just run the car, it's huge. In fact, it's so big that the pandas automatically truncates it and just does head plus tail, so you can see the two. So we really don't want to look at the whole thing. We'll go ahead and go back to, let's stick with the head, displaying our data. There we go. So there's the head of our data. It gives us a quick look to see what's actually in there. I can zoom out if we want so you can actually get a better view. Although we'll keep it zoomed in so you can see the code I'm working on. And then from the data standpoint, we of course want to look at data types. What's going on with our data? What does it look like? Now this, you show when you're talking to your shareholders, they like to see these nice, easy to read charts. They look like a spreadsheet. So it's a nice way of displaying pieces of the chart. When we talk about the data types, now we're getting into the data science side of it. What are we working with? Well, we have make model, we have an integer 64 for the year. Engine fuel type is an object. If we go up here, you can see that most of them are it's a set manual, rear wheel drive. So they might be very limited number of types in there. And so forth. And it's either going to be a float 64, an integer, or an object is the way it's going to read it on here. And the next thing you're going to know is like your columns. And since it loaded the columns automatically, we have here the make, the model, the year, the engine, the size, all the way up to the MSRP. And just out of something you'll see come up a lot is whenever you're in pandas and you type in .values, it converts it from a pandas list to a Numpy array. And that's true of any of these. So then you end up in a Numpy array. So you'll see a little switch in there in the way that the data is actually stored. And that's true of any of these. In this case, we want car.columns. You have a total list of your car columns. And like any good data scientist, we want to start looking at analytical summary of the data set. What's going on with our data? So we can start trying to piecemeal it together. So we can do car, describe, and then what we'll do include equals all. So a nice panda command is to describe your data. If you're working with R, this should start looking familiar. And we come down here and you can see count. There's the make, the model, the year, how many of each one, how many unique values of each one, the top value of each one, what's most common, the frequency, the mean. Clearly on some of these it's an object, so it really can't tell you what the average is. It'd just be the top one's the average, I guess. The year, what's the average year on there? All this stuff comes down here. Your standard deviation, your minimum value, your maximum value, what's in the lower quarter, 50% mark, where's that line at, and what's in the upper 75%, the top 25% going into the max. Now, this next part is just cool. This is what we always wanted computers to be back like in the 90s instead of 5,000 lines of code to do this. Maybe not 5,000. All right, I built my own plot library back in 95, and the amount of code for doing a simple plot was, I don't know, probably about 100 lines of code. This is being done in one line of code. We have our car, which is our pandas. We generated that. It's our data frame. And we have .hist for histogram. That is the power of Seaborn. Now, it's still going to generate a Numpy graph, but Seaborn sits on top, and then we can do the figure size. This is just so it fits nicely on the paper on here. And we do something simple like this, and you can see here where it comes up, and it does say matplot library and does subplots and everything. But we're looking at a histogram of all the different pieces in our database. And we have our engine cylinders. That's always a good one because you can see like they have some that they had a null on there, so they came out as 0. Maybe one of them had a 2-cylinder engine way back when. 4 is a common, 6 a little less common, and then you see the 8-cylinder, 12-cylinder engines. Boy, that's got to be a speedster or something. But you can see right here, it just breaks it down. So now you have how many cars with how many, whatever it is, cylinders, horsepower, and so on. And it does a nice job displaying it. You can see if you're working with your, you're going into your demo, it's really nice just to be able to type that in and boom, there it is. It can see it all the way across. And we might want to zero in and use like a box plot. And this time we'll go ahead and call the Seaborn, SNS, box plot. And we're going to go ahead and do vehicle size versus engine horsepower XY plot. And the data comes from the car. So if we run this, we end up with a nice box plot. You see our mid-size, compact, and large. You can see the variation. There's our outlier showing up there on the compact. That must be a high-end sports car. Large car might have a couple engines, and again we have all these outliers and then your deviation on them. Very powerful and quick way to zero in on one small piece of data and display it for people who need to have it reduced to something they can see and look at and understand. And that's our Seaborn box plot, or sns.boxplot. And then if we're going to back out and we want a quick look at what they call pair plotting, we can run that, and you can see with the Seaborn it just does all the work for you. It takes it just a moment for it to pull the data in and compile it. And once it does, it creates a nice grid. And this grid, if you look at this one space here, which is, you might not be able to see the small number, it says engine horsepower. This is engine horsepower to the year it was built, and it's just flipped. So everything to the right of the middle diagonal is just the rotation of what's on the left. And as you expect, the engine horsepower gets bigger and bigger and bigger as time goes on. So the year it was built, the further up in the year, the more likely you are to have a heavy horsepower engine. And you can quickly look at trends with our pair plot coming up. And look how fast that was. It took it a moment to process. But right away I get a nice view of all these different information which I can look at visually and kind of see how things group and look. Now, if I was doing a meeting, I probably wouldn't show all the data. One of the things I've learned over the years is people, myself included, love to show all our work. You know, we were taught in school, show all your work, prove what you know. The CEO doesn't want to see a huge grid of graphs, I guarantee it. So what we want to do is we want to go ahead and drop the stuff that might not be interested in. And I'm not really a car person. Our guy in the back is, obviously. So you have your engine fuel type. We're going to drop that. We're going to drop market category, vehicle style, popularity, number of doors, vehicle size. And we have the axes in here. If you remember from Numpy, we have to include that axes to make it clear what we're working on. That's also true with pandas. And then we'll look at just what it looks like from the head. And you can see that we dropped out those categories, and now we have the make, model, year, and so forth. And we took out the engine fuel type, market category, etc. And this should look familiar to you now. When you start working with pandas, I just love pandas for this reason. Look how easy it is. It just displays it as a nice spreadsheet for you. You can just look at it and view it very easily. It's also the same kind of view you're going to get if you're working in Spark or PySpark, which is Python for Spark across big data. This is the kind of thing that they come up with, and this is why pandas is so powerful. And we may look at this and decide we don't like these columns. And so you can go in here and we can actually rename the columns. Simple command, car equals car, rename. Columns equals engine horsepower equals horsepower. This is just your standard Python dictionary. So it just maps them out. And instead of having like the lengthy, here we had engine horsepower, we just want horsepower. We don't need to know it's the engine horsepower. Engine cylinders, we don't need to know that it's for the engine, because there's only one thing we're describing if we're talking about cars, and that's cylinders. And we'll go ahead and just run this. And again, here's our car head, and you can see how that changed. We have model year and horsepower versus model year, engine horsepower, engine cylinders, and just cylinders. Again, we want to keep reducing this so it's more and more readable. The more readable you get it, the better. And of course, we can also adjust the size a little bit so that when it prints out, instead of splitting it on 2 lines, we get like a single line. We can do that also. That's just your control mouse up or plus sign you use in Chrome. That's a Chrome command. And if you remember from Numpy, we had shape. Well, pandas works the same way. We can look at the shape of the data. So we now have 11,914 rows and 10 columns. So you see some similarities because pandas is built on Numpy. And questions that come up just like you did in Numpy, we might want to know duplicate rows. And so we can do car. And look at this switch here. We're doing a selection. This is a pandas selection with the brackets. But we want to select it based on car.duplicated. So how many duplicates on there? So it's starting to look a little bit different as far as how we access some of the data on here. This can be a logical statement. And we get the number of duplicate rows. We have 989 rows by 10 columns again. And this is one of those troubleshooting things that we end up doing a lot, more than we really feel like we should. We might go ahead and do like a car count just to see how many rows we're dealing with. And then right after that, we might want to go ahead and say, hey, let's drop duplicates. So remember we did all the duplicates on there. So car equals car dot drop duplicates. And then we can print the head again. We'll just do car head here. And you can see the data on there looks the same as before. And just note that we did car equals car dot duplicates. There are commands in here where you can do, where it changes the actual value. And it works on some of them and not on others depending on what you're doing. But by default, it always returns a copy. So when we do this, we're reassigning it to car. And you can see it's the same header, but we want to go ahead and do count and see how the count changes. Let's go ahead and run this. And you can see here, instead of 11,914, we have 10,925. So we've removed about 100 cars that were duplicated, just slightly under 100 there. And then as we're prepping our data, we might want to know car is null. So it's going to count the values of null, and then we want to sum that up. And when we do that, we do the car is null function dot sum. We end up with HP, the horsepower is 69 have null values, and 30 have cylinders have null values. Now, if you don't put the sum at the end, it's just going to return a mask with the true false of is it null or is it not, by 0 and 1. So you're summing up the ones underneath each column. And this, of course, then you have to decide what you're going to do with the null values. There's a lot of different options. It might be that you need to put in the average or means. Maybe you want to put in the median value. There's a lot of different ways to fill it. Usually when you first start out with the data, a lot of them you just drop your null values. And you can see here car.drop NA, which is equal to all. And then we're going to go ahead and count it. And you can see that we've dropped almost another 100 values. So from 10,925 to 10,827, maybe 75 or so values. So we cleaned this is really a big part of cleaning data. You need to know how to get rid of your null values, or at least count them and what to do with them. And of course, if we go back to counting our null values, we should now have null values. There we go. And you'll see there's 0 null values. I don't know how many times I've been running a model that doesn't take null values and it crashes, and I just sit there and look at it trying to get, why did that crash? It should have worked. It's because I forgot to remove the null values. So we've been jumping around a lot. We're going to go back to finding outliers. And let's go ahead and bring that back into our Seaborn. And if you remember, we did a box plot earlier. This time we're going to do a box plot just on the price. And you can see here our price value, and we have the deviation with the 2 thinner bars on each side of the main value. And then as we get up here, we have all these outliers. In fact, we have one way out here that's probably a really expensive high-end car is what we're looking at. If you were doing fraud analysis, you would be jumping on all over these outliers. Why are these deviation from the standard? What are these people doing? Again, this is probably, like I said, a really high-end expensive car out here. That's what we're looking at. And we can also look at the box plot for the horsepower. And we'll put that in down here and run that. And you can see again, here's our horsepower, and it just jumps, and there's these really odd, huge muscle cars out here that are outliers. And we're going to jump into making this a little bit more, as you start displaying your data or your information to your shareholders. We're going to look at plotting a histogram for the number of cars per brand. And the first thing we want to go ahead and do is we have with our car, go back over here, here we go. We have our make value counts, largest plot, and we want to do a kind equals bar, figure size 10.5. And right off the bat, we jump up here and we see Chevrolet. It's going against, what was it? It's figuration, the value counts, and we want the largest value. So here's our value counts and compared to what the different cars are. Chevrolet puts out a lot of different kinds of cars. I didn't realize that they made that many cars or different types. And then for readability, let's go ahead and add a title, number of cars by make, number of cars, and make. If you had looked at this the first time, you would have been like, well, what the heck am I looking at? Well, we're looking at the number of cars by make. And then you can see here, now we're talking about the type of cars and the different ones are put out. Lotus, I guess, only had a few different kinds of cars over there. Very high-end cars. And then as doing data analytics and as a data scientist, one of the things I am most interested in is the relationship between the variables. So this is always a place to start. We want to know what's going on with our variables and how they connect with each other. So the first thing we're going to do is we're going to go ahead and set a figure size because we want to make sure it fits our graph. We'll just go ahead and set this one plot figure set to figure size 2010. If you never use the matplot library, which is sitting behind Seaborn, whatever is in the PLT, this is what's loaded. It's like a canvas you're painting on. So the second you load that PyPlot as PLT, anything you do to that is affecting everything on it. And then we want to go ahead, since we're using Seaborn, we'll go ahead and create a variable C for relationships or correspondence, and car.corr. That's a correlation in Seaborn on top of pandas. Again, one line and you get the whole correlation on there. And because we're working with Seaborn, let's put it into a nice heat map. If you're not familiar with heat maps, that means we're just using color as part of our setup. So we have a nice visual. And we can see here that the Seaborn connected to the pandas prints out a nice chart. We'll talk a little bit about the color here in a second. It prints out a nice chart. This is a chart I look at. As a data scientist, these are the numbers I want to look at. And we'll just highlight one of them. Here's cylinders versus horsepower. The closer to 1, the higher the correlation. So 0.788. Pretty high correlation between the number of cylinders and how heavy the horsepower is. I'm betting if you looked at the year versus horsepower, we can just look at that one. Here's year and horsepower. 0.314, not as so much, but if you combine them, you don't actually add them. But if you combine them, you'll start to see an increase in horsepower per year and cylinders. You could probably get a correlation there. And just like 0.78 is a positive correlation, you might notice if we look at cylinders, or let's look at horsepower and mileage. So if we go here to horsepower to mileage, you get a nice negative. We'll do cylinders, that's a bigger number. With cylinders to the miles per gallon, it's a minus 0.6. So it's a negative correlation. The closer to -1, the more the negative correlation is. And then the chart you would actually show people is a nice heat map. This is all our colors, and it's just those numbers put into a heat map. The darker the color, the higher the correlation. You can see straight down the middle, obviously the year correlates directly with the year, horsepower with horsepower, and so on. That's why it's a 1. The closer to the 1, the higher the correlation between the two pieces of data. Now, this is a good introduction. Pandas goes way beyond this. Most of the functionality in Numpy, since Pandas sits on it, is also in Pandas, and then it even has additional features in it. And we use Seaborn pretty extensively sitting on top over our pie plot. So keep in mind that our pie plot has a ton of other features in it that we didn't even touch on in here. We couldn't, even if you had a sole course in it, there's just so many things hidden in there depending on what your domain you're working on. But you can see here, here's our Seaborn and here's our matplot library. That's all our graphics that we did. And then the Seaborn works really nicely with the pandas. We really like that.
Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle, a good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of X, the squared value of Y, and X times Y. And then it takes all of X and adds them up, all of Y adds them up, all of X squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to X times Y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from is called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, X and Y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic. Multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that, and we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import Numpy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The Numpy, which stands for NumPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :-1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it, since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one-hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the third row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. And let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn model selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there.
And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines. And then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do xtrain and ytrain because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the xTest. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have yPredict equals regressor.predict xTest going in, and this gives us yPredict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. We're looking at the error. So, in the R2 score, we take our y-test versus our y-predict. Y-test is the actual values we're testing. That was the one that was given to us so we know are true. The y-predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score.
And if our squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
Alright, what is logistic regression? Logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis. X is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation. Remember, this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1. And let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now, let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them. So that can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the height. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you're trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not. Yes, no, right? So there is nothing in between. And what is the employee's rating? Okay. And ratings can be continuous. That is not an issue. But the output is discrete in this case. Whether employee got promotion, yes, no. Okay. So if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right, because it looks like there will be a lot of errors. Thus, root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix. the heat map and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. All right, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting, right? So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there's a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and 1 has been predicted as number 8, and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's the gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, all right, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like Numpy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay. And based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of the entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right? This is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this. In this case, the data is not large, but by and large, the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose, we use the fit method. There is a method called fit, which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method and we pass this particular image, and we see that the shape is, or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, The diagonals again are all the values are here, most of the values, so which means reasonably, this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0, actual value is of course 0. Then this is the image of 9, so this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
Need for confusion matrices. Classification models have multiple output categories. Most error measures will tell us the total error in our model, but we cannot use it to find out individual instances of errors in our models. So you have your input coming in, you have your classifier, it measures the error and it says, oh, 53 of these are correct. But we don't know which 53% are correct. Is it 53% correct on guessing on the spam? Is it 23% guessing on spam and 27% guessing on what's not spam? This is where the confusion matrix comes in. So during the classification, we also have to overcome the limitations of accuracy. Accuracy can be misleading for classification problems. If there is a significant class imbalance, a model might predict the majority class for all cases and have a high accuracy score. And so you can see here we have our email coming in and there's 2 spams. The classifier comes in and goes, hey, it only catches one of those spams and it misclassifies one that's not spam. So our model predicted 8 out of 10 instances and will have an accuracy of 80%. But is it classifying correctly? A confusion matrix represents a table layout of the different outcomes of prediction and results of a classification problem and helps visualize its outcomes. And so you see here we have our simple chart, predicted and actual. The confusion matrix helps us identify the correct predictions of a model for different individual classes, as well as the errors. So you'll see here that the values predicted by our classifier are along the rows. This is what we're going to guess it is, or our model is guessing what this is based on its training. So we've already trained the model to guess whether it's spam or not spam or whatever it is you're working on. And then the actual values of our data set are along the columns. So this is the actual value that's supposed to be. People who can speak English will be classified as positives. So, because they have remember 0 or 1. Do you speak English? Yes, no. And you could extend this that they might have, do you speak French? Do you speak whatever languages? And so you might have a whole lot of classifiers that you would look at each one of these. People who cannot speak English will be classified as negatives. So there'll be a 0. So, 0 ones. The number of times our actual positive values are equal to predicted positive values gives us true positive, TP. The number of times our actual negative values are equal to predictive negative values gives us true negative, TN. The number of times our model wrongly predicts negative values as positives gives us a false positive, FP. And you'll see when you're working with these a lot, memorizing that it's false positive, you can easily figure out what that is, and pretty soon you're just looking at the FP or the TP, depending on what you're working on. And the number of times our model wrongly predicts positive values as negatives gives us a false negative, FP. Now, I'm going to do a quick step out here. Let's say you're working in the medical and we're talking about cancer. Do you really want a bunch of false negatives? You want 0 under false negative. So when we look at this confusion matrix, if you have 5% false positives and 5% false negatives, it'd be much better to even have 20% false positives because they go in and test it, and 0 false negatives. The same might be true if you're working on, say, a car driving. Is this a safe place for the car to go? Well, you really don't want any false positives. Yes, this is safe right over the cliff. So again, when you're working on the project or whatever it is you're working on, this chart suddenly has huge value. We were talking about spam email. How many important emails, say from your banking overdraft charge coming in, that you want to be a true false negative? You don't want it to go in the spam folder. Likewise, you want to get as much of the spam out of there, but you don't want to miss anything really important. Confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics: accuracy, precision, recall, and F1 score. The F1 score is the one I usually hear the most, and accuracy is usually what you put on your chart when you're sending in front of the shareholders. How accurate is it? People understand accuracy. F1 score is a little bit more on the math side, and so you got to be a little careful when you're quoting F1 scores in the when you're sitting there with all the shareholders, because a lot of them will just glaze over. So confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics. Accuracy. The accuracy is used to find the portion of the correctly classified values. It tells us how often our classifier is right. It is the sum of all true values divided by the total values. And this makes sense. Again, it's one of those things. I don't want to, it depends on what you're looking for. Are you looking for not to miss any spam mails? Are you looking to drive down the road and not run anybody over? Precision is used to calculate the model's ability to classify positive values correctly. It answers the question, when the model predicts a positive value, how often is it right? It is the true positive divided by the total number of predicted positive values. Again, this one depends on what project you're working on, whether this is what you're going to be focusing on. So recall, it is used to calculate the model's ability to predict positive values. How often does the model actually predict the correct positive values? It is the true positives divided by the total number of actual positive values. And then your F1 score. It is the harmonic mean of recall and precision. It is useful when you need to take both precision and recall into account. Consider the following 2 confusion matrices, derived from 2 different classifiers. To figure out which one performs better, we can find the confusion matrix for both of them. And you can see we're back to, does it classify whether they can speak English or are non-speaker? They don't know the English language. And so we put these 2 confusion matrices out here. We can go ahead and do the math behind that. We can look up the accuracy. That's a TPN plus TN over the TF plus TN plus FP plus FN. And so we get an accuracy of 0.8125. And we have a precision. If you do the precision, which is your TP, truth positive, over TP plus FP, we get 0.891. And if we do the recall, we'll end up with the 0.825. That's your TP over TP plus FN. And then, of course, your F1 score, which is 2 times precision times recall over precision plus recall. And we get the 0.857. And if we do that with another model, let's say we had 2 different models and we're trying to see which one we want to use for whatever reason, we might go ahead and compute the same things. We have our accuracy, our precision, and our recall, and our F1 score. And as we're looking at this, we might look at the accuracy, because that's really what we're interested in, is how many people are we able to classify as being able to speak English. I really don't want to know I really don't want to know if they're non-speakers. I'd rather miss 10 people speaking English instead of 15. And so you can see from these charts, we'd probably go with the first model because it does a better job guessing who speaks English and has a higher accuracy, because in this case, that is what we're looking for. So with that, we'll go ahead and pull up a demo so you can see what this looks like in the Python setup and in the actual coding. For this, we'll go into Anaconda Navigator. If you're not familiar with Anaconda, it's a really good tool to use as far as doing display and demos. And for quick development. As a data scientist, I just love the package. Now, if you're going to do something heavier lifting, there's some limitations with Anaconda and with the setup. But in general, you can do just about anything in here with your Python. And for this, we'll go with Jupyter Notebook. Jupyter Lab is the same as Jupyter Notebook. You'll see they now have integration with PyCharm if you work in PyCharm. Certainly there's a lot of other integrations that Anaconda has. And we've opened up my Simplilearn files I work on and create a new file called Confusion Matrix Demo. And the first thing we want to note is the data we're working with. Here I've opened it up in a WordPad or Notepad or whatever. You can see it's got a row of headers, comma separated, and then all the data going down below. And then I save this in the same file so I don't have to remember what path I'm working on. Of course, if you have your data separated and you're working with a lot of data, you probably want to put it into a different folder or file depending on what you're doing. And the first thing we want to do is go ahead and import our tools. We're going to use the pandas. That's our data frame. If you haven't had a chance to work with the data frame, please review Pandas data frame and go into Simplilearn. You can pull up the Pandas data frame tutorial on there. And then we're going to use the scikit framework, which is all denoted as sklearn. And I can just pull this in. You can see here's the scikit-learn.org with the stable version that you can import into your Python. And from here, we're going to use the train test split. For splitting our data, we're going to do some pre-processing. We're going to use the logistic regression model. That's our actual machine learning model we're using. And then what this particular setup is about is we're going to do the accuracy score, the confusion matrix, and the classifier report. So let me go ahead and run that and bring all that information in. And just like we opened the file, we need to go ahead and load our data in here. So we're going to go ahead and do our pandas read CSV. And then just because we're in Jupyter Notebook, we can just put data to read the data in here. A lot of times we'll actually, let me just do this. I prefer to do just the head of the data, or the top part. And you can see we have age, sex, I'm not sure what CP stands for, test BPS, cholesterol. So a lot of different measurements. If you were in this domain, you'd want to know what all these different measurements mean. I don't want to focus on that too much because when we're talking about data science, a lot of times you have no idea what the data means. If you've ever looked up the breast cancer measurement, it's just a bunch of measurements and numbers. Unless you're a doctor, you're going to have no idea what those measurements mean. But if it's your specialty in your domain, you better know them. So we're going to go ahead and create Y, and we're going to set it equal to the target. So here's our target value here. And it's either 1 or 0. So we have a classifier. If you're dealing with 1, 0, true, false, what do you have? You have a classifier. And then our X is going to be everything except for the target. So we're going to go ahead and drop the target. Axes equals 1. Remember, that's columns versus the index or rows. Axes equals 0 would give you an error, but you would drop like row 2. And then we'll go ahead and just print that out so you can see what we're looking at. And here we have Y data, X data. And you can see from the X data we have the X head. And we can go ahead and just do print the Y head data and run that. So this is all loading the data that we've done so far. If there's a confusion in there, go back and rewind the tape and review it. And then we need to go ahead and split our data into our X train, X test, Y train, Y test. And then keep in mind, you always want to split the data before we do the scalar. And the reason is that you want the scalar on the training data to be set on the training data or fit to it, but not on the test data. Think of this as being out in the field. It could actually alter your results. So it's always important to make sure whatever you do to the training data or whatever fit you're doing is always done on the training, not on the test. And then we want to go ahead and scale the data. Now, we are working with linear regression model. And I'll mention this here in a minute when we get to the actual model. So sometimes you don't need to scale it when you're working with linear regression models. It's not going to change your result as much as, say, a neural network where it has a huge impact. But we're going to go ahead and take, here's our X train, X test, Y train, Y test. We create our scalar. We go ahead and scale. The scale is going to fit the X train. And then we're going to go ahead and take our X train and transform it. And then we also need to take our X test and transform it based on the scale on here, so that our X is now between that nice -1 to 1. And so this is all our pre-data setup. And hopefully all of that looks fairly familiar to you if you've done a number of our other classes and you're up to the setup on here. And then what we want to go ahead and do is create our model. And we're going to use a logistic regression model. And from the logistic regression model, we're going to go ahead and fit our X train and Y train. And then we'll run our predicted value on here. And so let's go ahead and run that. And so now we actually have like our X test and our prediction. So if you remember from our matrix, we're looking for the actual versus the prediction and how those compare. And if I take us back up here, you're going to notice that we imported the accuracy score, the confusion matrix, and the classification report. And there's, of course, our logistic regression, the model we're using for this. And I did mention I was going to talk a little bit about scalar and the regression model. The scalar, on a lot of your regression models, your basic math standard regression models, and I'd have to look it up for the logistic regression model. When you're using a standard regression model, you don't need to scale the data. It's already just built in by the way the model works, in most cases. But if you're in a neural network and there's a lot of other different setups, then you really want to take this and fit that on there. And so we can go in and do the accuracy. And this is, if you remember correctly, we were looking at the accuracy with the English speaking. So this is saying our accuracy as to whether this person is, I believe this is the heart data set. It's going to be accurate about 85% of the time as far as whether it's going to predict the person's going to have a heart condition, or the 1 as it comes up with the 0, 1 on there. Which would mean at this point that you have an 85% being correct on telling someone they're extremely high risk for a heart attack kind of thing. And so we want to go ahead and create our confusion matrix. And let me just do that. Of course, the software does everything for us. So we'll go ahead and run this. And you can see right here, here's our 25 prediction, correct predictions right here. And if you remember from our slide, I'll just bring this over so it's a nice visual. We have our true positive, false positive. So we had 25 which were true, that it said, hey, this person's going to be high risk at heart. And we had 4 that were still high risk that it said were false. So out of these 25 people, or out of these 29 people, and that makes sense because you have 0.85, out of 29 people, it was correct on 25 of them. And so here's our accuracy score. We were just looking at that. Our accuracy is your true positive and your true negative over all of them. So how true is it? And there was our accuracy coming up here, 0.85. And then we have our nice matrix generated from that. And you can see right here is a similar matrix we had going for from the slide. And this should start asking questions at this point. So if you're in a board meeting or you're working with this, you really want to start looking at this data here and saying, well, is this good enough? Is this number of people, and hopefully you'd have a much larger data set, is my confusion matrix showing for the true positive and false positive, is that acceptable for what we're doing? And of course, if you're going to put together whatever data you're putting out, you might want to separate the true negative, false positive, false negative, true positive. And you can simply do that by doing the confusion matrix. And then, of course, the ravel part lets you set that up. So you can just split that right up into a nice tuple. And the final thing we want to show you here in the coding on this part is the confusion matrix metrics. And so we can come in here and just use the matrix equals classification report, the y-test and the predict. And then we're going to take that classification report and go ahead and print that out. And you can see here it does a nice job giving you your accuracy, your micro average, your weighted average, you have your precision, your recall, your F1 score, and your support all in one window, so you can start looking at this data and saying, oh, okay, our precision's at 0.83, 0.87 for getting a positive, and 0.83 for the negative side for a 0. And we start talking about whether this is a valid information or not to use. And when we're looking at a heart attack prediction, we're only looking at one aspect. What's the chances of this person having a heart attack or not? You might have something where we went back to the languages. Maybe you also want to know whether they speak English or Hindi or French. And you can see right here that we can now take our confusion matrix and just expand it as big as we need to, depending on how many different classifiers we're working on.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree, important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or our calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. I have to make a couple changes as we go through this first part of the import. The first thing we bring in is Numpy as NP. That's very standard when we're dealing with mathematics, especially with very complicated machine learning tools. You almost always see the Numpy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and this is very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as a opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the Open Office Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or Open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in x equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database, so it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, I always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves is 5. So it's going to have at least 5 leaves at the end. So it'll have at least 3 splits, or have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created, and then you'll see .predict, and that's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on, and then we put in our y predict en, that's the answers we got, and we're just going to multiply that by 100 because this is just going to give us an answer as a decimal, and we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. How does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by a diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code, and you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there, and let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have Numpy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames, is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the 3 that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into 2 different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. Remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into 2 different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create 2 variables. We're going to create 2 new data frames. One's called train, one's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, We're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines, and that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans, and let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the DF columns, and we know the first four of them, 0, 1, 2, 3, that'd be the first four, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first four. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What is factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. CLF dot fit. So we're fitting, we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the Y. So the Y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this like just like when we were up here and I typed in Y and it printed out Y instead of print Y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see injobs equals 2. You can see the random state equals 0. Those are the two that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only, I think, 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have, like, we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal length, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually do, let's do the first 25 just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have setosa where they meet, you have versicolor where they meet, and you have virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says virginica, but it was supposed to be versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we read it on test features. But, we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. So in this example, last week my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you can figure out that it was a strawberry. So let's take this model a step further, and let's, why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know our strawberries, and they're already labeled as such. We already have a bunch of apples, we know our apples, and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of 2 categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the 2 groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where we have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have 2 groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in 2 lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the two classes. Here you can see there's a clear split between the two different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the two. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have 2 sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a 2-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a 2-dimensional output. As you can see in this picture here, the 1D when transferred to a 2-dimensional makes it very easy to draw a line between the 2 data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a 2-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the 2 classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a 3-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These 3 advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work. It's especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout, and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here in the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice collection of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. And let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are Numpy as NP and matplotlibary.pyplot as PLT. Now these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the Numpy array. And I'll talk about that in a minute so you can understand why we want to use a Numpy array versus the standard Python array. And normally it's pretty standard setup to use NP for Numpy. The matplot library is how we're going to view our data. So this has, you do need the NP for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals SVM.SVC kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane. plane, so we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y, and that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created two blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our two sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from Numpy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a Numpy array. It turns out that our makeblobs returns a Numpy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma, 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot and the second one is the Y plot. So the first one is on the bottom 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dots, so we can see them instead of real tiny dots. And then CMAP equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using two colors, 0, 1, and that's why we get the nice blue and the two different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process one line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it. And you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here. And I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show was down here and then removed right there on line 5. I'll go ahead and just delete that out of there because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines because we did that before. And let's take a look at the AX equals plt.gca. Now right now, we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is very standard used variable when you talk about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a Numpy command. So we're back to our numbers Python. Let's go through what these Numpy commands mean with the line space and the mesh grid. We've taken xx, small s xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together, so it forms a nice grid. So if we were going to do this, say, between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with Numpy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally we get down to the Numpy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created, and we've already trained. And we have a dot decision function, and we're going to put the XY in there. So here we have all this data. We're going to put that XY in there, that data, and we're going to reshape it. And you'll see that we have the XX.shape in here. This literally takes the XX, resets it up connected to the Y, and the Z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the Z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it, and we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data, and we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash line and the dash line on that grid. And you can see here, when we do the CLF.support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our 2 support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the 2 different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the 2 groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future. And you can see how easy they are to set up and look at in depth.
So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data, which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with K-means clustering, we will have here, that means K is equal to 2, and we will have 2 clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in K-means clustering is the allocation of 2 centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means K is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, So that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of these new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add BC to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is the top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique, whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop, so let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares, and the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS, because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated, like so. You see this? So this point earlier was closer to C2 because C2 was here, but after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned a value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do, we have to calculate the actual centroids for each of these groups, which is like the mean position, which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to Ck, and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. x1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing. And that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to Ck. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from C3 and so on up to CK, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups, because we wanted to create k clusters, right? So we have k groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position, which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python Notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python Notebook. So in this block, we are basically importing all the required libraries like Numpy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, if we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like matplotlib and numpy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually, also we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and it will create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0. Cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k-means. When we call predict, that is what it does. And we can take a quick look at these y underscore k-means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering. And there is a function or a library calculates for a given two pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid. And then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare. And if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this, And so this is how the original, the pixel distribution is. These are two plots. One is red against green and another is red against blue. And this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now, what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are this is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger. So we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors, and this is basically how it would look, 16 million colors. And now we can create the clusters out of this, the 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors, and then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering. And we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering. And we use some sample data using blob to just execute the k-means clustering.
Dimensionality reduction. Dimensionality reduction refers to the technique that reduces the number of input variables in a data set. And so you can see on the table on the right shows the orders made at an automobile parts retailer. The retailer sells different automobile parts from different companies. And you can see we have company BPAX, Isomax, and they have the item, the tire, the axle, an order ID, a price number, and a quantity. In order to predict the future sales, we find out that using correlation analysis that we just need 3 attributes. Therefore, we have reduced the number of attributes from 5 to 3. And clearly we don't really care about the part number. I don't think the part number would have an effect on how many tires are bought. And even the store, who's buying them, probably does not have an effect on that. In this case, that's what they've actually done, is remove those. And we just have the item, the tire, the price, and the quantity. One of the things you should be taking away from this is, in the scheme of things, we are in the descriptive phase. We're describing the data, and we're pre-processing the data. What can we do to clean it up? Why dimensionality reduction? Well, number one, less dimensions for a given data set means less computation or training time. That can be really important if you're trying a number of different models and you're rerunning them over and over again. And even if you have 7 gigabytes of data, that can start taking days to go through all those different models. So this is huge. This is probably the hugest part as far as reducing our data set. Redundancy is removed after removing similar entries from the data set. Again, pre-processing, some of our models, like a neural network, if you put in 2 of the same data, it might give them a higher weight than they would if it was just one. So we want to get rid of that redundancy. It also increases the processing time if you have multiple data coming in. Space required to store the data is reduced. So if we're committing this into a big data pool, we might not send the company that bought it. Why would we want to store 2 whole extra columns when we add it into that pool of data? Makes the data easy for plotting in 2D and 3D plots. This is my favorite part. Very important. You're in your shareholder meeting. You want to be able to give them a really good, clear, and simplified version. You want to reduce it down to something people can take in. It helps to find out the most significant features and skip the rest, which also comes in post-scribing. Leads to better human interpretation. That kind of goes with number 4, where it makes data easy for plotting. You have a better interpretation when we're looking at it. Principal component analysis. So what is it? Principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. So we take some very complex data set with lots of variables, we run it through the PCA, we reduce the variables. We end up with a reduced variable setup. This is very confusing to look at because if you look at the end result, we have the different colors all lined up. So what we're going to take a look at is, let's say we have a picture here. Let's say you are asked to take a picture of some toddlers and you are deciding which angle would be the best to take the picture from. So if we come up here, we look at this, we say, okay, this is one angle. We get the back of a lot of heads, not many faces. So we'll do it from here. We might get the one person up front smiling. A lot of the people in the class are missing, so we have a huge amount off to the right of blank space. Maybe from up here, again, we have the back of someone's head. And it turns out that the best angle to click the picture from might be this bottom left angle. You look at it and you say, hey, that makes sense. It's a good configuration of all the people in the picture. Now, when we're talking about data, it's not, you really can't do it by what you think is going to be the best. We need to have some kind of mathematical formula so it's consistent and so it makes sense in the back end. One of the projects I worked on many years ago has something similar to the iris. And if you've ever done the iris data set, it's probably one of the most common ones out there where they have the flower and they're measuring the stamen in the petals, and they have width and they have length of the petal. Instead of putting through the width and the length of the petal, we could just as easily do the width to length ratio. We can divide the width by the length and you get a single number where you had 2. That's the kind of idea that's going on into this, in pre-processing and looking at what we can do to bring the data down. The very simplified example on my iris petal example. When we look at the similarity in PCA, we find the best picture or projection of the data points. And so when we look down at from one angle, we've drawn a line down there, we can see these data points based on, in this case, just 2 variables. Now keep in mind, we're usually talking about 36, 40 variables. Almost all of your business models usually have about 26 to 27 different variables they're looking at. Same thing with like a bank loan model. We're talking 26 to 36 different variables they're looking at that are going in. So what we want to do is we want to find the best view. In this case, we're just looking at the XY. We look down at it, and we have our second idea, PC2. And again, we're looking at the XY, this time from a different direction. Here, for our ease, we can consider that we get 2 principal components, namely PC1 and PC2. Comparing both the principal components, we find the data points are sufficiently spaced in PC1. So if you look at what we got here, we have PC1. You can see along the line how the data points are spaced versus the spacing in PC2. And that's what they're coming up with. What is going to give us the best look for these data points when we combine them? And we're looking at them from just a single angle. Whereas in PC2, they are less spaced, which makes the observation and further calculations much more difficult. Therefore, we accept the PC1 and not the PC2 as the data points are more spaced. Now, obviously, the back-end calculations are a little bit more complicated when we get into the math of how they decide what is more valuable. This gives you an idea, though, that when we're talking about this, we're talking about the perspective, which would help in understanding how PCA analysis works. What we want to go ahead and do is dive into the important terminologies under PCA. And important terminologies are views, the perspective through which data points are observed. And so you'll hear that if someone's talking about a PCA presentation and they're not taking the time to reduce it to something that the average person, shareholders, can understand, you might hear them refer to it as the different views. What view are we taking? Dimension, number of columns in a data set are called the dimensions of that data set. And we talked about, you'll hear features, dimensions. Now I was talking about features. There's usually, when you're running a business, you're talking 25, 26, 27 different features minimal. And then you have the principal component, new variables that are constructed as linear combinations or mixtures of the initial variables. Principal component is very important. It's a combination. If you remember my flower example, it would be the width over the length of the petal as opposed to putting both width and length in. You just put in the ratio instead, which is a single number versus 2 separate numbers. Projections. The perpendicular distance between the principal component and the data points. And that goes to that line we had earlier. It's that right angle line of where how all those points fall onto the line. Important properties. Important properties. Number of principal components is always less than or equal to the number of attributes. That just makes common sense. You're not going to do 10 principal properties with only 3 features. You're trying to reduce them, so it's just kind of goofy, but it is important to remember that. People will throw weird code out there and just randomly do stuff instead of really thinking it through. Principal components are orthogonal. And this is what we're talking about, that right angle from the line. When we do PC1, we're looking at how those points fall on to that line. Same thing with PC2. And we want to make sure that PC1 does not equal PC2. We don't want to have the same 2 principal points when we do 2 points. The priority of principal components decreases as their numbers increase. This is important to understand. If you're going to create one principal component, everything is summarized into that one component. As we go to 2 components, the priority, how much it holds value decreases as we go down. So if you have 5 different points, each one of those points is going to have less value than just the one point, which has everything summarized in it. How PCA works. I said there was more in the back end when we talk about the math. This is what we're talking about, is how does it actually work? So now we have understanding that you're looking at a perspective. Now we want to see how that math side works. PCA performs the following operations in order to evaluate the principal components for a given data set. First, we start with the standardization. Then we have a covariance matrix computation. And we use that to generate our igene vectors and igene values, which is the feature vector. And if you remember, the igene vector is like a translation if we're moving the data from x equals 1 to x equals 2 or whatever, altering it. And the igene value is the final value that we generate. When we talk about standardization, the main aim of this step is to standardize the range of the attributes so that each one of them lie within similar boundaries. This process involves removal of the mean from the variable values and scaling the data with respect to the standard deviation. And you can see here we have z equals the variable values minus the mean over the standard deviation. The covariance matrix computation. Covariance matrix is used to express the correlation between any 2 or more attributes in multi-dimensional data set. The covariance matrix has the entries as the variance and the covariance of the attribute values. The variance is denoted by var and the covariance is denoted by cov. On the right, we can see the covariance matrix for 2 attributes and their values. When we do a hands-on look at the code, we'll do a display of this so you can see what we're talking about and what that looks like. For now, you can just notice that this is a matrix that we're generating with the variance and then the covariance of x to y. On the right side, we can see the covariance table for more than 2 attributes in a multi-dimensional data set. And this is what I was talking about. We usually are looking at not just 1 feature or 2 features. We're usually looking at 25, 30 features going on. And so if we do a setup like this, we should see all those different features as the different variables. Covariance matrix tells us how the 2 or more variables are related. Positive covariance indicate that the value of one variable is directly proportional to the other variable. Negative covariance indicate that the value of one variable is inversely proportional to the other variable. That is always important to note whenever we're doing any of these matrices, that we're going to be looking at that positive and negative, whether it's inverted or not. And then we have the igene values and the igene vectors. Igene values and igene vectors are the mathematical value that are extracted from the covariance table. They are responsible for the generation of a new set of variables from the old set of variables, which further lead to the construction of the principal components. Igene vectors do not change directions after linear transformation. Igene values are the scalars or the magnitude of the igene vectors. And again, this is just transforming that data. So we're going to change the vector b to the b prime as denoted on the chart. And so when we have like multiple variables, how do we calculate that new variable? And then we have feature vectors. Feature vectors is simply a matrix that has igene vectors of the components that we decide to keep as the columns. Here we decide whether we must keep or discard the less significant principal components that we have generated in the above steps. This becomes really important as we start looking at the back end of this, and we'll do this in the demo, but one of the more important steps to understand. And so we have the PCA example. Consider matrix X with n rows or observations and k columns or variables. Now for this matrix, we would construct a variable space with as many dimensions as the variable. But for our simplicity, let's consider this 3 dimensions for now. Now each observation, row of the matrix X, is placed in the k-dimensional variable space, such that the rows in the data table form a swarm of points in this space. Now we find the mean of all the observations and then place it along the data points on the plot. The first principal component is a line that best accounts for the shape of the point swarm. It represents the maximal variance direction in the data. Each observation may be projected onto this line in order to get a coordinate value along the PC1. This value is known as a score. Usually only one principal component is insufficient to model the systematic variation for a data set. Thus, a second principal axis is created. The second principal component is oriented such that it reflects the second largest source of variation in the data. While being orthogonal to PC1, PC2 also passes through the average point. Let's go ahead and pull this up and just see what that means inside our Python scripting. I'm going to use the Anaconda Navigator, and I will be in Python 3.6 for this example. I believe there's even like a 3.9 out. I tend to stay in 3.6 because a lot of the models I use, especially with the neural networks, are stable in 3.6. And then we open up our Jupyter. I'm in Chrome, and we go ahead and create a new Python 3. And for ease of use, our team in the back was nice enough to put this together for me. And we'll go ahead and start with the libraries. The first thing I like to do whenever I'm looking at any new setup, well, you know what, let's do the libraries first. We're going to do our basic libraries, which is matplotlib library, the PLT from the matplotlib library. Pandas, our data frame, PD, Numpy, our numbers array, NP, Seaborn for graphing, SNS, that goes with the plot that actually sits on matplotlib library, so the Seaborn sits on there. And then we have our ampersand, because we're in Jupyter Notebook, matplotlib library inline. The newer version actually doesn't require that, but I put it in there anyway just because I'm so used to it. And then we want to go ahead and take a look at the data. And in this case, we're going to pull in, certainly you can have lots of fun with different data, but we're going to use the cancer data set. And one of the reasons the cancer data set is it has like 36, 35 different features. So it's kind of fun to use that as our base for this. And we'll go ahead and run this and look at our keys. And the first thing we notice in our keys for the cancer data set is we have our data, we have our target, our frame, target names, description, feature names, and file name. So what we're looking for in all this is, well, let's take a look at the description. Let's go in here and pull up the description on here. I'm not going to spend a huge amount of time on the description because we don't want to get into a medical domain. We want to focus on our PCA setup. What's important is you start looking at what the different attributes are, what they mean. If you were in the medical field, you'd want to note all these different things, what they're measuring, where it's coming from. You can actually see the actual different measurements they're taking. No missing attributes. We page all the way to the bottom. And you're going to have your data, in this case our target. And if you dig deep enough to the target, let's actually do this. Let's go ahead and print target names. Real quick here, I always like to just take a look and see what's on the other end of this. Target names. Run that. And so the target name is it malignant or is it benign? So in other words, is this dangerous growth or is it something we don't have to worry about? That's the bottom line with the cancer in this case. And then we can go ahead and load our data. And you know what, let me go up just a notch here for easy of reading. It's hard to get that just right. I guess I'll have to do. So let's go ahead and look at our data. We're going to use our pandas. And we're going to go ahead and do our data frame. It's going to equal cancer data. Columns equals cancer. Feature equals feature names. So remember up here, we already loaded the names up of the features in there. What is going to come out of this? Let me just see if I can get to that. It's at the top of target names. That's just this list of names here in the setup. And we can go ahead and run this code. And it'll print the head. And you can see here we have the mean radius, the mean texture, mean perimeter. I don't know about you, this is a wonderful data set if you're playing with it, because like most of the data that comes in, half the time we don't even know what we're looking at. We're just handed a bunch of stuff as a data scientist going, what the heck is this? And so this is a good place to start, because this has a number of different features in there and we have no idea what these features means or where they come from. We want to just look at the data and figure that out. And now we actually are getting into the PCA side of it. As we've noticed before, it is difficult to visualize high-dimensional data. We can use PCA to find the first two principal components and visualize the data, this new two-dimensional space, with a single scatter plot. Before we do this, we need to go ahead and scale our data. Now, I haven't run this to see if you really have to scale the data on this, but as just a general runtime, I almost do that as the first step of any modeling, even if it's pre-modeling as we're doing here. In neural networks, that is so important. With PCA visualization, it's already going to scale it when we do the means and deviation inside the PCA. But just in case, it's always good to scale it. And then we're going to take our PCA with the scikit-learn uses very similar process to other pre-processing functions that come with scikit-learn. We instantiate a PCA object, find the principal components using the fit method, then apply the rotation and dimensionality reduction by calling transform. We can also specify how many components we want to keep when creating the PCA object. And so the code for this, oops, getting a little bit ahead. Let me go ahead and run this code. So the code for this is from sklearn decomposition import PCA. PCA equals PCA and components equals 2. And that's really important to note that, because we're only going to want to look at 2 components. I would never go over 4 components, especially if you're going to demo this with somebody else. If you're showing this to the shareholders, the whole idea is to reduce it to something people can see. And then the PCA fit, we're going to is going to take the scaled data that we generated up here, and then you can see we've created our PCA model with in components equals 2. Now, whenever I use a new tool, I like to go in there and actually see what I'm using. So let's go to the scikit webpage for the PCA. And you can see in here, here's our call statement. It describes what all the different setups you have on there. Probably the biggest one to look at would be, well, the biggest one is your components. How many components do you want, which you have to put in there pretty much. And then you also might look at the SVD solver. It's on auto right now, but you can override that and do different things with it. It does a pretty good job as it is. And if we go down, all the way down to, here we go, to our methods, if you notice we have fit and we have fit transform. Nowhere in here is predict, because this is not used for prediction. It's used to look at the data. Again, we're in the describe setup. We're fitting the data. We're taking a look at it. We've already looked at our minimum maximum. We've already looked at what's in each quarter. We've done a full description of the data. This is part of describing the data. That's the biggest thing I take away when I come zooming in here. And of course, they have examples of it down here if you forget. And the biggest one, of course, is the number of components. And then, I mean, the rest you can play with. The actual solver, whether you're doing a full or randomized, there's different things. It does pretty good on the auto. And now we can transform this data to its first 2 principal components. And so we have our XPCA. We're going to set that equal to PCA transform scaled data. So there we go. There's our first transformation. And let's just go ahead and print the scaled data shape and the XPCA data shape. And the reason we want to do this is just to show us what's going on here. We've taken 30 features. I think I said 36 or something like that, but it's 30. and we've compressed it down to 2 features. And we decided we wanted 2 features, and that's where this comes from. We still have 569 data sets. I mean data rows, not data sets. We still have 569 rows of data, but instead of computing 30 features, we're now only doing our model on 2 features. So let's go ahead and plot these and take a look and see what's going on. And we're just going to use our PLT figure. We're going to set the figure size on here. Here's our scatter plot, XPCA, X underscore PCA of 1. These are our 2 different perceptions we're using. And then you'll see right here, C for color, cancer equals target. And so remember, we have 0, we have 1. And if I remember correctly, 0 was malignant, 1 was benign. So everything in the 0 column is going to be 1 color, and the other color is going to be 1. And then we're going to use the plasma map, just kind of telling you what color it is. Add some labels, first principal component, second principal component. And we'll go ahead and run this. And you can see here, instead of having a chart, one of those heat maps with 30 different columns in it, we can look at this and say, hey, this one actually did a pretty good job of separating the data. And a couple things when I'm looking at this that I notice is, first, we have a very clear area where it's clumped together, where it's going to be benign. And we have a huge area, it's still clumped together, more spread out, where it's going to be malignant. Or I think I had that backwards. And then in the middle, because we're dealing with something, in this particular case, cancer, we would try to separate, I would be exploring how to separate this middle group out. In other words, there's an area where everything overlaps, and we're not going to have a clear result on it. Just because those are the people you want to go in there and have extra tests, or treat it differently, versus going in and saying just cutting into the cancer so that the body absorbs it and it dissipates, versus actively going in there, removing it, testing it, going through chemo and all the different things. That's a big difference, you know, as far as what's going to happen here. And that middle line where they overlap is going to be huge. That's domain specific. Going back to the data, we can see here, clearly by using these 2 components, we can easily separate these 2 classes. So the next step is, what does that mean? Interpreting the components. Unfortunately, with this great power of dimensionality reduction comes the cost of not being able to easily understand what these components represent. I don't know what principal component 1 represents, or second principal. The components correspond to combinations of original features. The components themselves are stored as an attribute of the filtered PCA object. And so when we look at that, we can go ahead and look at the PCA components. This is in our model we built. We've trained it. We can run that, and you can see here's the actual components. It's the 2 components each have their own array. And within the array, you can see what the scores they're using. And these actually give weight to what features are doing what. So in this Numpy matrix array, each row represents a principal component, and each column relates back to the original features. What's really neat about this is we can now go in reverse and drop this onto a heat map and start seeing what this means. And so let me go ahead and just put this down. Oops, I already got it down here. We'll go ahead and put this in here. We're going to use our dfcomp data frame, and we do our PCA components. And I want you to notice how easy this is. We're going to set our columns equal to cancer feature names. That just makes it really easy. And we're dumping it into a data frame. What's neat about a data frame is when we get to Seaborn, it will pull that data frame apart and set it up for us the way we want. And so we're just going to do the Seaborn heat map of our data frame composition, and we'll use the plasma coloring. And it creates a nice little color graph here. You can see we have the mean radius and all the different features along the bottom. On the right, we have a scale, so we can see we have the dark colors all the way to the really light colors, which are what's really shining there. This is like the primary stuff we want to look at. So this heat map and the color bar basically represent the correlation between the various features and the principal component itself. So, very powerful map to look at, and then you can go in here, and we might notice that the mean radius, look how on the bottom of the map it is on some of this. So you have some interesting correlations here that change the variations on that and what means what. This is more when you get to PostScribe. You can also use this to try to guess as what these things mean and what you want to change to get a better result.
Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. You can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. To see how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut one model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning, probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors, used to solve reward-based problems. No predefined data is used, no supervision, follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works and this is my reward, doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options. And we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching, and then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that. And it goes, oh, this is also reward based. And so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, that you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was, and then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import Numpy as NP. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here It looks like there's going to be a lie here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row. Same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, so it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3 just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment. And suddenly a reward system like this is going to be just, it's going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing, you add weights to it. And so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game, or even learn something that isn't a game, is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess, I think was a big one, where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where you get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent. In this case, our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on. How is this player figuring out how to maneuver around the board? And then the board, of course, returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state. This is class player. And when you say class player, we're not talking about a human player. We're talking about just the computer players. And this is kind of interesting. So remember I told you, depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it? As you try different moves, it gets to the end. The first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board. For P in positions, it's actually storing the different boards each time you go through. So it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important. This is kind of the heart of this. of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2, I probably should have done ABC. This has a step 3, step 4, and so on until you get to step N. And this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have our self set up on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here. And feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There is actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go, and it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here, and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just one round of training, in fact minimal training. And so it puts an X there, and I'm going to go ahead and do row 0, column 1. You can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, and you can see right here it let me win. Just like that I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3x3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. So you pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
In this video, we will learn the top job roles that you can get after becoming a data science professional. So what really is data science? Data science is the art of discovering patterns and trends from vast volumes of data using modern analytical tools and techniques. It helps you draw meaningful insights to make business decisions. As you can see on the screen, data science uses vast volumes of data which is fed to a machine that runs several algorithms to process the data and finally derive insights. Data science continues to evolve as one of the most promising and in-demand career paths for skilled professionals. Data science involves knowledge of programming, mathematics and algorithms, as well as domain expertise. Data science is being used in almost every sector of business these days. With companies generating vast volumes of data on a regular basis, they want to make sense of this data. So now, let's look at the various applications of data science. Data science is transforming the healthcare sector and is playing a pivotal role in monitoring a patient's health and deciding the necessary steps to be taken in order to prevent potential diseases from taking place. The primary use of data science in the health industry is through medical imaging. There are various imaging techniques like X-ray, MRI, and CT scan. All these techniques visualize the inner parts of the human body. Data science is also used for drug discovery and genomics, which is the study of sequencing and analysis of genomes. Retail sectors use data science to analyze their customer data and build sophisticated models to understand the customer behavior and find his or her sore points. Thereby, a customer tends to be easily influenced by the tricks developed by the retailers. Data science is widely used for inventory management, which refers to the stocking goods in order to use them in the time of crisis. Data science proves to be really efficient in deciding the location to set up a new store. Merchandising has become an essential part of retail business. The merchandising mechanisms go through the data, pick up the insights, and form the priority sets for the customers, taking into account seasonality, relevancy, and trends. Data science is mostly applied in the marketing domain for profiling, search engine optimization, customer management, responsiveness, and running real-time marketing campaigns. Predictive analytics is used in marketing to understand customers' behavior. Cluster models, collaborative filtering, and regression analysis are applied to spot the correlation patterns in the customer's behavior to predict future tendencies in purchasing. Data science is also used to qualify and prioritize leads, bring the right product to the market, and for targeting new customers. Data science in automotives isn't just about self-driving cars. Advancement in technologies can help keep auto organizations competitive by improving everything from research to design manufacturing to marketing processes. Image recognition and anomaly detection can quickly detect and eliminate faulty parts before they get into the vehicle manufacturing workflow. Root cause analysis, predictive maintenance, and supply chain optimization are done using data science in the automobile sector. Next, we have fraud detection. Frauds can happen in many forms and it affects virtually every industry. It has become a billion-dollar business and it is increasing every year. The PwC Global Economic Crime Survey of 2018 found that half, that is around 49% of the 7,200 companies they surveyed had experienced fraud of some kind. Fraud regularly happens in the banking and insurance sector as well as in e-commerce. Data science techniques and algorithms can help you overcome these frauds. The last application is regarding recommender systems. Data science helps companies make better decisions and recommender systems help data scientists succeed in it. Recommender systems are tools designed for interacting with large and complex information spaces and prioritizing items in these spaces that are likely to be of interest to the user. Personalized recommendations are an important part of many online e-commerce applications like Amazon.com, Netflix, and Pandora. Now that we have looked at the various applications of data science, let's see the different job roles you can get into after becoming a data science professional. So the first job role we have is of a data analyst. A data analyst is responsible to collect, process, and perform analysis on large data sets. They bring technical expertise to ensure the quality and accuracy of that data, then process, design, and present it in ways to help people, businesses, and organizations make better decisions. They also have to perform queries on the databases from time to time. They should have technical expertise in SQL, business intelligence, and programming languages such as Java and Python. Now coming to the salary, a data analyst in the United States earns around $62,453 per annum, while in India you can expect to earn nearly 5,21,000 rupees per annum. Some of the companies hiring for data analysts are Electronic Arts, Microsoft, Bloomberg, Amazon, Accenture, and Siemens. The second job role we have is of a business analyst. Business analysts are people who are responsible for bridging the gap between IT and the business using data analytics to assess processes, determine requirements, and deliver data-driven recommendations and reports to executives and stakeholders. They create a detailed business analysis outlining problems, opportunities, and solutions for a business. A business analyst should have good communication and problem-solving skills. Also, they need to know Python, R, BI tools, SQL, and Excel. Now moving to their salaries, a business analyst earns around $68,346 per annum in the United States, while in India, they earn nearly 7 lakh rupees per annum. The companies that can help you start your career as a business analyst are Dell, Genpact, Philips, IQVIA, and Honeywell, to name a few. Next, we have data engineer or data architect. A data engineer or architect develops, constructs, tests, and maintains architectures such as databases and large-scale processing systems. They discover opportunities for data acquisition, develop dataset processes for data modeling, data mining, and production. They also recommend ways to improve data reliability, efficiency, and data quality. They should be well versed with big data analytics, Hadoop, Scala, data warehousing, data modeling, ETL, and Linux operating systems. A data engineer earns around $103,000 in the United States, while in India they earn around 8,85,000 rupees per annum. Companies hiring for data engineers and architects are Fidelity Investments, Capgemini, Genpact, Accenture, Standard Chartered, and Hewlett Packard Enterprise. At number 4, we have machine learning engineer. A machine learning engineer uses different algorithms and statistical modeling to make sense of vast volumes of data. They are also expected to perform A/B testing, build data pipelines, and implement common machine learning algorithms such as regression, classification, clustering, etc. They should know programming, probability and statistics, SQL, data visualization, and machine learning. Coming to their salary, a machine learning engineer earns around $114,000 per annum in the United States, while in India, they can earn around 8 lakh rupees per annum. Some of the companies that can help you excel in your career as a machine learning engineer are Apple, Oracle, CloudX Lab, Rapido, Qualcomm, and Amazon. And finally, we have the most exciting job role in the field of data science, that is, of a data scientist. A data scientist makes value out of data. They proactively fetch information from various sources and analyze it for better understanding about how the business performs and builds AI tools that automate certain processes within the company. A data scientist understands the challenges in business and comes up with the best solutions using modern tools and techniques to analyze, visualize, and build prediction models to make business decisions. They need to have experience querying databases and using statistical computer languages such as R, Python, SQL, etc. They should have knowledge of advanced statistical techniques and concepts such as regression, properties of distributions, and statistical tests. As per current trends, a data scientist can earn around $113,000 per annum in the United States, while in India, they can earn an average of 10,47,000 rupees per annum. Companies hiring for data scientists are Amazon, IBM, Apple, Rakuten, General Electric, Philips, and Google. Now let me repeat the list once again. First, we covered data analyst, then business analyst, followed by data engineer or architect, machine learning engineer, and finally, data scientist. So with that, we have covered the top 5 job roles in data science. Apart from these job roles, you can also become a statistician, a database administrator, an analytics consultant, and business intelligence professional.
Let's go ahead and take a look at building a resume. Always exciting, putting ourselves out, selling ourselves. And if you looked at some of our other videos dealing with resumes, you'll see a trend here. The top part is so different than what resumes were in the 90s, in the 2000 to 2010. They've evolved. They've really evolved. It used to be 2000, 2010, maybe LinkedIn, maybe one other reference. Now you're going to see that we want those references. This is a sales tactic, which now has come into resumes. It used to be that if you were a real estate agent, every real estate agent I knew, I used to deal with real estate software for the real estate industry back in the 90s. Every real estate agent wanted their picture on their business card. They wanted their picture, if they could, put on their contracts. They want people to see the face. So that's really a big change, is to make sure that it stands out. You stand out. Here's a picture of somebody, so you're more than just a couple letters and a name. And of course, you need your contact information, should always be at the top. You have your summary. What are you focusing on? Be a little careful with your summary, because if you have everything in your summary and then they scroll down to experience and education and skills, they're going to stop. The second you repeat yourself in your resume, that usually means to the reader, hey, this person doesn't have anything more to offer me, I'm done. So be a little careful how you word your summary. Most companies appreciate when you come in here and you've adjusted this summary to be both about you and how you're going to serve that company. So it's worth researching that company to find out how those connect and put that in the summary. Take some time to do that. That's actually a pretty big deal. And the references are huge also, especially in data science. When you're talking about any of the programming or data science, data analytics, having a place to go where they can look it up and scroll down and see different things you're doing, whether it's LinkedIn in this case, which is the business profile most commonly used, GitHub where you have stuff published, Facebook. I'm always hesitant because that tends to push more towards social media type jobs and other jobs. But certainly there's people who have Facebook who do marketing and stuff like that. But these links, having these basic links here is important. People are starting to look for that for some other setup. Maybe you have a personal website. This is a good place to put that so that they now have a multitude of links that go back to you and highlight who you are. And then the next part, or next 4 parts. So for the next 4 parts, we have a combination of experience, education, skills, certifications. And you can see they're organized. If you have, a lot of people like to see what kind of degree you have. They want to know where it came from. And if you just got out of college, you're going to put education at the top. And then maybe you'll put skills after that, and then your experience at the bottom. If you've been in the field for years, my degree, just to give you my age, goes back to the early 90s. So I usually put education at the very bottom. And then because a lot of the stuff I'm trying to sell myself on right now is my skills, I actually put that at the top. And I'll put my education, my certifications at the bottom, my skills, and then my experience is, since it's a huge part of my resume, goes next. You can organize these in whatever order you want that's going to work best for you and sell you. So remember, you're selling yourself. This is your image. Probably don't wear an old tie-dye t-shirt with holes in it. Something nice because it is professional. And of course your summary. And then what do you have to offer the company? And again, when I put out resumes, and I haven't done a resume in a while, you go in there and you can take this and reorganize this. So if the company's looking for something specific, you might put the experiences specific to that company. You might even take experience, if you have like a long job history like I do, I've gone into a lot of different things, you might leave out those companies or those experiences that had nothing to do with data science because it just becomes overwhelming. Resume should only take about 30 seconds to glance over, maybe a minute tops, because after that point you've lost the person's interest. And if they want to dig deeper, they now have links, they have your website, they have LinkedIn, and they can now take this and they come back to it and they go, oh, okay, let's look at this person a little closer. So quick overview, this is your sell sheet selling you to the company. So always tie it to the company so that you have that, what am I going to give this company? What are they going to get from me? Welcome to Data Science Interview Questions. Before we dive in and start going through the questions one at a time, we're going to start with some of the logical kind of concept that enters in a lot of interviews. In this one, you have 2 buckets, one of 3 liters and the other of 5 liters. You're expected to measure exactly 4 liters. How will you complete the task? And note, you only have the 2 buckets. You don't have a 3rd bucket or anything like that, just the 2 buckets. And the object of the question like this is to see how well you are thinking outside the box. In this case, you're in a larger box. You have 2 buckets. And also the pattern which you go on. And what that means is if you look at the 2 buckets, and we'll show you their answer in just a second, you have a bucket with 3 liters and a bucket with 5 liters. And the first thought is, what happens if you go from left to right? So we have a direction. And what happens if you pour the 3 liters into the 5 liter bucket? Well, if you pour the 3 liters into the 5 liter bucket, you have an empty bucket of 3 liters. And what's really important here is thinking outside the box, you realize that you have a 5 liter bucket that has 3 liters in it and 2 empty liters. So you have 2 additional liters you can fill up. If we continue that process, we can pour from the left to right, from the small bucket to the large bucket. You can now measure in 2 additional liters into the 5 liter bucket. And 3 minus 2 is 1, and you can keep doing that. You can empty the 5 liter bucket in, pour those 3 liters in, that 1 liter in, and then you can pour 3 liters in. What's cool about these questions as you explore them is you realize there's multiple ways usually to solve them. I went from small bucket to big bucket. The Simplilearn team, their solution that they pulled out was you fill the 5 liter bucket and empty it into the 3 liter bucket. Now you're left with 2 liters in the 5 liter bucket. So that's great. We can empty the 3 liter bucket. So now we're going from large to small. Remember, we went from small to large. So you can go either way, but you have to go one way or the other, it turns out. And you can empty the 3 liter bucket and pour the contents of the 5 liter bucket in it. So the 3 liter bucket now has 2 liters. And if it has 2 liters, that means it has an empty 1 liter. And by now you probably have guessed that if you have that empty space, you can start using that empty space of 1 liter as a measuring. So we fill the 5 liter bucket again, and we pour the water in the 3 liter bucket. It already has the 2 liters, and so we're only pouring 1 liter in there, and 5 minus 1 is 4. So interview questions, they break up into all kinds of different patterns. We have logic like this one, which is a lot of fun. We have questions that come up that are more vocabulary. List the difference between supervised and unsupervised learning. Probably one of the fundamental breakdowns in data science. And supervised learning uses known and labeled data as input. Supervised learning has a feedback mechanism. Most commonly used supervised learning algorithms are decision tree, logistic regression, support vector machine. And you should know that those are probably the most common used right now, and there certainly are so many coming out. So that's a very evolving thing, and be aware of a lot of the different algorithms that are out there outside of the deep learning. Because a lot of these work faster on raw data and numbers than a deep neural network would. Unsupervised learning uses unlabeled data as input. Unsupervised learning has no feedback mechanism. Most commonly used unsupervised learning algorithms are k-means, clustering, hierarchical clustering, the Aporia algorithm. And there certainly are more. I'm going to say k-means definitely is at the top of the list, and the hierarchical clustering, those two are used so many times. So really important to understand what those are and how they're used. And most important is understand that supervised learning is you have your data set where you have training data and you have all those different pieces moving around, but you're able to train it. You know the answers. And unsupervised, we're just grouping things together that look like they go together. How is logistic regression done? Logistic regression measures the relationship between the dependent variable, our label, what we want to predict, and the one or more independent variables, our features, by estimating probability using its underlying logistic function, sigmoid. And whenever I draw these charts, I always end up drawing them the right-hand side first, because you want to know what your output is. What is it you want out of here? And the left-hand side, what do you have going in? So you have your in and out. You can see we have a nice labeled image here to help you remember this. We have our inputs, we have our linear model, we have our probabilities. What are the probabilities of it being a certain way based on these features coming in? The sigmoid function, and it's important to note that the sigmoid function is maybe the most commonly used, but it's only one of a number of functions that are out there. And the sigmoid function turns our probabilities into a value between 0 and 1, or very close to 0 and very close to 1, between 0.1 and 0.009. And based on that, we generate an answer, in this case is 0 or 1. How is logistic regression done? So last time we talked about the sigmoid function. Generally, depending on what your interview and level of math and what expertise you're going in for the market, you'll have to understand that formula of the probability equals 1 over 1 plus e to the negative y. And that's e to the base 2. So you have your probability function or your sigmoid function, which pushes it. As you can see, we have a nice visual of that, and that helps a lot to have that visual on the sigmoid function. You definitely should know your y equals m times x plus c, your basic Euclidean geometry of forming a line, and the slope plus the intercept, the y-intercept. And then you have your natural log, and the natural log is to the e as opposed to a base 2 or base 10. So your natural log to the e of the probability over 1 minus a probability equals your m times x plus c, or your Euclidean line. That helps a lot as far as the graphing and understanding the sigmoid function. So we'll just keep pushing on to question number 3. Explain the steps in making a decision tree. And I noticed last time we brought up the decision tree in the forest, a lot of questions came up. What is the difference? So let's go through that. When you make a decision tree, you're going to take the entire data set as input. You're going to calculate entropy of the target variable as well as the predictor attributes. And remember, entropy is just how chaotic is it. So if you have like, banana and grapes and oranges, if you're mixing in fruit and that's your data coming in, you have all these different objects that are so separate from each other, and the more they become uniform, the lower the entropy. And we call that information gain. So we gain information on sorting different objects from each other. So you have your entropy, you have to calculate your information gain of all attributes, and then you choose the attribute with the highest information gain as the root node. So if you can separate your group and each group, chaos in each group is lowered, whichever split lowers the chaos the most, that's where you split it, and that's your root node. At that point, you repeat the same procedure on every branch till the decision node of each branch finalized. So understanding that setup is pretty important as far as decision trees. And you can see here we have a nice visual of a decision tree. For example, if you want to build a decision tree to decide whether we should accept or decline a job offer, since these are interview questions, that's a good one to ask. And just as a tip, you should be pretty aware of the formula for entropy and information gain. So you need to look those up if you don't remember those. And the salary, if it's greater than 50,000, no, decline the offer. Yes, it's got a good salary. The commute is greater than an hour. Yes, decline the offer. No. Offers incentives. Yes, accept the offer. No incentives, decline the offer. So we use decision tree pretty much for everything if you want. And if you have a decision tree, then you also should understand how do you build a random forest model. And remember that a random forest is built up of a number of decision trees. So if you split your data up into a lot of different packages and you do a decision tree in each of those different groups of data, the random forest is bringing all those trees together. So how do you build a random forest model? Randomly select k features from a total of m features, where k is less than m. Among the k features, calculate the node D using the best split point. Split the node into daughter nodes using the best split. Repeat steps 2 and 3 steps until leaf nodes are finalized. Build forest by repeating steps 1 to 4 for n number times to create n number of trees. So you can see it's got the same build pattern as the tree, but instead you're building a number of different trees, little small trees, so it all have an n leaf node. Random forest has a vote at the end, and whoever gets the most votes wins. That's the answer. How can you avoid overfitting of your model? Very important question in any kind of mathematical, scientific, data science setup, in any of them. There are 3 main methods to avoid overfitting, and you should really understand overfitting. Overfitting means that your model is only set for a very small amount of data and ignores the bigger picture. Keep the model simple. Take into account fewer variables, thereby removing some of the noise in the training data. Good advice for any programming at all. Use cross-validation techniques such as k-folds cross-validation. Use regularization techniques such as lasso that penalize certain model parameters if they're likely to cause overfitting. And you should also be well aware that your cross-validation techniques, that's like a pre-data, or your lasso and your regularization techniques are usually during the process. So when you're prepping your data, that's when you're going to do a cross-validation, such as like splitting your data into 3 groups, and you train it on 2 groups and test it on 1, and then switch which 2 groups you test it on, that kind of thing. So can you solve, another one of these, I love these things. There are 9 balls, out of which 1 ball is heavy in weight, and the rest are of the same weight. In how many minimum weighings will you find the heavier ball? And when we say weighing, think of a scale where you can put objects on one side and the other, and you can see which side is heavier. And you want to minimize that. You want to split the balls up in such a way that you're going to do as few measurements as you can. You will need to perform 2 weighings. So you can get it down to just 2 weighings. And I always think if there's 9 balls, I'm going to divide them into 3 groups of 3. Place 3 balls on each side. So you can just randomly pick 6 of the balls and 3 on one side, 3 on the other. And if they balance out, both sides are equal, then you know the heavy weight isn't in any of those. So out of the remaining 3 balls from step 1, take 2 balls and place 1 ball on each side. A little tricky there because I always want to put all 3. I want to put 2 on one side and 1 on the other, but no, just randomly pick 2 of those, put 1 on each side. If they balance out, then the left out ball, the one you didn't measure, will be the heavier one. Otherwise, you'll see it in the balance. You'll see which one's heavier because you'll take one of the balls down. Now we go to scenario B. where they did not balance out. So now we know which side has a heavier ball in it. And it's just very similar to what we did before. If the balls in step 1 do not balance out, then take those 3 balls that had the heavier side on them and reproduce step 2 to find out the heavier ball. Difference between univariate, bivariate, and multivariate analysis. And hopefully, if you know a little Latin, it'll kick in there that you have uni and you have bi and you have multi, because the answer is in the words themselves. So the first one, this type of data contains only one variable, so that's the univariate. The purpose of the univariate analysis is to describe the data and find patterns that exist within it. So when you only see one variable coming in this case we're using height of students, you're limited as far as what you can do with that data. So you can come up and draw different patterns and conclusions from those patterns using the means, the median, the mode, dispersion, range, minimum, maximum. So we're describing the data. So all those words would describe the data, and that's about all you can do with data like that. There's no correlation, there's nothing to go beyond that as far as guessing or predicting anything. So we move into bivariate. Uni means 1, bi means 2. Bivariate, this type of data involves 2 different variables. The analysis of this type of data deals with causes and relationships, and the analysis is done to find out the relationship among the 2 variables. And this is always a favorite one because everybody loves ice cream in the summer when it's hot, and very few people go for ice cream in the winter when it's really cold, so it's easy to see the correlation in the data. The temperature and ice cream cells in summer season. And you can see here where the temperature goes from 20 to 35. And as the temperature goes up, so does the cells of ice cream. It goes from 2,000, I'm not sure 2,000 of what, so I'm guessing it's a very large chain, because if they're selling 2,000 ice cream cones, and they have a lot of business, good for them. A little vendor on the corner selling 2,000 ice cream cones a day and 3,100 the next day. Here, the relationship is visible from the table that temperature and cells are directly proportional to each other. So the hotter the temperature, we can predict an increase in cells. So the word prediction should come up. So we have description and prediction. When the data involves 3 or more variables, it is categorized under multivariate. It is similar to bivariate, but contains more than one dependent variable. In this example, another really common one, the data for house price prediction, the patterns can be studied by drawing conclusions using mean, median, and mode, dispersion, or range minimum, maximum, etc. And so you can start describing the data, that's what all that was, and then using that description to guess what the price is going to be. So this is very good if you're in the market and you have already looked at the area and you already know that a 2-bedroom, 0-floor, 900 square foot house usually runs about 40,000. You can guess what the next one that looks similar to it is. And I'll just throw in another word in there I don't see very often unless you're really a hardcore data science. We talked about describing the data, descriptive. We talked about predictive, and there's also postscriptive. Postscriptive means we're going to change the variables to try to guess what the outcome is if we change what's going on. So that would be the next step. But that usually doesn't show up unless you're dealing with some really hardcore data science groups. What are the feature selection methods to select the right variables? There are 2 main methods for feature selection. There's filter methods and wrapper methods. And when you're filtering before we discuss the 2 methods real quick, the best analogy for selecting features is bad data in, bad answer out. So when we're limiting or selecting our features, it's all about cleaning up the data coming in so it's cleaner and is more representative of what we're trying to predict. Filter method. Filter methods as they come in, we have linear discrimination analysis, ANOVA, chi-squared. Chi-squared is probably the most common one. And these are all part of pre-processing. We're taking out all the outliers, all the things that have a difference that is very different from the data we're looking at, the odd ones. And sometimes you take the odd ones out and then you analyze them separately to see why they're odd. But remember your filter methods, you want to pull all that weird stuff out. Wrapper methods, on the other hand, are forward selection, backward selection, recursive feature elimination. And one of the most important things to remember about wrapper methods is they're very labor intensive. You have to have some pretty high-end computers if you're doing a lot of data analysis with the wrapper method. And just quickly, forward selection means you have all your different features. They're off to the side, and we test just one feature at a time, and we keep adding them in until we get a good fit. Backward is we have all the features, and we run a test on that to see how well it does, and then we start removing features to see what works. And recursive, which is the most processing-hungry algorithm out there, goes through and just recursively looks through all the different features and how they pair together. But again, we have filter method and wrapper method, and it's important to understand that we're sorting the data out and finding out which features are going to represent the data the best and which ones are not going to really add any value to our models. Let's jump to number 8. In your choice of language, write a program that prints the numbers from 1 to 50, but for multiples of 3, print fizz instead of the number, and for the multiples of 5, print buzz. For numbers which are multiples of both 3 and 5, print fizz buzz. And this really is testing your knowledge in iterating over data. Very important. My sister, who runs at the university, the data science team, is in charge of their department. The first question she asks in her interview of anybody who comes in is, how do they iterate through data? So if this question comes up a lot and it's very important you have an understanding, and there's actually a slight error on this code, which I'll point out in just a second. The concept is we have fizz buzz in range, and you have range 51, which in this case goes from 0 to 51. And I'm going to challenge you to see if you can catch the error, and I'll tell you at the end of the code where the error is. What that means is that we're going to go through all the numbers 0, 1, 2, 3, 4, and we're going to process through this loop. If the remainder of fizz buzz divided by 3 equals 0, and fizz buzz divided by 5 also equals 0, then print fizz buzz. Continue. And else if fizz buzz divided by 3 equals 0, then print fizz, continue. Else if fizz buzz divided by 5 equals 0, print buzz, continue, and print fizz buzz. You print the answer. In this case, fizz buzz is either going to be the number we generated, which is 0, or it'll be the fizz buzz, fizz, or buzz. Whew, that's a mouthful. Now, if you didn't catch the error in the code, which is always a fun game, find the error. It has to do with the range. And it's important to remember the range here says range to 51. That's 0 to 51, which is correct. We want to go to 51 because it stops. It gets to 50 and it stops. So that's 0 to 50. But if you remember, the question asks from 1 to 50. So the range should be 1, 51, not just 51, which does 0 to 51. In this particular script, in Python, you could leave out the continue, but the continue in this script skips the next else if, so it doesn't keep processing it going down. And in programming, a lot of scripts you don't need the continue answer, so it would depend on what script you chose. And there's probably some other ways to do this. It's a lot of fun. And you can see here from the output, we end up with fizz buzz for 0, which shouldn't be there. 1, 2 fizz, 4 buzz, fizz, 7, 8 fizz buzz, 11 fizz, and so on. Sounds like a drinking game from my college days. So long ago, many decades ago. You are given a data set consisting of variables having more than 30% missing values. How will you deal with them? Oh, the joy of messy data coming in. Ways to handle missing data values. Data set is huge. We can just simply remove the rows with missing data values. It is the quickest way, i.e. we use the rest of the data to predict the values. You just go in there and say any row of our data that has a NA in it, get rid of it. That doesn't work with smaller data. So with smaller data, you start running into problems because you lose a lot of data. And so we can substitute missing values with the mean or average of the rest of the data using Pandas data frame in Python. There's different ways to do this, obviously, in different languages. And even in Python, there's different ways to do this. But in Python, it's real easy. You can do the df.mean, so you get the mean value. So if you set mean equal to that, then you can do a df.fillNA with the mean value. Very easy to do in a Python Pandas script. And if you're using Python, you should really know Pandas and Numpy, NumPython and Pandas data frames. For the given points, how will you calculate the Euclidean distance in Python? So back to our basic algebra from high school. Euclidean distance is the line on the triangle. And so if we're given the points plot 1 equals 1, 3, plot 2 equals 2, 5, we know that from this we can take the difference of each one of those points, square them, and then take the square root of everything. So the Euclidean distance equals the square root of plot 1, 0 minus plot 2 of 0 squared plus plot 1 of 1 minus plot 2 of 1 squared. Mouthful there. And you can remember if you have multiple dimensions that go past 2 dimensions, you could have plot 3 can simply be the distance from plot 1. You only need to do one side of that. Or plot 2, you can do either way and square that and take the square root of that. Another mind bender. How to calculate something, how to figure out the solution to something. What is the angle between the hour and minute hands of a clock when the time is half past 6? So you want to kind of imagine that clock where the large hand is pointed down to the 30 and the other half is going to be right between the 6 and the 7 because it's half past 6. There's actually a couple ways to solve this, but let's take a look and see how they did it. Note, a clock is a complete circle having 360 degrees. In 1 hour, the hour hand covers 360 over 12, so it equals 30 degrees for each hour. In 1 minute, the minute hand covers 360 degrees over 60 minutes, or 6 degrees per minute. The minute hand has traveled for 30 minutes, so it has covered 30 times 6, which equals 180 degrees. So we know that's 180 degrees from the 12. The hour hand has traveled for 6.5 hours, 6.5, 6.5, so it's covered 6.5 times 30, which equals 195 degrees. The difference between the two will give the angle between the two hands, thus the required angle equals 195 minus 180 equals 15 degrees. And this is nice the way they solved it, because you can now punch in any kind of time within reason. The hard part is on the hours, is you have to be able to convert the hours into decimals. Explain dimensionality reduction and list its benefits. Dimension reduction refers to the process of converting a set of data having vast dimensions into data with lesser dimensions, fields, to convey similar information concisely. It helps in data compressing and reducing the storage space. It reduces computation time as less dimensions lead to less computing. It removes redundant features. For example, there's no point in storing a value in two different units, meters and inches. And I certainly run into a lot with this with text analysis. I've been known to run a text analysis over a series of documents, ends up with over 1.4 million different features. That's a lot of different words being used. And if you do what they call connect them, you connect two words together, now you're up to 4.8 million different features, and you start having to figure ways to bring that down. What can we get rid of? That kind of thing. So you can see where that can get really high in on processing, and learning how to reduce the list dimensions is very important. How will you calculate eigenvalues and eigenvectors of a 3x3 matrix? And what they're really looking for here is when you write it out, for the eigen is that you know that you're going to use the lambda. That's the most common one. Obviously you can use any symbol you want, but lambda is usually what they use. And that you do it down the middle diagonal. And so when you take that matrix and you take the characteristic equation, you end up with the determinant, and that's the minus 2 minus lambda, minus 4, 2, minus 2, 1 minus lambda, 2, 4, 2, 5 minus lambda. And that's what they're looking for, and you know that's equal to 0. So when you're doing a matrix in the eigen setup with the eigenvectors, that's all going to come out equal to 0. And then you can go ahead and write the whole equation out. So we can expand the determinant, as you can see right here, the minus 2 minus lambda times, it's a mouthful. I'll leave it up here for a second so you can look at it. When you break it down into the algebraic functions, you end up with minus lambda cubed plus 4 lambda squared plus 27 lambda minus 90 equals 0. So now we have a nice algebraic equation built from the eigenvectors. And always remember, you can hit the pause button, and you can also send a note. Send a note to Simplilearn if you have more questions on vectors or on this. Definitely have that resource available to you, or post down in below on the YouTube video comments. And so when we calculate the eigenvalues and eigenvectors of a 3x3 matrix, as we continue on down the math of this, and to be honest, I really don't like working with matrices like this. It's important to understand the math behind it, and it's important to know the code just enough so that you're not lost when someone's explaining it or it comes up when I'm working on different data science models. Of course, if you're dealing with the high-end math side of it, then you better know this. First is by hit and trial. So you try in different variables to solve for 0, and you can come in here and you'll find that if we put in the 3 in there, we end up with a 0 at the end, and substitute the 3. Hence, we end up with lambda minus 3 as one of the factors. And you can do the math going out on that, where we have lambda cubed minus 4 lambda squared minus 27 lambda plus 90 equals lambda minus 3 times lambda squared minus lambda minus 30. So eigenvalues based on that one are 3, minus 5, and 6. And then from there we can calculate the eigenvector for lambda equals 3. And you can see here where the matrix as we write it out is the minus 5, minus 4, 2, minus 2, minus 2, minus 2, 4, 2, 2. That was from the beginning. Put in the x, y, and z equals 0, 0, 0. And so when we put in those numbers and we calculate them out, we have for x equals 1, we have the minus 5 minus 4y plus 2z equals 0, minus 2 minus 2y plus 2z equals 0. And subtracting the two equations we just had, we get 3 plus 2y equals 0, y equals minus 3 over 2, and z equals minus 1 over 2. That's going back to the first equation. And similarly, we can calculate the eigenvectors for minus 5 and 6. How should you maintain your deployed model? Ooh, distribution time, my favorite. I spent 10 years in software distribution. So first thing, and this is true not just of your data science model, but of any computer code going out there. This is basic setup can work, although usually there's a little added steps in there. First, we're going to monitor it. So we have a constant monitoring of all the model is needed to determine the performance accuracy of the models. So yeah, we want to just keep an eye on it. We want to make sure they're accurate. We want to make sure that whatever they're supposed to predict, or I threw in that bonus word, postscript, where you change something and you want to figure out how your changes are going to affect things, we need to monitor it and make sure it's doing what it's supposed to do. Evaluation metrics of the current model is calculated to determine if new algorithm is needed. And then we compare it. The new models are compared against each other to determine which model performs the best. And then we do a rebuild. The best performing model is rebuilt on the current state of data. And this is interesting. I found this out just recently. If you're in weather prediction, the really big weather areas have about 7 or 8 different models depending on what's going on. And so you actually have almost a little forest going on there where they're like, which model is going to fit best, and this is what we're going to use to predict the weather with. So not only do you don't necessarily get rid of the models, but you figure out which models fit data of what's going on, or the current state of data. What are recommender systems? Most commonly used nowadays in marketing, so a very big industry understanding recommender systems predicts the rating or preference a user would give to a product. And they're split into 2 different areas. One is collaborative filtering, and a good example of that is the Last.fm recommends tracks that are often played by other users with similar interests. So people who, if you're on Amazon, people who bought this also bought that. This got me a few times. And then there's content-based filtering. And we're looking at content instead of looking at who else is listening to the music. They use the example Pandora, which uses the properties of a song to recommend music with similar properties. So you have collaborative filtering and content-based filtering. How to find RMSE and MSE in linear regression model. Hopefully you remember what the 2 acronyms mean, because that is like half the answer. We have the root mean square error and the mean square error in linear regression model. So we're looking for error. The RMSE and the MSE are the 2 of the most common measures of accuracy for a linear regression model. And you can see here we have the root mean square error, RMSE equals, and this is the square root of the sum of the predicted minus the actual squared over the total number. So we're just looking for the average, mean. So we're looking for the average over the n. And the reason you need to know about the difference between RMSE versus MSE is when you're doing a lot of these models and you're building your own model, why do you need to take the square root of it? It doesn't change the value as far as the way you're using it, because you're looking at to see whether the error is greater or less than. So why add that extra computation in? So a lot of models use the MSE, which indicates the mean square error, or the average error. And it's the same formula minus the square root at the end, or across the whole thing. Another riddle to solve. If it rains on Saturday with a probability of 0.6, and it rains on Sunday with a probability 0.2, what is the probability that it rains this weekend? And the trick in probabilities on this case is we need to know what is the probability of it not raining. What's the chance of it not raining on Saturday? And if it doesn't rain on Saturday, we want to take that and combine that with the chance of it not raining on Sunday. The total probability, which in this case we're just going to use 1, minus the probability that it will not rain on Saturday, so that's 1 minus 0.6. We're going to take that as a union, which we simply just multiply them together, of the probability that it will not rain on Sunday. And it's important to recognize the union here, or and you can see by the formula down here, we end up with 0.68 or 68% chance that it will rain on the weekend. And there are a couple other ways to solve this, but this is probably the most traditional way of doing that. How can you select K for K-means? So first you better understand that what K-means is, and that K is a number of different groupings. And most commonly we use is the elbow method to select K for K-means. The idea of the elbow method is to run K-means clustering on the data set where K is the number of clusters. Within the sum of squares, WSS is defined as the sum of the squared distance between each member of the cluster and its centroid. And you should know all the terms for your K-means on there. And with the elbow point, and again, here's our iteration in our code. We talked about that earlier. You iterate starting with, usually you don't start right at 1, but you might start with 2, 3, or 4. And you just see where it comes out, and you can see the nice elbow there, which is easy to see graphically, where the number of K clusters and the WSS value drops, and then it just kind of flattens out, and there's no reason to take the K-means any further. What is the significance of p-value? Oh, good one. especially if you're dealing with R, because that's the first thing that pops up. P-value typically less than or equal to 0.05 indicates a strong evidence against the null hypothesis, and you should know what a difference, why we use null hypothesis instead of the hypothesis. So you reject the null hypothesis. Very important, that term null hypothesis, in any scientific setup and also in data science. It doesn't mean that it's true. It means that there's a high correlation that it's true. So if your null hypothesis means it's not true, your hypothesis has a high correlation that it's probably true. And if the p-value is typically greater than 0.05, it indicates a weak evidence against the null hypothesis. So you fail to reject the whole null hypothesis, and if you reject that, then your actual hypothesis is probably not true. The correlation of your data with what you think it's saying is probably incorrect. And if you're right at the cutoff of 0.05, it's considered to be marginal. Could go either way. And again, you can use that p-value on different features to decide whether you're going to include your features as far as something worth exploring in your data science model. How can outlier values be treated? Ooh, good one. You can drop outliers only if it is a garbage value. So sometimes you end up with like one outlier that just is probably someone's measurements way off. Height of an adult equals ABC feet. This cannot be true, as height cannot be a string value. In this case, outliers can be removed. If the outliers have extreme values, they can be removed. For example, if all the data points are clustered between 0 to 10, but one point lies at 100, then we can remove this point. And again, sometimes you just look for the outliers so you can see what's going on, if there's something unusual there. So maybe the equipment's not calibrated correctly. If you cannot drop outliers, you can try the following. Try a different model. Data detected as outliers by linear model can be fit by nonlinear model. So be sure you are choosing the right model. So if it has like more of a curved look to it instead of a straight line, you might need to use something other than just a straight line linear model. Try normalizing the data. This way the extreme data points are pulled to a similar range. If you can use algorithms which are less affected by outliers, example random forest. So there's another solution, is you can come up with the random forest, which a lot of times completely bypasses your outliers. How can you say that a time series data is stationary? Oh, that's an interesting term. Stationary, meaning it's not moving, but it's a time series. We can say that a time series is stationary when the variance and mean of the series is constant with time. And the graphic example is very easy to see. We have our the variance is constant with time, so we have our first variable y and x being the time factor and y being the variable. As you can see, goes through the same values all the time. It's not changing in the long period of time. So that's stationary. And then you can see in the second example, the waves get bigger and bigger, so that's non-stationary. Here the variance is changing with time. Again, we have y, which stays constant, so that if you look at the bigger picture, it's the same wave over and over again. And then of course we have where the wave is growing in size going up. It can also go down, so it'd also be non-stationary. How can you calculate accuracy using confusion matrix? Oh, great one. Confusion matrices are so useful when you're taking that first look at data, and also when you're showing the shareholders and you want to ask them for money. How can you calculate accuracy using confusion matrix? So you have your total data that we're looking at is 650, and you have your predicted values and your actual values, and you have your predicted P and your actual P. And so when you look at this, you'll note that if the predicted P and the actual P are 262, but our predicted P also had 15 that weren't correct. So you can see there's a false positive there of 15. And the same thing with the N. You can see where N predicts N, and it has a false negative of 26 out of the total number of N values in there. And so we can do an accuracy on there. The true positive plus the true negative is our total observations. So you have a total of 0.93 accuracy, or 93%. And just a quick note on this, this is so important, because it's one thing if someone is being diagnosed with, say, cancer. You know, this is life, death, or is my nuclear reactor going to blow up? Suddenly, if the P is the probability of it blowing up, and this, let's say you have 15, that's a lot less than, say, the 26 chances of it blowing up. You know, so the actual domain of your data is very important. So if you're non-positive, you don't really care about the predicted value having non-positive as positive, because they're going to go do a biopsy on the cancer or whatever anyway. But you're very interested if you have a positive, an actual positive value, which is looked at as negative, a false negative. That's really important in that domain, depending on what domain you're in. Write the equation and calculate precision and recall rate. And so continuing with our confusion matrix, I was just talking about the different domains. We have the precision equals 262 over 277. So your precision is the true positive over the true positive plus false positive. And the recall rate is your true positive over the total positive plus false negative. And you can see here we have that 262 over 277 equals a 94%. And the recall over here is the 262 over 280, which equals 9.9 or 90%. And oh good, we're going to take a pause for another brain teaser. If a drawer contains 12 red socks, 16 blue socks, and 20 white socks, how many must pull out to be sure of having a matching pair? The last time I went through these kind of brain teaser things was like 20 years ago, and I had 6 people sitting across the table waiting for my answer. That's kind of mind-numbing when you're in an interview like that. Hopefully you're not stuck in an interview like that. But on this, you need to ask yourself, how many different colors of socks are there? So they've thrown a lot of extra data in here that you don't need to solve the answer. The answer is 4. An example, your first pick is white, your second pick is red, third pick is blue, so no pairs yet. And that means when you get to the fourth pick, there's a 100% chance you're going to have a match. So the most is going to be 4 that you ever have to pull out of your drawer. If it was 4 colors, the answer would be 5, and so on. It doesn't matter how many white socks you have or how many red socks or blue socks, different pairs you have. It's the different colors, the number of different colors. People who bought this also bought recommendations seen on Amazon as a result of which algorithm? Ooh, we covered this earlier. Recommendation engine is done with collaborative filtering. Collaborative filtering exploits the behavior of other users and their purchase history in terms of ratings, selection, etc. It makes predictions on what you might interest a person based on the preference of many other users. In this algorithm, features of the items are not known. And we have a nice example here where they took a snapshot of a sales page. It says, for example, suppose X number of people buy a new phone and then also buy tempered glass with it. Next time when a person buys a phone, he'll be recommended to buy tempered glass along with it. And if you remember the vocabulary words we covered earlier, this is the recommendation. This is collaborative. The other word was content-based. So looking at things with similar content versus collaborative, which is similar people. And remember, you're not going to know every vocabulary word, but it also doesn't hurt to get your 3x5 cards out and make yourself a vocabulary stack of cards. Buy an app on your phone for it. SQL query. I remember back in the 90s, it was so important to know SQL query, and only a few people got it. Nowadays, it's just part of your kit. You have to know some basic SQL. So write a basic SQL query to list all orders with customer information. And you can kind of make up your own name for the database. And you can pause it here if you want to write that down on a paper. And let's go ahead and look at this. We have to list all orders with customer information. And so usually you have an order table and a customer table. And you have an order ID, a customer ID, order number, total amount. And then from your customer table you have ID, first name, last name, city, county. And so if we're going to write in SQL with this, we're going to select, keyword there for SQL, selecting, order number, total amount, first name, last name, city, country. So that's the columns we're going to look at. We're going to do that from our order, where we're going to join it with our customer, and we're going to join it on the order customer ID equals the customer ID. So very basic SQL query that's going to return a table of data for us. You are given a data set on cancer detection. You've built a classification model and achieved an accuracy of 96%. Woo, 96%! Why shouldn't you be happy with your model performance? What can you do about it? That's an interesting one because this comes up. That's one of the standard data sets on there is for cancer detection. Cancer detection results in imbalanced data. In an imbalanced data set, accuracy should not be based as a measure of performance because it is important to focus on the remaining 4%, which are the people who were wrongly diagnosed. We talked a little bit about this earlier. You have to know your domain. This is the medical cancer domain versus weather domain. Weather channel, they can get by with 50% wrong. In cancer, you don't want 4% of the people being wrongly diagnosed. Wrong diagnosis is of a major concern because there can be people who have cancer but were not predicted so. In an imbalanced data set, accuracy should not be used as a measurement of performance. Which of the following machine learning algorithm can be used for inputting missing values of both categorical and continuous variables? So we have a couple choices here. We have k-means clustering, we have linear regression, we have the k NN, nearest neighbor, and decision tree. And which of the following machine learning algorithms can be used for inputting missing values of both categorical and continuous variables? Now, certainly you can use some pre-processing to do some of that, but you should have gone with the K nearest neighbor, because it can compute the nearest neighbor, and if it doesn't have the value, it just computes the nearest neighbor based on all the other features. Where when you're dealing with k-means clustering or linear regression, you need to do that in your pre-processing, otherwise it'll crash. Decision trees also, although there's some variance on that too. Can you solve? Another riddle, always fun ones. Given a box of matches and 2 ropes, not necessarily identical, measure a period of 45 minutes. And in this particular setup, the ropes are not uniform in nature, and the rope takes exactly 60 minutes to completely burn out. So each rope takes up to 60 minutes to burn out. And there's actually a couple different solutions to this. But let me go ahead. And one of the things is they're not uniform in nature. So even though they take 60 minutes... Anyways, let's go ahead and see what they did to solve it. And then we can also look at different options. We have 2 ropes, A and B. Light A from both ends and B from one end. Okay? When A is finished burning, we know that 30 minutes have elapsed and B has 30 minutes remaining. Now light the other end of B also, so that the remaining part of B will burn, taking 15 minutes to burn. This we have gotten 30 plus 15 equals 45 minutes. Excellent solution. Mine, which I like, was to take one rope, fold it in 2, so we know it's a half hour. Take the other rope, fold it in 4 places, so we know that that one's 15 minutes, and then you can just connect the 2 and burn it straight across. I think they're trying to cover that by saying they're not regular. The ropes have some irregularities. Maybe that's what they meant by that, is you couldn't do something like that. But that's my solution. Below are the 8 actual values of target variable in the train file. So we have a training file, not to be confused with the train on the tracks. We have 0, 0, 0, 1, 1, 1, 1, 1. What is the entropy of the target variable? We mentioned earlier that you should know your entropy and how to calculate the entropy. What is the entropy of the target variable? So we have a couple options here. We have minus 5 over 8 logarithm of 5 over 8 plus 3 over 8 logarithm of 3 over 8. Okay, let's just see where they got those numbers from. We have 1, which is going to be 5 ones and 3 zeros, and then we have a total of 8. Okay, and then we have the option of 5, which is number of ones, 5 8 logarithm of 5 eighths plus 3 eighths logarithm of 3 eighths. And we also have 3 eighths logarithm of 5 eighths plus 5 eighths logarithm of 3 eighths. And then we kind of reverse those numbers around. And let's see what you're going to get here. Which one did you think it was? You should check the first one. So what is the entropy of the target variable? The key there is the target variable. So we're looking at the target in this case is going to be 1. Usually that's what you're looking for. And so the entropy of that one, we want to subtract out the entropy of the non-target variable. Whoops, I had that backwards. We're looking at 0, so we want to subtract out the 5 eighths from there. So 5 eighths logarithm 5 eighths, or negative 5 eighths logarithm 5 eighths plus 3 eighths logarithm 3 eighths. And they have the hint on the bottom, entropy equals I of P of N. So we have a negative P plus P and N times the logarithm base 2 of P over P plus N minus the N over P plus N times the logarithm 2 of N over P plus N. We want to predict the probability of death from heart disease based on 3 risk factors: age, gender, and blood cholesterol level. What is the most appropriate algorithm for this case? So we have 3 features, and we want to know the predictability of death. Okay, a little morbid there. Choose the right algorithm. Do we want to use logistic regression for this, linear regression, k-means clustering, or the Aporia algorithm? And if you selected logistic regression, then you probably got the right answer. Linear regression, remember, deals with, like, you take your line and draw a line through the data. And of course, you don't necessarily have to use a straight line. There's other means for that. But you're dealing with a lot of numbers. And k-means means we're just going to cluster objects together. With the logistic regression, though, you can mix those things together in buckets. So really, the logistic regression is what you want to use in that model, would be the most apt fit. After studying the behavior of a population, you have identified 4 specific individual types who are valuable to your study. You would like to find all users who are most similar to each individual type. Which algorithm is most appropriate for this study? Certainly, identifying census in just about a lot of different markets is common, so maybe they have a census or whatever it means. But let's take a look at some of the different algorithms we might use on this. We have k-means clustering, linear regression, association rules, and decision trees. And I'll give you a hint. We're looking for grouping people together by similarities, and by 4 different similarities, so very specific. They gave you one of the values, specifically the k value. So k-means clustering would be great for this particular problem. You have run the association rules algorithm on your data set, and the 2 rules, banana apple is associated with grape and apple orange is associated with grape, have been found to be relevant. What else must be true? So this would challenge you to understand association rules. You could picture in this particular one, you're going shopping, and you almost always see somebody who has bananas, they usually have grapes in their bag also. And somebody who has apples usually has grapes in their bags. And then apples and oranges is also associated with grapes. And let's go ahead and take a look at that. And we have a couple different options here. First one is banana, apple, and grape, orange must be a frequent item set. Not so much. Banana, apples, oranges must be relevant rule. Grape is common with banana, apple, must be a relevant rule. And how about grape, apple must be a frequent item set? Let's go back and take a look at that. And we notice that we have bananas, apples to grapes. We have apple, orange to grape. Boy, there's a lot of grapes and a lot of apples in there. And so if you said the last one, grape and apple must be a frequent item set, then you got it correct. Your organization has a website where visitors randomly receive one of 2 coupons. It is also possible that visitors to the website will not receive a coupon. You have been asked to determine if offering a coupon to visitors to your website has any impact on their purchase decision. Which analysis method should you use? And so let's go ahead and start by giving you another hint and give you some limiting your selection. We have a one-way ANOVA, k-means clustering, association rules, and student t-test. So obviously you should know what each one of these means, but let's take a look at the question again. So you want to know which method should you use to see if the coupon's valid for their purchase. Well, we're not clustering and we're not associating things together. We want to know the end result. Student t-test also drawing that little t in boxes and switching them around. There's really only one answer that works in here, and that's the one-way ANOVA.
In this video, we will learn some of the important questions that are often asked in any data science interview. We'll discuss questions related to various aspects of data science such as programming, SQL, mathematics, statistics, linear algebra, and probability. Finally, we'll get an idea about the top machine learning and deep learning interview questions that are frequently asked in interviews. So let's begin. Our first question is, how do you get a list of all the keys in a dictionary? Now in Python for data science, data structures play an important role to store and manipulate data. Dictionary is one such data structure that is declared using curly braces, and they are written as key value pairs. You can see on the screen I have my dictionary called D, and it is assigned using curly braces. Now to get a list of all the keys in a dictionary, we use the .keys function. Now let me take you to my Jupyter notebook. So here is my Jupyter notebook, and you can see my first cell. I have my dictionary defined. So the name of the dictionary is D, and it has the key values. The keys are the country names and the values are the capitals of each country. So I have India and the capital is New Delhi. Then I have USA, the capital is Washington. Similarly, I have Spain, Madrid, and we have Germany and Berlin. Now India, USA, France, Spain, all these are my keys. So to get the keys, I'll use the .keys function. So I'll write my dictionary name, that is D dot, I'll give keys, close the brackets and hit Shift Enter. You can see these are the list of my keys in the dictionary D. Alright. Okay. Now let's move to our next question. So our next question is, what do you mean by list comprehension in Python? So list comprehensions are a short and easy way to define and create new lists based on existing lists. So suppose you want to iterate through a list and find all the even numbers in the list. You can either use a for loop and an if condition as shown here, or you can write a list comprehension to do it in one line of code. You can see this is my list comprehension. So let me show you both the ways. Alright. So here on my Jupyter notebook, let me declare my list as L, equal to, I'll pass in a few numbers, let's say 5, 12, 10, we have 14, 43, 11, 7, 9, and let's say the last element in the list is 6. Alright, let me run this list. Okay, now let me create an empty list, let's say list 1, and let this be an empty list with square brackets. Then I'll use the looping construct to find the even elements in the list. So I'll write a for loop called for item in my list L. I'll give colon, then I'll give my condition if item percentage 2 is equal to 0, which means if the remainder is 0, then I'll append the items to my empty list, which is list 1. So I'll write list 1 dot append, and I'll pass in the argument my item. Now let me go ahead and print my list. I'll write print the final list using a for loop. I'll give colon, give a comma, and pass in my new list name, which is list 1. Now let's run this. You can see using this for loop and the if condition, I have got all the even elements in my list, which was L. You can see my original list, and 12, 10, 14 and 6 were all the even numbers present in my list. Now this task you can do it using list comprehensions as well. So let me show you how to do that. So I have my list defined. Let me just copy this here. I'll paste it, and now I'll create another variable which is list 1. I'll write equal to. Now here using square brackets, I'll write item for item in L, and I'll give my if condition as if item percentage 2 is equal to 0, then I'll print my resultant list. So I'll write print, let's say resultant list using list comprehension. I'll give a colon, then a comma, and I'll pass in my new list, which is list 1. So here whatever is there in my square brackets is called the list comprehension technique. Let me just print this, and I'll get the same result. So these are my even numbers. Alright, so let's move to the third question. So our third question is, given a list of numbers, find the squares of the numbers using the map function in Python. Now the map function calls the specified function for each element of an iterable and returns a result. So let me show you an example to find out squares of a list of numbers using the map function. Okay, so let's first define a function called square. So I'm using my def keyword, and I'll pass in my user defined function name as square, and I'll give my parameter as x, and I want to return the square of x, which is x star x. Alright, and then let me define my list of numbers. So I'll pass in a variable called num, and let's say I want to find the squares of 5 numbers 1, 2, 3, 4, 5. Here I'll pass in another variable which will store the resultant list. So I'll write num underscore squared equal to, here I'll use my map function. So map function takes in two parameters. First it will take in the user defined function name, which is square here, and the list of numbers, which is num. I'll run a for loop. I'll write for, let me just scroll down. I'll write for num in num underscore squared print num. So this is my map function. So it will map all the elements in the list to this function, which is square. I'll just print it. You can see we have the list of squares from the num list, which has the elements 1, 2, 3, 4 and 5. Now moving ahead, coming to our fourth question. The fourth question is on to write a program that will filter out the numbers divisible by 3 from a tuple using the lambda functions. So lambda functions are anonymous functions that are not defined by the def keyword in Python. So here you can see I have the example. So this is a tuple I have defined, and using filter along with the lambda function I am trying to find out the numbers that are divisible by 3, and finally I am printing those numbers. So let's do it on our Jupyter notebook. Alright, so we are on the Jupyter notebook. So first I'll define a tuple. Let's say the variable name is my underscore tup, which stands for my tuple, and using brackets I'll pass in my tuple values. Let's say 5, 12, 10, 18. We have 43, 9, 7, 11 and let's say 6. So you can see these are the numbers present in my tuple. Now I'll create another variable called new tuple, and I'll use my tuple function, and inside the tuple function I'll use the filter function that will filter out only the values that are divisible by 3. And now I'll write my lambda function. So notice this clearly how to use a lambda function. I'll use the keyword lambda, and then I'll pass in a variable x. Now this should consider only those values that are divisible by 3. So I'll write x %3 should be equal to 0, and I'll give my tuple as the variable here. Alright, now we have declared our lambda function. Let's just go ahead and print my new tuple, which is new underscore tup. So here you can see I have my tuple function. Inside the tuple function I'll use my filter function that will filter only those values divisible by 3, and to filter those values I have used my lambda function here and passed in my original tuple, which is my tuple. It's actually my tup, so let's delete the last 2 letters. Let's just go ahead and print this. There you go. You can see we have 12, 18, 9 and 6 are the only numbers that are divisible by 3 from this tuple. Moving to the next question. So our next question is how to create a data frame from a dictionary. Now to create a data frame from a dictionary, you can use the pandas library and the .dataframe function. Now pandas is a popular library in Python that is used for data manipulation. So let me show you how you can create an employee dictionary and then convert that into a data frame. Okay, so here on my Jupyter notebook, let me go ahead and import my pandas library. So I'll write import pandas as pd, and next let's create my employee dictionary. So I'll write emp, which stands for employee, and within curly braces I'll give my key value pairs. So my first column would be the name of the employee, and let's pass in a list of employee names. I'll write Amy. Let's say we have Angela. The third employee's name, let's say we have Samuel, and let Danny be our fourth employee. I'll give a comma. Now the second attribute in our dictionary will be the age of the employee. So my key would be age, and let's create a list of age values. I'm assigning random values to those employee age, 30 and let's say 32. And let's create another variable called city. Here variable refers to the column name of the data frame. Let's say Amy is from New York. Then we have Angela from Chicago. Let's say Samuel is from Boston, and we have Danny from, let's say, Seattle. Okay, so if I run this, I have my employee dictionary created. So if you want to see the dictionary, you can write print and pass the variable name, which is emp here. So this is my dictionary. Now to convert this dictionary into a data frame, you can simply write df, and you can give the pandas library as pd and use the data frame function. So I'll write data frame and I'll pass in my dictionary name, which is emp here. Let's run it. Okay, so we have successfully created our data frame. Now let me just print the data frame. I'll write df. There you go. You can see I have a nice table here, which is actually a data frame. Here you can see the indices, and you can see our column names as name, age and city, and these are the values or the rows. Alright. Now let's see the sixth question we have. So the question is, what is the difference between LOC and ILOC in Python? Now as data scientists, you would often want to analyze a chunk of data and not all the rows in it. So LOC and ILOC functions can help you fetch specific rows and columns from your data frame. LOC function uses row or column labels to select and slice data from a data frame, while ILOC uses integer index to select specific rows and columns. Remember, ILOC stands for index location. I'll use a car data frame to show how LOC and ILOC works. Now on your screens you can see the data frame. So it has a column called brand, which has different brand names such as Ford, there's Hyundai, Tata, Mahindra, there's Maruti, there's Kia Motors. Then we have the year in which the car was manufactured. We have the number of kilometers the car has run. We have the city and the mileage the car gives. So let me first create this data frame on my Jupyter notebook. Okay, so here on my notepad I have my code written to create the data frame, that is car. I'll just copy this code and I'll paste it to this cell. Okay, let me just run it. So if I go on top, you can see we have successfully created our car data frame. Now let me go ahead and print this data frame. So I'll write print, in brackets I'll give my data frame as car. Let me run it. Alright, so here is my data frame. Now suppose you want to see the data from second row till the fifth row for brand and city columns, so you can use the LOC function. So I want my data from the second row till the fifth row for brand and city columns. So let me show you how to do that. So first I'll write my data frame name, that is car, and then I'll give my function as LOC, and within brackets I'll give my row index values. So I'll give from 2 to 5, which is second row to fifth row, and I'll give my column names as brand. I'll give a comma, and my second column which I want is city. So here I'm using the labeled based indexing. Let me just run it. There you go. You can see we have the information available for the second row, third row, fourth row and the fifth row. Alright. Similarly, let's see one more example for index location based slicing. So suppose you want to see the data from second, third and fourth row for year, kilometers and city columns. So for that you can use the ILOC function. So I want the value for second, third and fourth row, and the columns that I want are years, kilometers and the city column. So for that I'll give my data frame name as car dot, this time I'll use ILOC, and within square brackets I'll give my row values and the column values. Now one thing you should notice here is if you use ILOC, Python will exclude the last index, which is the fifth row, and similarly here it will exclude the last index from the column, which is the fourth column. If I run this, you get the desired result. Now let's see another example. Let's say this time I want to print the rows that have mileage less than 25 for brand and city columns. So you can use a print function, and I'll pass in my data frame as car and use LOC. Here I'll give my condition as car, and I want my condition that is mileage should be less than 25, and I want the brand name. So I'll use a square bracket and give my brand column, and I also want the city column. Okay, let me close it. If you run this, now these are the brand names Renault, Tata and Kia, which have mileage less than 25. Let me just verify this. You can see all these values are less than 25. Similarly, you can use the ILOC function as well. I can write print, I'll give car dot ILOC, within square brackets I'll give car, and my condition column is mileage. Now this should be less than 25. I'll use dot values, and then I'll give my column numbers as 0, 2. Let me run it. There you go. The same result, we have got it using ILOC function this time. And you can see the columns were 0, 2, which means we wanted the first column, which is brand, and the second column, which was kilometers. Alright. Now moving to our 7th question in the list of questions that we have. The question is, how is list.append different from list.extend? Now list.append adds its arguments as a single element to the end of the list. The length of the list increases by 1 here. And list.extend iterates over its arguments and adds each element to the list. The length of the list increases by the number of elements in its arguments. So let me show you the difference on my Jupyter notebook. Okay, so let's create a list called list1 equal to, I'll create a list, let's say it has some country names like India, then we have USA, and I'll consider one more country, let's say Canada. Okay, now let me print the length of this list also. I'll use the length function for that. Alright, now let me append one more list. So I'll use the append function. I'll write list1 dot append, and within brackets I'll give my new list which has two more country names, let's say France and Spain. Okay, and here let me print list 1, and let's also print the length of the list again. I'll use the length function and my list name, which is list 1. So just mark we are using append here. Let me run this. There you go. So here you can see my original list had 3 elements, hence the length is 3. Now when I appended this new list which had 2 elements, France and Spain, our size increased by 1 and the length of the new list is 4. Now let me just copy this code, and instead of append let me write extend, so that we can see the difference between append and extend. I'll just scroll down, run it. Here you can see our original list had 3 elements, but after we extended our list with 2 more elements, the length of the new list became 5. So these are the 5 elements in the list, and here you can see there were total 4 elements in the list when we appended the new list. Okay, now moving to our 8th question. Suppose you have a car dataset which has a mileage column. You need to create a new field called MLG that will accept 2 values. If mileage is less than 25, then the value should be low MLG, and if the mileage is greater than or equal to 25, then the mileage should be high MLG, or the value should be high MLG. Now while analyzing data, data scientists often need to create extra columns in the data frame to add more values that will help you make your data analysis more efficient. So this question is related to one such instance or one such idea. So here you can see my data set. It has the brand name, year, kilometers, city, and the mileage column. Now if mileage is less than 25, I'll add the value low MLG to my new column. Else, if mileage is greater than or equal to 25, I'll add high MLG to my new column. So here you can see my final output. Wherever the mileage is less than 25, it should print low MLG, else it should print high MLG. And now let's do this on my Jupyter notebook. So we'll use lambda functions that we learned earlier to perform this task. I'll write a function, let's say f is equal to, you can call this as a function or a variable. I'll give the keyword lambda and use x as my parameter. Now x should be low MLG if x is less than 25, which is mileage here, else if it's not less than 25, it should return high MLG. Now what I'll do is I'll give my data frame as car and I'll create my new column, that is MLG. Then I'll write equal to car dot, I'll give my column name from the original data frame, which is mileage, and I use my apply function and pass in the variable f. Now let's just print this data frame. If I run it, you can see the output here. We have created a new column which is MLG. You can see our new column name was MLG, and these are the results. So for Renault, Tata and Kia, for the last 3 rows, since the mileage is less than 25, it returned low MLG. For the remaining, it gave us high MLG. Now moving to the 9th question. So this is our next question. We want to create a 4x4 matrix and find the sum of all the diagonal elements in the matrix. Data scientists often work with multiple dimensional arrays or multi-dimensional arrays and matrices to build models. This question is related to an operation on a 4x4 matrix. So first, we need to create an array which will be a Numpy array of 4x4 shape, and then we'll see how to calculate the diagonal elements. or the sum of the diagonal elements. So I am on my Jupyter notebook. First, let's import the Numpy library. So I'll write import Numpy or NumPy as np. Let me run it. Okay. Now I'll create my 4x4 matrix. So I'll write m is equal to np dot array, and I'll create my 4x4 matrix. Let's say the values are 1, 2, 3, 4 in the first row, and in the second row I'll pass 5, 6, 7, 8. In the third row we'll have 9, 10 and 11, also 12, and finally we'll have 13, 14, 15 and 16 in the fourth row. I'll just run it. Now if I print m, you can see this is a 4x4 matrix. So this is one way of creating a 4x4 matrix, which is a bit tedious and lengthy. Instead of that, you can also use arange function. So if I write m is equal to np dot arange function, and here I'll give my values starting from 1 till 17. So this will actually exclude 17 and take from 1 to 16, and I'll give my shape as 4, 4. Let me print it. There you go. It has printed the exact same matrix that we saw above. Alright. Now to print the diagonal elements, we'll use the diagonal function. So I'll write print m dot diagonal. Let me just run it. So 1, 6, 11 and 16 are my diagonal elements. You can see this matrix. 1, 6, 11 and 16 are my diagonal elements. Now to print the sum of all the diagonal elements, I'll use the sum function. So I'll write m dot diagonal. Along with that, I'll pass my sum function. If I run it, so the sum of 1, 6, 11 and 16 is 34. Okay, so coming to the last question on this interesting session on programming interview questions for data scientists. Our question is, given a vehicle data frame, find the average and maximum mileage of the vehicles using pandas. So here, data scientists use statistical measures to analyze their data, so it is important to have knowledge of the statistical functions in Python. Here is my vehicle data set, and for each brand of vehicle we want to find the average and the maximum mileage. So let me show you how to do it. Okay, so here on the notepad I have my code written to create the vehicle data frame. I'll just copy it and paste it on this cell. You can see we have the brand column, the year column, kilometers, city, mileage. Here you can see the different brand of vehicles. Let me just create this data frame first, and let me go ahead and print the vehicle data frame. So I'll write vehicle and run it. So here is the data frame. Now I want to find the average and maximum mileage for each of the brands. So for this we'll use the group by function and the aggregate function that is available in the pandas library of Python. So let me show you how to do it. I'll give a variable called result, and then I'll use my data frame name as vehicle, followed by the group by function. I'll write group by, and since I want to check for all the brands, so I'll group all the brand of vehicles. Then I'll use an aggregate function which is agg, and within curly braces I'll give my column as mileage, I'll give a colon and pass in mean, which is for average, and I'll use max to find the maximum mileage. Now let's print it. I'll write print. I'll give a message as the average and maximum mileage of vehicles. Let me just print the result. I'll run it. You can see it has resulted in an error. The reason is in vehicle the V is capital. If I run it, there you go. Here you can see on the left we have the brand names. We have Hyundai, there's Maruti and Tata, because those were the only 3 brand of vehicles we had. And for each brand you can see the mean mileage and the maximum mileage. For Maruti it was 26.33 and the maximum mileage is 28. Similarly you can see for Tata vehicle as well. SQL is a widely used language for querying data from databases. It allows you to store, retrieve, manipulate and update data present in the form of rows and columns. Data scientists often work with structured data that is stored in MySQL databases, Microsoft SQL servers, Oracle databases, or even NoSQL databases such as MongoDB. Today, we will look at a variety of SQL questions. We'll be using the MySQL database for our demo. Throughout the video, we'll be using MySQL Workbench and the MySQL command line to solve the SQL queries. Let me show you the database that we will be using for this demo and the tables we are going to use. Okay, so here I am on my SQL Workbench, and below you can see I have a local instance created. I'll just click on it. Now it's asking me to enter the password. I'll give my password and hit OK. Now this will take me to the SQL editor. Now this is the SQL Workbench. So let me first create a new SQL query file. Alright, so first and foremost, let me show you the databases we have. For that, I'll use the command show databases. If I hit tab, it will autocomplete. I'll give a semicolon and hit Control Enter to run this. There you go. Here you can see the list of databases that we already have, and from the list of databases we are going to use the SQL_IQ database. So to use this database, I'll write the command use SQL_IQ. I'll give a semicolon. I'll select this and I'll click on this execute button. If I run this, you can see now I'm using SQL_IQ database. Now if you want to see all the tables present in SQL_IQ database, we'll use the following command. So I'll write show tables. Now this will list all the tables present inside SQL_IQ database. If I run it, you can see here it has executed successfully and it has given us 7 rows, which means we have a total of 7 tables in this database. You can see there's an author table, there's a table called books, we have customers, email, employee, players and weather table. So all these tables we are going to use in the course of this video. Now if you want to have a look at the data present in one of the tables, you can just use the select statement. So I'll write select star from, let's say I want to see the data present inside the employee table, so I'll write employee. So this is my table name. I give a semicolon. If I select this, hit the execute button, there you go. It shows me that it has returned 6 rows, and these are the column names. We have the name of the employee, the age of the employee, we have the employee's salary and the employee ID. So there are total 6 employees in the table. Alright, now I can do the same operations on my SQL command line as well. Now let me open the command line first. Okay, so this is the MySQL command line client. It is asking me to enter the password, so I'll give my password first. Alright, now here you can see I have come inside MySQL. Now the operations that we performed on the MySQL workbench, the same operations can be performed on the command line as well. So I'll write use SQL underscore IQ. I'll hit enter. You can see the message, it says database changed. Now if you want to display the tables present inside this database, I can use show tables command. I have to give a semicolon and hit enter. There you go. You can see the list of tables we have inside the database. Now if you want to have a look at the content of one of the tables, I can just write select star from, let's say, players. If I give a semicolon, hit enter, you can see the rows and columns in the dataset. Alright, and with that, let's move on to our first question on SQL. Okay, so our question is, what is the difference between where and having clause in SQL? So where clause is used to filter the records based on the specified condition, while the having clause is used to filter the records from groups based on specified conditions. You need not worry, we'll do the demo for where and having clause using the employee table. So where clause cannot have aggregate functions such as count, sum, min or maximum functions. Having clause can operate on aggregate functions. Now where clause is implemented on rows, while having clause is implemented on columns. Now let me show you an example of how a where clause is different from an having clause. So I'll take you to my MySQL workbench. Alright, so we are on the SQL workbench. So suppose I want to get the records of the employees whose age is greater than 30. For this, I can use a where clause. So since I want to get the employees whose age is greater than 30, I'll use a where clause. I'll write my SQL query as select star from employee where I'll write age is greater than 30. If I give a semicolon and run this, it will return all the employees whose age is greater than 30. You can see 36, 36 and 35. These are the employees whose age is greater than 30. Now I have intentionally kept some duplicate rows because we are going to use this in our next questions. Again, I can also do the same task using the having clause. So let me just copy this query. I'll paste it here. Now instead of where, I'll write having. So you will see that even this query will return the same result. If I run it, you can see it gives me the same result. Now let's say I want to find all the records where the count of age for all the employees is greater than 1. In this case, I can't use a where clause. It will throw me an error since where clause cannot be used with aggregate functions. So let's try using an aggregate function in the where clause. So I'll write select star from employee where count of age is greater than 1. So the idea is to find all the records where the count of age for all the employees is greater than 1. So if I run this SQL query, you can see it has given me an error. It says invalid use of group function. Now instead, we need to use a having clause along with the group by clause to solve the problem. So I'll group all the age values and then find the count of each age value. So let me just paste this, and here I'll edit my SQL query. Instead of where, I'll write having, and just after the table name I'll use the group by clause. So I'll write group by age. Now let's run it. Alright, you can see our SQL query has returned only those employees whose age occurs more than once. Now let me just verify this. If I run my employee table, you can see Angela's age, that is 36, has been repeated twice. You can see Angela here as well, and similarly we have Mike also repeated twice. Alright. Now let's see the second question. Now this is a multiple choice question where you need to answer the correct SQL query based on the question. So the question is, the correct SQL query to select all the records of employees with ARI in their names is. So we have a list of 4 options given, and out of that you need to find the correct option. Now the answer to this question is this. So if you write select star from the table name, which is employee here, where name like, then if you give this condition, it will return all the records where employees have ARI in their names. Now like is an operator in SQL that is used to search a specified pattern. So here our pattern is we want all those employees who have ARI in their names. The first percentage means that the name can have any number of letters in the beginning, followed by ARI in the middle, and the last percentage means the name can have any number of letters in the end. So let's do this on our MySQL workbench. Let me first display all the employees in the table. So I'll write select star from employee. I'll run this. If you see my table, I have one employee who has ARI in its name, and that person is Karin. I now want to get this particular record. So what I can do is I'll write a select query, select star from employee where name, then I'll use the like operator where name like, within double quotes I'll give percentage ARI, again a percentage, close the double quotes and give a semicolon. If I run this, you can see my SQL query will return only Karin. Now let's do one more example. Suppose I want to find the employee whose name starts with D. So the way to do is something similar to what we saw just now. So here in my condition, I'll just replace this with D. This means the name should start with D, and after that it can contain any number of letters. Now let's run it. There you go. So our table had one employee called Danny whose name started with D. Now moving to our third question. So the question is, we want to write a query to find the players with the least number of goals. So there are 2 methods to do it. One where you can use a subquery, and the other method to use the limit operator. So let me show you both the methods. First, let me go ahead and display all the tables present in my database, that is SQL or SQL_IQ. Alright, if I scroll down, you can see we have a table called players. So I'm going to use the players table to find the player with the least number of goals. So let me show you the first method, that is by using a subquery. So I'll write select star from my table name, which is players, where goals equal to, and in this I'll write my subquery using brackets. So I'll select minimum goals from the table, that is players. I'll close the bracket and then I'll give a semicolon. Now let me go ahead and run this. You can see Matt was the player from Scotland who scored the least number of goals, that is 3. Now let's break it down. So what we did was, First, my SQL query found out what was the minimum goal scored by a player. So if I run this, you will see it will return me 3. So 3 was the least number of goals scored by one of the players. Now in my outer query, what SQL did was it searched for those goals where the value was equal to 3. So we wrote select star from players where goals equal to 3. Hence, if I run this, you will find the player who scored only 3 goals, and that player is Matt. Alright. Now the other way to do is using the limit operator. So this is more simpler than the previous method. I can write select star from players, order by goals. Now let me first run this SQL statement. If I run this, you can see we have ordered this in ascending order. So the person who has scored the least number of goals appears at the top, and the person with the player with the highest number of goals appears at the bottom. And from this table I only want the first row, and for that I can use the limit operator. So if I write limit 1, it will display only the first row. If I run it, you can see it shows me only the record for Matt. Moving ahead, now let's see the fourth question in our list. The question is, write the SQL query to find the player with the second highest number of goals. Now again, there are two methods to do it. One is by using limit and offset, and the other method is to use a subquery. So let's see both the methods. I'll first write my SQL query using limit and offset. So my query will be select star from players, order by goals, descending. Let me just run this. Alright, so here you can see my table has been ordered in descending order of goals. So Anthony has scored the most number of goals, then comes Daniel, followed by Sam, and at the end we have Matt, who scored the least number of goals. Now out of this, I want the player who scored the second highest number of goals, which is Daniel. So I want my SQL query to return this row that has player ID 103, name is Daniel, country is England, and goals is 7. For that, MySQL has two features. So I can use limit 1 followed by offset 1. So what this query does is it will offset one row, that is, it is going to offset the first row, or it is going to skip the first row and then print only the second row, because I have set my limit to 1. So let me just run it. You will see we get the desired result. The player name is Daniel and the number of goals scored is 7. Now the other method to do is using a subquery. Now let me write my subquery. First I'll write my outer query, which is select star from, and here I'll write my subquery select star from players, order by my column name, which is goals, in descending order. Here I'll limit it to 2. Then I'll give my alias name as T. Then I'll use order by goals limit 1. Let me just run it first. If I run this, you see here I get the same result. Now let's first break it down. I'm going to run this subquery first. So here I have select star from players, order by goals, descending, and limit is 2. Let me just run it. So the selected SQL query returns the first two rows ordered by goals, and if you see here clearly, we have again ordered the value returned in ascending order, which means from this table, if I order this table in ascending order, Daniel should appear first, and out of that I'm limiting my result to 1, so it will print only Daniel. If I run this again, you can see I have the desired output. Now let's check the fifth question in our list. Given the below email table, write a SQL query to find the distinct domain names from the email column. So if you consider this as my email table, the domain names are gmail.com, yahoo.in, and we have hotmail.com. These are the distinct domain names. Now to solve this task, again we have two methods. Either you can use the substring underscore index function, or you can use the substring function. Now the substring underscore index function returns a substring of a given string before a specified number of delimiters. So let me first use the first method. Okay, so here on my SQL workbench, I'll write select. I'll use the keyword that is distinct. Then I'll use my function, which is substring underscore index. Here substring underscore index will take three parameters. The first is the original column name, which is email, followed by the delimiter I'm looking for, that is @. So I'll put @ with single quotes since it is a text or a character, and then I'll give the number of times to search for the delimiter. Here it is going to be -1. So you can either give a positive value or a negative value. If it is a positive number, then this function will return all to the left of the delimiter. If it is a negative number, the function returns all to the right of the delimiter. Alright. And then I'll give an alias name as, say, domain name from my table, that is email. If I run this, you can see I have the list of all unique domain names or distinct domain names that we saw in our table. This is one of the ways. The other way is to use the substring function. Now the substring function extracts a substring from a string starting at any position. So let me write my SQL query. I'll write select distinct. I'll then give my function as substring. Here substring will take in two parameters. The first parameter is the column name, which is email ID here. So I'll write email. I'll give a comma. Next, I want to find my delimiter. So for that, I'm going to use another function called locate. And here I want to locate the index position of @. So I want to give my delimiter as @ followed by the column name, which is email. And then I want to fetch everything after the delimiter, and for that I'm giving +1. Again, let me give a domain name as the alias name from email. If I run this, you will see we'll get all the unique domain names: Gmail, yahoo.in, and hotmail.com. So these were the two ways to solve the same problem. Now moving ahead, let's look at our sixth question. So our question is, write the SQL query to find duplicate records from a table without using a temporary table. Now, one of the other variants of this question is to delete all the duplicate records from a table without using a temporary table. Now to solve such queries, you can use the group by and the having clause. Let's look at how to do it. So here on my SQL workbench, I'll write my select query as select star, and then I want to count all the duplicate values. Let me give it an alias name as frequency from my table name, which is employee here, and then I want to group by name having count star greater than 1. Let me just run it. Alright, you can see it has returned me 2 rows. The name is Angela and Mike, and the frequency is 2. Let me just verify this to see all the repeated records that were present in my employee table. So I'll write select star from employee. If I run this and scroll down here, you can see Angela is present here as well as at the bottom. Similarly, we have Mike present twice in the table, and hence our SQL query returned only Angela and Mike because they were repeated twice. You can see the frequency here. So let's now look at our 7th question. Given the below employee table, I want to write a query to find all the even and odd records from the table. So as you can see, there are 2 ways to do it. One is to use a subquery, and another you can use the mod function. So let me show you both the ways. Alright, so let me run this SQL query to see all the values present in the employee table. So if you see, the last column, which is the employee ID column, has all the employee IDs as unique values. So I'm going to use this in my where condition. So to find out all the even records, I'll write my SQL query something like this. I'll write select star from employee, which is my table name, where employee ID, then I'm going to give my in operator, and inside the in operator I'm going to write my subquery, which is select employee ID from employee, where employee ID %2 is equal to 0. This means wherever my employee ID is divisible by 2, it will return only those records. So let me just run it. There you go. So here we have easily fetched only the even records from the table. Similarly, if you want to get only the odd records from the table, you can use the mod function also. So I'll write select star from employee, where here I'm using the mod function, mod empid comma 2 is not equal to 0. So I'll use the exclamation mark is equal to 0. So if I run this, it will return only the odd employee IDs. You can see it here. So those were the 2 ways in which you can fetch the even and odd records from the table. Now let's see our 8th question. So here is the question. Below is the customer table. Write a query to get the first purchase of each customer. Now if you look at the table, there are 3 customer IDs, 101, 102 and 103. Now customer 101 made its first purchase on 2nd October 2018, which is this one, and customer 102 made its first purchase on 5th of October 2018. And since we have just one record for customer ID 103, so this is going to be his or her first purchase. So I want to return 101 phone, 102 tablet and 103 books. To do this, we are going to use an inner join. If you can see, I have used an inner join and I have also used a subquery. Let's write this query on my SQL workbench. Okay, so this query is going to be a little complicated. If you have any questions, then please put it in the chat section. We'll be happy to help you. So I'll start with select. I'm going to take an alias name as t dot. I'll write cust underscore id comma t dot purchased at comma. The next field I'm going to select is t dot item from customers as T. Next, I'm going to write my inner join, and inside the inner join I'll write my subquery, which is going to be select customer ID, comma, I'm going to take the minimum value from the purchased at column, which is my date column. Close this. I'll give another alias as min underscore purchased underscore at from my table name is customers. Then I'm going to group it by 1. Here 1 means the first column that you have put in the select statement, which is customer ID. So I'm grouping by customer ID. I close the bracket, and everything I'm going to give an alias name as T1. Now I'm going to join on T dot customer ID is equal to T1 dot customer ID, and my next condition would be T dot purchased at is equal to T1 dot min underscore purchased underscore at. I'll give a semicolon. I would request you to go through this SQL query in a detailed manner so that you understand it line by line. Let me just run it now. If I run it, okay, it has thrown me an error which says table SQL underscore IQ customer does not exist. The reason is my table name is customers. Alright, so let me run it once again. Okay, so there's one more error. It says unknown column purchases at. So we had made a spelling mistake here. It should be purchased at. Now let's try and run it. Alright, there you go. So for customer ID 101, the first purchase was made on 2nd of October 2018. Likewise, for customer ID 103, the first purchase was made on 5th of October. And similarly for customer ID 102, the first purchase was made on 5th of October again. Now moving to the 9th question. So here we have a weather table. We want to write an SQL query to find all the date IDs with higher temperature compared to its previous dates. So if you see, we have a date ID column, we have the date and the temperature. Using this table, I want to find those IDs with higher temperature compared to its previous dates. So if you look for date ID 1, the temperature is 32. For date ID 2, the temperature is 31. For date ID 3, the temperature is 30.8. Now if you clearly notice, for date ID 4, the temperature is 31.5, which is actually higher than the previous date ID, which is 30.8. Similarly, for date ID 5, the temperature is 33, which is again higher than the previous date, which is 31.5. Now if you look at the date values, they start from 10th of March till 15th of March 2020. Now to solve this query, we are going to use SQL joins again, and I'm going to use a function called to_days. Now MySQL to_days function returns the number of days between a given date and year 0. So let's go ahead and write this SQL query. Alright, so first let me select all the rows from the temperature table which we are going to use for this particular question. I'll run it. Alright, there's some error. Actually the name of the table is weather and not temperature, so I'll write weather. Let me run it. Okay, so here you can see these are all the rows present in the weather table, and as I explained, I want to return only the date ID 4 and this date ID which is 5. Now one thing I want to make it clear here, that this date ID should actually be 6, so there was a mistake while creating the table. So please consider this date ID as 6 and not 5. So I want to return date ID 4 and date ID 5. Alright, so let me go ahead and write my SQL query. So I'll write select, I'll write a dot date underscore ID from weather as A, comma, I'll join weather as B, where A dot temperature is greater than B dot temperature, and I'll give my condition, and I'll use the function to underscore days and give my value a dot date underscore val is equal to, I'll use the function again, to underscore days, b dot date underscore val plus 1. Now I would like to know from our viewers, why have we used plus 1 in the where condition? So please put your comments in the chat section. Let me just run it. There you go. So here you can see my SQL query has returned the date ID 4 and 5, which means these are the date IDs where the temperature was higher compared to the previous dates. Alright. Now coming to the last question on this interesting session on SQL interview questions for data scientists. So there are two tables. One is the authors table and the other is the books table. I want to write an SQL query to find the second highest author who sold the most number of books. Now this is going to be my SQL query. Again, we are going to use joins on both tables author and books along with limit and offset operators. So let me show you how to do it. So first I'm going to join my author table and the book table. So I'll write select a dot author underscore name, comma, I'm going to find the sum of copies sold from the books table. So I am giving my alias name as b dot copies underscore sold, which is my table name. I'll give an alias as sum underscore sold from author as A, join books as B on, I'll write b dot book underscore name is equal to a dot book underscore name. Now I'm using book underscore name as my criteria because book underscore name is the common column to both the tables. Then I'll use a group by clause. I'll write group by a dot author name. Then again I'm going to use an order by clause. I'll write order by sum underscore sold, and I am going to order it in descending order, so I'll write DESC. I'll set my limit as 1 and offset as 1. If I run this, you will find that my SQL query has thrown an error. The reason is we have used a column called bull underscore name, so it should be book underscore name. There was an error here. Let me run it again. Okay, there was another small error. This should be sum underscore sold. Let's run it. There you go. So my SQL query has returned author 3 because author 3 sold the second highest number of books. Now let me just remove the last few lines in the script. Let me just run it now. If I run this, you can see author 1 sold the highest number of books, followed by author 3 who sold the second highest number of books, and then it was author 2 who sold the least number of books. So if I write limit 1 and offset 1, what this line of code will do is it will skip the first row and print the next row. So let's just run it. And you can see it has returned me the author who sold the second highest number of books. In this video, we'll be discussing some of the top mathematics interview questions for data science. These questions are based on various topics in mathematics such as statistics, probability, and linear algebra. So let's begin with our first question. The first question we have is, what is normal distribution? Now, normal distribution is a probability distribution that is used to check how your data is distributed. Your data could be spread out to the left or to the right, but in many cases, the data tends to be around a central value with no bias left or right, as you can see on your screens. Now, this is called a normal distribution where half of the points are to the left and another half of the points are to the right of the center. Now, such a distribution contributes to 68% of the data falling within one standard deviation of the mean. Then we have 95% of the data falls within second standard deviation of the mean. So if you add up 13.6% and the 68% plus 13.6%, this will result to 95% of data falling within two standard deviations of the mean. And finally, we have close to 99.7% of the data falling within three standard deviations of the mean. So this is what a normal distribution is all about. Now moving on to the next question. So what are the different measures that are used to summarize a distribution? Now, to get more idea about the data and summarize a distribution, you can use three types of statistical measures. The first, we have central tendency measures, then we have variation measures, and finally we have shape measures. Now, under central tendency measures, we have mean, median, and mode. Now, the mean is the most frequently used measure of central tendency in a data set. Let me take you to the Wikipedia page and explain you what mean exactly is. Okay. So here you can see on the Wikipedia page, it has the formula to calculate the mean of a distribution. So this is basically the summation of all the data points divided by the total number of data points. So here you can see an example. We want to find the arithmetic mean of 5 values, which are 4, 36. We'll pick the fourth element from our ordered set of points, that is 6 here, and hence 6 is the median for this ordered set of points. Now if you have an even number of observations, as you can see here, total we have 8 observations. Now the median becomes xn by 2 plus xn by 2 plus 1 divided by 2. So your median becomes the mean of the middle two numbers, that is 4 plus 5 by 2, which is 4.5. Alright. Now the next statistical measure we have under central tendency is called the mode. So the mode is the most frequently occurring value in a set of data points. So here you can see an example. We have a set of data points 6, 3, 9, 6, 6, 5, 9, 3. So your mode is going to be 6 here, since 6 is occurring thrice in the set of data points. Okay. Now under variation measures, we have variance, standard deviation, and interquartile range. So first look at what variance is. So variance is the average of the squared differences from the mean. Now this is the formula for variance. You can see xi represents the individual set of data points and mu represents the average value. So mu is nothing but the summation of all the data points divided by the total number of data points. So this is your formula for variance. Next we have standard deviation. So standard deviation is a measure of the amount of variation or dispersion of a set of values. A low standard deviation suggests that the values tend to be close to the mean, while a high standard deviation suggests that the values are very spread out. Now here you can see the formula for variance. Now this is denoted by sigma, and Your standard deviation is nothing but the square root of variance. So here you can see the formula for variance. You have xi minus your mu square, which is the mean of all the data points, divided by n. Then we have the interquartile range, which is also known as IQR. So IQR is a measure of variability based on dividing a data set into quartiles. So an interquartile range measures where the bulk of values lie. So the formula for IQR is Q3, which is the third quartile minus the first quartile. So here you can see we have a list of data points. Then we are ordering the data points first, and then we cut the list into quarters. So first you have the Q1, then you have Q2, and finally you have Q3. So for these set of data points, your IQR is going to be 7 minus 4, that is 3. Then we have shape measures. So under shape measures we have skewness and kurtosis. So skewness is a measure of symmetry. Your distribution is symmetric if it looks the same to the left and the right of a center point. Now they are majorly of two types. One is called negative skew, or which is also known as left skew. Then we have positive skewed or right skewed. And finally we have kurtosis. So kurtosis is a measure of the tailedness of a probability distribution. It defines how heavily the tails of a distribution differ from the tails of a normal distribution. So if you consider these distributions, the kurtosis will calculate the tailedness, which is actually these areas of a distribution. Now let's look at a third question. So the question is, create a sparse matrix in Python. Now in numerical analysis, a sparse matrix or a sparse array is a matrix in which most of the elements are 0. Now there are multiple ways to create a sparse matrix. I'll show you two ways to create a sparse matrix. So let me take you to my Jupyter notebook, where I'll create a matrix first, and then we'll see how to create sparse matrix out of it. So I am on my Jupyter notebook here. First let me import the necessary libraries. So first I am going to import Numpy as np, and then from scipy we'll import sparse. I'll run this cell. Okay. Next, let me go ahead and create a matrix. I'll use the np.array function, and within this function I'll create a 3 cross 3 matrix, and I'll assign the elements. So my first row will have 1 2 3. Next we'll have 4 5 6. Then we'll have 7 8 and 9. Alright, let me run this cell. Okay, now let me go ahead and print my matrix. So I'll use the print function, and let's say I'll pass in a message that is original matrix, comma, and then pass in my variable name, that is matrix. Let's run it. So here you can see I have my original matrix. It is a 3 cross 3 matrix and has 9 elements in it. First, let's see how using dictionary of keys you can create a sparse matrix. So for that, I'll write the print statement, and then I'm going to use a function which is called doc, that stands for dictionary of keys underscore matrix, and I'll pass in my variable name, which is my original matrix. So if I run this, you can see I have got my dictionary of keys sparse matrix. Next, I'll show you how using diagonal storage based you can create a sparse. For that I am going to use another function, that is sparse.dia, which stands for diagonal underscore matrix, and within this function I'll pass in my original matrix variable name. If I run this, you can see we have created diagonal storage based sparse matrix. Alright, now moving to the next question. So given below, is a matrix. Now we need to find the inverse of this matrix. Now the inverse of a square matrix A, which is sometimes called as a reciprocal matrix, is a matrix A inverse such that the dot product of A and A inverse is always I, which is an identity matrix. Now in Numpy we have a function which you can see here, that is np.linalg.inv, that helps you find the inverse of a matrix. Let me show you on the Jupyter notebook. First, let me print my original matrix. Alright, now here I'll use the function with mint, that is np.linalg.inv, which stands for inverse, and then pass me my variable name, that is matrix. If I run this, you can see I've got the inverse of my original matrix. Now moving to our fifth question. So this question is related to probability. You call 2 Uber X and 3 lifts. If the time that each takes to reach you is IID, what is the probability that all the lifts arrive first? Next, we want to find what is the probability that all the Uber X arrive first. Now this is fairly a simple question. First, let's look at all the lifts arrive first. Then first we need to find the probability that the first car is a lift, which is going to be 3 by 5, since we have 3 lifts and total we have 5 vehicles. Next, we want to find the probability that the second car is a lift, which is going to be 2 by 4. Third, we need to find the probability that the third car is also a lift, which is 1 by 3. Now arrive first is going to be the multiplication of the product of the above 3 probabilities, that is 3 by 5 into 2 by 4 into 1 by 3, which is nothing but 1 by 10. Next, let's say you want to find for all the Ubers that arrive first. So you need to find the probability that the first car is Uber, which is nothing but 2 by 5, since we have 2 Ubers. Next, the probability that the second car is an Uber is going to be 1 by 4. So the total probability that all the Ubers arrive first is going to be the product of 2 by 5 and 1 by 4, which is also 1 by 10. Now moving to the sixth question, the mean, median and mode of a distribution are 30, 25 and 20. We need to determine if the distribution plot will be positively skewed or negatively skewed. So you can see from the distribution graph, the mean is to the right, median to the middle and mode to the left. So since the value of mode is less than the mean and median, the data will be positively skewed. And similarly, the skewness of the distribution is on the left if the mean value is less than the median and the mode occurs at the highest frequency of the distribution. Now the next question we have is, what are covariance and correlation? So covariance and correlation are measures that help you understand the relationship between two continuous variables. So covariance tells the direction of the linear relationship between two random variables. The direction means if the variables are directly proportional or inversely proportional to each other. So increasing the value of one variable might have a positive or a negative impact on the value of the other variable. Now covariance can take any value between minus infinity and plus infinity. So below you can see the formula to calculate the covariance. So you have summation xi minus x bar or x dash here represents the mean, xi represents the individual points, then this is multiplied by yi minus y dash or the mean of y divided by the total number of observations. Next, we have correlation. So correlation explains the change in one variable leads to how much proportion changes in the second variable. Correlation tells how strongly two random variables are related to each other. It takes values between -1 and +1. A negative correlation means they are inversely proportional to each other. A positive correlation means they are directly proportional to each other. If the correlation coefficient is 0, then there is no linear relationship between the variables. So here below you can see the formula to calculate the correlation. Now moving to the eighth question. So what are the sampling methods used in data science? Now, sampling is a statistical technique that is used to select, manipulate, and analyze a subset of data points and find patterns and trends in the large dataset being examined. Now, there are two types of sampling methods. We have probability sampling and non-probability sampling. Now, under probability sampling, we have something called as random sampling. So in random sampling, every individual is chosen entirely by chance and each member of the population has an equal chance of being selected. Then we have stratified sampling. So in stratified sampling, subsets of the population are created based on a common factor and samples are randomly collected from each other. Now talking about systematic sampling. So in systematic sampling, a sample is created by setting an interval at which to extract data from the larger population. An example could be selecting every fifth row in a spreadsheet of 100 items and creating a sample size of 20 rows for analysis. And finally, under probability sampling, we have cluster sampling. So in a cluster sampling, subgroups of the population are used as the sampling unit rather than individuals. So the population is divided into clusters and a whole cluster is randomly selected to be included in the analysis. Now let's look at the sampling methods that are present under non-probability sampling. So first we have convenience sampling. So for convenience sampling, the samples are selected based on the availability. So this method is used when the availability of samples is rare and costly. So based on convenience, samples are selected. Second, we have quota sampling. So quota sampling depends on some preset standard. The proportion of characteristics in sample should be the same as the population. Next, we have purposive sampling. It is also known as judgmental sampling. You select members of sampling on the basis of the objective of the study. It is very useful when you want to reach a particular or targeted sample quickly. Finally, we have snowball sampling. So the snowball sampling technique is used in situations where the population is completely unknown and rare. Now coming to the 9th question in our list. So explain what p-value tells about statistical significance. So p-value is a statistical test that is used in hypothesis testing. It helps you to decide whether to accept or reject the null hypothesis. The null hypothesis, represented as H0, is a commonly accepted fact. It is the opposite of alternative hypothesis. Researchers and scientists work to reject or disapprove the null hypothesis. They come up with an alternative hypothesis that they think explains a phenomenon and they work to reject the null hypothesis. For example, null hypothesis or H0 could be the world is flat and an alternative hypothesis could be the world is round. So lower the p-value, the greater the statistical significance of the observed difference. Now the p-value is just one piece of information you can use when deciding if your null hypothesis is true or not. The p-value lies between 0 and 1, as you can see here. The threshold for p is set to 0.05. When the value is below 0.05, the null hypothesis is rejected. Now coming to the final question in our list of mathematics interview questions for data science. So the question is, what do you understand by type 1 versus type 2 error? Now in statistical theory, the statistical error is an integral part of hypothesis testing. In statistical hypothesis testing, no test is ever 100% certain. That's because we rely on probabilities to experiment. Even though hypothesis tests are meant to be reliable, there are two types. So type 1 error occurs when the null hypothesis is true and we reject it. It is also known as a false positive finding or conclusion. An example could be an innocent person is convicted. And type 2 error occurs when the null hypothesis is false and we accept it. It is also known as false negative finding or conclusion. An example could be a guilty person is not convicted. So here you can see we have a reality where your null hypothesis is true and here we have the null hypothesis is false, and this is where the type 1 error lies. So this can also be represented as false positive, where the null hypothesis is true and we reject it, and this could be false negative, where the null hypothesis is in reality it's false and we accept it. In this video, we will learn about some of the machine learning and deep learning interview questions. So let's begin with our first question. The first question is how to detect outliers in data. So in data analytics and machine learning, you often find data points that lie at an abnormal distance from other points in a random sample from a population. Those are called outliers. Now, outliers in data can significantly impact any prediction analysis. There are majorly three different methods to treat outliers. First, we have the univariate method. It is one of the simplest methods for detecting outliers. The univariate method uses box plots. A box plot is a graphical display for describing the distributions of the data. Box plots use the median and the lower and upper quartiles. This method looks for data points with extreme values on one variable. Next, we have the multivariate method. So the multivariate outliers can be found in an n-dimensional space having n features. We look for unusual combinations of all the variables in this method. Finally, we have Minkowski error. This method reduces the contribution of potential outliers in the training process. The Minkowski error is a loss index that is more insensitive to outliers than the standard mean squared error. Now moving on to the second question, what is a confusion matrix? So a confusion matrix is a table that is used to describe the performance of a classification model on a set of test data for which the true values are already known. The target variable has two values, positive or negative. The columns represent the actual values of the target variable, which you can see here. The rows represent the predicted values of the target variable, which you can see here. Now there are four important terms that are related to confusion matrix. First, we have true positive, which is this one. So in true positive, the predicted value matches the actual value. So the actual value was positive and the model also predicted a positive value. Then we have true negative, which is also represented as Tn. The true negative depicts the predicted value matches the actual value. Now the actual value was negative and the model predicted a negative value. Next we have false positive. Now false positive is also known as type 1 error. In false positive, the predicted value was falsely predicted. The actual value was negative, but the model predicted a positive value. And finally, we have false negative. Now false negative is also known as type 2 error. So in false negative, the predicted value was falsely predicted. The actual value was positive, but the model predicted a negative value. Now moving to our third question, which is explain the ROC curve. Now the ROC curve is one of the most important evaluation metrics for checking the performance of any classification model. ROC stands for Receiver Operating Characteristic. Receiver Operating Characteristic or ROC curve is a method to compare the diagnostic tests. The ROC curve is created by plotting the true positive rate against the false positive rate at various threshold settings. So here on the y-axis you have the true positive rate, on the x-axis we have the false positive rate. The true positive rate indicates the proportion of observations that were correctly predicted to be positive out of all positive observations. Similarly, the false positive rate is the proportion of observations that are incorrectly predicted to be positive out of all negative observations. You can take an example. Suppose in medical testing, the true positive rate is the rate in which people are correctly identified to test positive for the disease in question, let's say the coronavirus testing. ROC does not depend on any class distribution. This makes it useful for evaluating classifiers predicting rare events such as diseases or disasters. Now moving to the fourth question, we have what are the assumptions for linear regression? So linear regression analysis is used for modeling the relationship between a single dependent variable y and one or more feature or predictor variables. Some of the important assumptions for linear regression are, so first, they should have linearity. So linear regression needs the relationship between the independent and the dependent variables to be linear. It is also crucial to check for outliers since linear regression is sensitive to outlier effects. Next we have homoscedasticity. Homoscedasticity illustrates a situation in which the error term, that is, the noise or random disturbance in the relationship between the features and the target variable, is the same across all levels of the dependent variables. Third, we have independence. So observations should be independent of each other. Finally, we have no multi-collinearity. So there should be little or no multi-collinearity. Independent variables should not be too highly correlated. Now moving to our fifth question in our list of interview questions. The question is, what is regularization in machine learning explain the L2 regularization. So regularization is a machine learning technique that is used to reduce the errors by fitting the function appropriately on the training set in order to avoid overfitting of data. So overfitting happens when a model learns the detail and noise in the training data to the extent that it negatively impacts the performance of the model on new data. So here you can see we have a nice plot which shows how overfitting of data can be visualized, and here we have a good fit line over the same data points. So this is also known as the regression line. Now L2 regularization is also known as ridge regression. So ridge regression modifies the overfitted model by adding the squared magnitude of coefficient as a penalty term to the loss function. So on the right you can see a set of data points plotted, and we have our linear regression line, and here we are calculating the cost function for the ridge regression line. So our cost function is actually loss plus lambda into summation of w squared, where loss is actually the sum of squared errors or squared residuals. Lambda stands for penalty for the errors. W is called the slope of the curve or line. Okay, now consider a case where there are 2 points passing through the linear regression line. Now if you calculate the cost function, we get the value as 1.69. So here we have assumed that loss is 0 since the 2 points lie directly on the line. We have taken lambda to be 1 and w is 1.3. So if you use this function or this formula, you get the cost function as 1.69. Now moving ahead, let's consider another situation where we'll calculate the same cost function for the ridge regression line. There is some loss for both the points as they are not on the same line. So here you can see the sum of squared residuals is 0.05, which actually is the sum of 0.2 square. I'm assuming this as 0.2 and 0.1 for this one. So if you square both and add it, the value is 0.05. A lambda is again 1 and w we have assumed to be 0.6. Now if you find the cost function, the value is 0.41. Let's draw the linear regression line and the ridge regression line with all the points. We find that the ridge regression line has the best fit since its cost function is less. Now coming to the sixth question, what are the different methods to split a tree in a decision tree algorithm? So there are 3 methods to split a decision tree. First we have variance. So reduction in variance is an algorithm that is used for continuous target variables. This algorithm uses the standard formula of variance to choose the best split. So here you can see the standard formula of variance, which is summation of x, that is all the individual points, minus x bar, which is the mean, squared divided by the total number of observations. Now the split with lower variance is selected as the criteria to split the population. Now the steps to calculate variance is, you need to calculate variance for each node, and then you need to calculate for each split as the weighted average of each node variance. Moving ahead, the second method we have is information gain. So information gain is used for splitting the nodes when the target variable is categorical. It works on the concept of entropy. Now the degree of disorganization in a system is known as entropy. So here you can see the formula for information gain, which is 1 minus entropy. Finally we have Gini impurity. So Gini impurity is the probability of incorrectly classifying a randomly chosen element in the dataset if it were randomly labeled according to the class distribution in the dataset. So below you can see the formula for Gini impurity. So we have 1 minus summation of pi whole square, where n represents the number of classes and p of I represents the probability of randomly picking an element of class I. Now moving to the 7th question. So the question is, how do we find the optimum cluster value in k-means clustering algorithm? Now there are 2 methods to find the optimum cluster value. So first we have the elbow method, which is one of the most well known for finding the optimum number of clusters. So in this method you need to calculate the within cluster sum of squared errors for different values of k and choose the k for which within cluster sum of squared errors first starts to diminish. So in the below plot of squared errors versus the number of clusters k, you can see at k is equal to 4, the squared error starts to diminish. So hence our optimum k value is 4. Next, we have the silhouette method. So the silhouette method measures how similar a point is to its own cluster compared to other clusters. The average silhouette method computes the average silhouette of observations for different values of k. The optimum number of clusters k is the one that maximizes the average silhouette over a range of possible values for k. The silhouette score reaches its global maximum at the optimal k. So in our case, the average silhouette reaches maximum at k is equal to 2, which you can see here. So our optimum cluster value will be 2 here. Moving ahead, the 8th question in our list is, how does the pooling layer work in a convolutional neural network? So the pooling layer performs a downsampling operation in order to reduce the dimensionality of the feature map. So in the pooling operation, you slide a two-dimensional filter over each channel of feature map and summarize the features lying within the region covered by the filter. It is a common practice to periodically insert a pooling layer in between successive convolutional layers in a convolutional neural network architecture. So the pooling layer operates independently on every depth slice in the input and resizes it spatially using the max operation. So in the diagram shown here, you can see we have a rectified feature map. We are using a 2x2 filter and performing a max pooling operation. So consider this as the filter. If you perform the max operation over the values, let's say 0, 5, 3 and 1. So considering this one, our pooled feature map maximum value will be 5. Similarly, for this chunk of data, it is going to be 7. Next, if you slide the filter over this square frame, you get 8, and similarly here you get 6. So this is also known as a pooled feature map. Moving ahead, the 9th question in our list is, how does LSTM network work? So long short-term memory networks are a type of recurrent neural networks that are capable of learning order dependence in sequence prediction problems. So remembering information for long periods of time is practically their default behavior. Now LSTMs also have this chain-like structure which you can see here, but the repeating module has a different structure. So instead of having a single neural network layer, there are 4 interacting in a very special way. Now you can see these are called as gates. These gates contain sigmoid activations. A sigmoid activation is similar to the tanh activation. Instead of squishing values between -1 and +1, it squishes values between 0 and 1. An LSTM has 4 gates. Now these are called forget, remember, learn and use or output. So if you see this, in the first step, we use the forget gate that decides what information should be thrown away or kept. The information from the previous hidden state and the information from the current input is passed through the sigmoid function. Values come out between 0 and 1. So if the value is closer to 0, it means you need to forget that information, and if the value is closer to 1, it means you need to keep that information. Next, we have the input gate. So the input gate is used to update the cell state. First, we pass the previous hidden state and the current input into a sigmoid function. That decides which values will be updated by transforming the values to be between 0 and 1. 0 means not important and 1 means important. You also pass the hidden state and current input into the tanh function to flatten the values between -1 and +1. This helps to regulate the network. Then you multiply the tanh output with the sigmoid output. The sigmoid output will decide which information is important to keep from the tanh output. And finally, in step 3, we have the output gate. This output gate is used to decide what the next hidden state should be. First, we pass the previous hidden state and the current input into a sigmoid function. Then, we pass the newly modified cell state into the tanh function. We then multiply the tanh output with the sigmoid output to decide what information the hidden state should carry. The output is the hidden state. The new cell state and the new hidden state is then carried over to the next time step. Finally, talking about the last question in our list of interview questions, we have explain the concept of gradient descent in deep learning. Now, gradient descent is an optimization algorithm which is mainly used to find the minimum of a function. In machine learning, gradient descent is used to update the parameters in a model. Parameters can vary according to the algorithm, such as coefficients in linear regression and weights in neural networks. You can see we have these maps, and on the y-axis we have the loss, on the x-axis we have the weight, and here we are trying to find the local minimum or the global minimum. Now this gradient descent method is used to minimize the cost function and update the parameters of the learning model. The gradient always points in the direction of the steepest increase in the loss function. The gradient descent algorithm takes a step in the direction of the negative gradient in order to reduce the loss as quickly as possible. To determine the next point along the loss function curve, the gradient descent algorithm adds some fraction of the gradient's magnitude to the starting point. Now this process is repeated to find the global minimum. So that brings us to the end of this video tutorial on Data Scientist full course. I hope it was useful and informative. Thank you for watching. Stay safe and keep learning.